All of you had a comfortable stay? Yes, no? How many commuters do we have? Those who are commuting every day? Oh, yeah, we do have. I'm surprised. Okay. Otherwise, hostels, okay? Okay. Right. I think I'll get started, kick off today's lecture. In fact, yesterday we had a few sessions on rheology. So we introduced to you what rheology is all about, and that was from the perspective of cement paste, where we're looking at cement paste as a fluid, right? And at that stage, then we are not exactly separating out cement paste and looking at constituents. So we say cement paste is like one continuum, right? So it's like one fluid, and we try to assess its behavior when we shear it, because flow is all about shear. You cannot induce flow unless you shear the any fluid, right? A fluid will flow only when you shear it. So we need to understand how a fluid flows under applied shear, right? Now, shear is a generic term. Shear can be a force or a stress, right? And oftentimes we have control over the force part of it. We do not have control over the stress. Stress is something that is generated internally inside a material, whether it's a solid or a fluid. A stress is generated inside. We can visualize stress as if it is a resistance of any material, right? If it is a solid, it will be resistance to a shear strain. So what happens when you apply a shear strain to a solid? It will deform and it will come to a rest, right? It will come to rest in a deformed state. And we treat that as if it's a quasi-static or a static problem. That's how, and basically the entire field of elasticity, as we call it, builds on that concept. And then we go on further to get into structural mechanics, where we do analysis of complicated structures and all these things. But the fundamental premise there is statics. The object is at rest, it's not moving. So what is the independent variable there? The strain, right? And what is the stress? It is the resistance that is generated from inside the material. And directly measuring stress is very difficult, right? So what do? When we're doing measurements, we have a control on the force, right? We can measure the force and we can measure the deformation. What do? We somehow infer the state of stress. Infer. Even when we are doing a simple static test like a tension test on a steel bar, we only have control on the force. We don't know what is the state of stress inside the material. We infer it. We make certain assumptions, right? What assumptions do we make? Suppose I take a steel rod and I do a tension test on it. What assumptions do we make? We assume that the stress is uniform across the cross section. Fundamental assumption. Has anybody bothered to check it? No, it's an assumption. Under that assumption, we derive the state of stress even for a solid. Same thing applies for the fluid also. I have control on the torque. That torque generates a shear stress in the fluid. What I try and do is try and create, as far as possible, idealistic or ideal boundary conditions so that I can create an idealized stress state in the fluid, right? Now, in the case of a fluid, when I apply a shear stress to it, what's going to happen? I'll produce flow, which means I'm not limited to strain only. What I start generating is a strain rate. It starts shearing and it continuously shears, right? So how did we measure continuous strain deformation of a fluid? Strain rate. That tells me how it is deforming, right? It's a dynamic state now. So that relationship between the shear strain rate and the shear stress is what we are looking for when we are trying to do the rheological characterization of a fluid. That is the essence of rheology, trying to understand how a fluid responds to a strain rate, right? And that was what last lecture was all about. Now what we are trying to do is to build up. We're trying to build up, knowing this information, how do we proportion concrete? So we're now going to the next scale, right? And so what is the next scale? Now aggregate come into the picture. And I think in the last lecture, Narayanan kind of left you in a very titillated position where he said, oh, I'm going to put some aggregate and then we'll create packing with this thing. So that's the essence of it. The minute you introduce aggregate, there one has to be a reason why you introduce aggregate. Okay. The second thing is we have to deal with the consequences of bringing in aggregate. Okay. So let's deal with this. Let's first try and understand how we've been doing it for regular concrete. And then, of course, once you get into 3D concrete printing, once we understand the causal links here, and they're embedded in our code, whether we believe it or not, then we extend it to the case of developing concrete mixtures for 3D concrete printing, right? So just again to recap, from rheology perspective of a cement paste, we understood that we have a Newtonian fluid, right? What is a Newtonian fluid? We said the stress, right, is directly proportional to the strain rate. That means if I try to deform it faster, the fluid will give me a higher resistance. Fundamentals of a Newtonian fluid. Then the next level of complication is when you have a fluid that has a yield stress. So what happens there then? If you look at the plot between gamma dot, which is the strain rate, and tau, which is the shear stress, it's a straight line that starts at origin for the case of Newtonian fluid. The minute I introduce yield stress, what happens? That curve shifts upwards. You get an intercept. What is that intercept? That is the yield stress. Why is the yield stress happening in this fluid? It's happening because there is something inside the fluid that is giving us a resistance to shear. When I apply some shearing to this fluid, internally there is some structure that is resisting it. Okay, and I have to overcome that structure to produce flow. Now, that resistance that the fluid gives to initiating the flow is what we are calling yield stress. Now, the question is, how do we measure it? To measure it, I have to use some protocol. Whether I call it a constant strain protocol, constant strain rate protocol, or a strain rate ramp, there are different protocols. And then it's all about inferring what the liquid is up to, what the fluid is up to, right? So now, well, that was all about paste, and now we're talking about concrete. The minute we come into concrete, this is a picture I've shamelessly stolen from the web. So this is typically what a concrete looks like, right? So we know that we have coarse aggregate, we have fine aggregate, and of course cement, water, and some admixtures. The proportions of this is what we are basically interested in when we are trying to proportion our concrete, right? So now, what does concrete look like? If you want the real technical description of concrete, this is what we are trying to describe, right? If somebody was to look at it, one is that it's a bit of a stretch if you were to call this a fluid. It doesn't look like a fluid in any sense of the word, right? But it behaves like a fluid. I mean, look at this. Would you call it a fluid? Because our sense of our imagination about a fluid is something that looks smooth, it's continuous, right? Applying those principles here is a bit of a stretch, but it behaves like a fluid, right? It flows. As you can see here, there's concrete being dumped off a chute, right? And it's flowing. So therefore, we say it's a fluid. But it's actually a very complex heterogeneous suspension. Right? What is the suspension? When you have solid particles which are suspended in a fluid medium. That is a simplistic definition of a suspension. Right? So, and that itself you'll see will become very complex once you get into concrete and trying to proportion it. So for now, we'll just simply stick to this definition where we say it's a complex heterogeneous suspension. Heterogeneous because there are different types of particles. It's not just one type of particle that we have there. So of aggregate of different sizes, in a paste, which is basically cement paste or a cementitious paste, okay, which basically is my fluid medium. Even that definition becomes complex because what do you call a fluid? We'll just see in the next slide is itself not very clear. So at some level of idealization, if I was to look at it, I could look at concrete, which is shown here, as if I have a fluid medium, which is at some level I can call it as a paste. That is the fluid medium. And basically, when we talk about a fluid, we immediately think of rheology, right? So the rheology of the fluid is, if I was to ask you, can you give me the property of a fluid? Your first question would be, which rheological property would you want me to give you? Because we're talking a fluid. Therefore, if I look at this as my concrete, I can separate out the paste and the aggregate. I can separate out two phases in there, right? The so-called fluid phase, which has a certain rheological component or which has a rheological behavior, and that is my fluid component. Then I have the solid component, which is the aggregate, which basically serves as the filler, is basically filling the space in there. And each component has a role to play in there, as we'll explore. When it comes to the aggregate, the two things that I will be looking at least in a concrete proportioning, will be the content of aggregate. How much aggregate do I have in the concrete mix? And the packing. This plays a very important role. I'll just touch upon packing, introduce to you packing. I think next few lectures are going to be heavy hitting on packing, where you'll get into the deep end of packing. I'll just merely introduce what packing is all about. So, what is it that we are proportioning a concrete mixture for? We're basically trying to come up with the proportions of these components, the fluid component and the solid component. How much should the fluid be? How much should the solid be? Right? And what is the purpose? Well, we're trying to achieve concrete with a certain strength and durability, workability and flow characteristics, and ultimately economy. I want to save money at the end of the day, right? These are my threefold objectives with which I try to develop the concrete mix designs. And for in India, we follow this IS 10262, which is our base code. It's been revised, that I remember, twice. Now, of course, we have this in the bilingual format, which I find rather confusing, but it is available in the bilingual format now. And this gives us the general guidelines. And what I want to do today is look at these guidelines that are available in IS 10262 and understand the basics of it. And believe it or not, a lot of these guidelines that have come into this code come from fundamental ideas of packing and what we understand about cement hydration and cement rheology. Okay, except they're stated in a layman language, because they don't expect everybody or a practicing engineer to be understanding the concepts of packing or rheology. So they're framed in such a way that thou shalt, that you will do this, right? And in doing so, they hope that some basics are covered. And what are our objectives in doing the concrete mix design? Strength and durability, workability or flow, and economy. Now, let's hit the strength component. So, if you read IS 10262, you'll find this generic statement where they cover all bases. They say, well, look, strength of concrete depends upon all of these factors. It depends upon cement, supplementary cementitious materials, the aggregate, maximum size and grading, surface texture of aggregate, and whole bunch. That notwithstanding, right, the most important characteristic that defines the strength of concrete is the water to cement or water to cementitious material, the ratio of that. And we all know, if I reduce the water to cementitious material, my strength goes up. But what is the consequence of that? If I was to reduce the water to cement ratio, let's just keep it at water to cement as my cementitious material, what would happen? Suppose I decide on a certain proportion of paste and aggregate. Right? If I decrease my water to cementitious material or water to cement material, what would happen? Now, my cement content in the concrete would go up, right? Because the proportion, I'm fixing them by masses. Let's say I say 40% of the concrete is going to be paste, 60% is aggregate. Now, what defines the cement content in this 40% of the paste is the water to cement ratio. If the water to cement ratio is low, cement content in the concrete will go up. Two things happen because of that. What are two things that happen because of that? My cost goes up. There are no free lunches. When I try to do something, something else goes wrong. So what happens when the cement content goes up? My economy goes for a toss. So unless I have a really good reason, I'm not going to do it. Right? What is the other thing? The other thing is that the rheology of the paste depends upon water to cement ratio. So my workability will take a hit. We have to expect both of these things to happen. But fundamentally now, this is the graph that is available in IS 10262, which relates the water to cement ratio to the strength. And we know it's an inverse proportion. This is now actually given in 10262. They give it as a master curve with enough riders there saying that you have to test this and establish this curve for your own water to, for your own cement type. right? But generic behavior is this, that we expect that we would see a decrease in the strength with the water to cement ratio. That's expected from this the cement paste. But please remember that if I start going up this curve in the hope of achieving more strength, I'm doing two things. I'm increasing the cement content, and at the same time, I'm making my paste thicker, more viscous, yield stress increases, and all the wonderful things that happen because of that. So now let's explore what happens when we start tinkering with these and what other levers do I have. So when you're trying to do a mixed design, you have a few levers in your hands, right? When all else fails, we'll say, fine, now I have this. Now let me bring in some admixtures. That is the role of admixtures. Admixtures are basically there that say, okay, I played with my fundamental components, cement, water, and aggregate. Okay, I'm now stuck with this because I have hit two of the three boxes, right? The third box, now how do I manage the third box, right? So at some point you'll find that you cannot manage all three boxes with just water, cement, and aggregate. So I need some other lever. That's where the admixtures come in. So what would we expect from an admixture? It is something that I would use in a very small quantity so that the basic proportioning does not get upset. I've already done that. Now, if I start introducing a third component, which starts playing around with my basic composition, then everything else changes. So it has to be used in such a small proportion that it doesn't upset what I've done with my basic proportioning. And it introduces some change in the behavior or modifies the property some way, which I can't do just with the basic proportioning. Okay, so admixtures are my last resort. Okay, which is the last lever that I have in order to tick all three boxes. Okay, right. Now, so we said strength, we've looked at it. Water to cement ratio is my primary lever that I'm going to press. The second thing is the durability. My concrete has to be durable. Okay, for this, there are provisions that are given in IS 456, which is the parent document for reinforced concrete design. There are a few provisions that are tucked away in here, which basically help guide you when it comes to assessing the issue of durability, right? Now, what are the durability concerns that we have? If you go to 456, which is there is a 8-point, the early sections in there, deals with concrete mix proportioning. And there, we talk about exposure conditions, right? So there are different exposure conditions that are listed that go from mild to extreme. I'm presuming everybody is familiar with this, right? Based on that, a certain maximum free water to cement ratio is prescribed, right? So basically, durability is somehow tagged to this water to cement ratio. The understanding is that if you look at the what makes cement paste denser, you reduce the water to cement ratio. What you get is something that is less porous, right? And that will basically prevent ingress of the deleterious materials, which could be chloride ions or sulfates from outside. So if you're looking at durability concern for concrete, the primary concern is to keep the external agents outside, not let them enter into concrete. How can I do that? Well, aggregate at some level are inert. They're not going to allow things to get in. How will things get in? Through the cement paste medium that is in the concrete. How do you control that? With the water to cement ratio. So this is prescribed. It's prescriptive. Okay. They say that we suggest this free water to cement ratio should be capped. And you see that when you go from mild to extreme, the free water to cement ratio that they cap at decreases. Two things happening there. When I decrease the water to cement ratio, what happens? Cement content increases, okay, and the hardened cement paste would be less porous. That is our understanding. Okay, so that is the basis of durability and mix proportioning, considering durability when we're talking about concrete mix design. So here what you have to do is, if you're bringing in durability concerns, you look at the parent document IS 10262 and use it in conjunction with IS 456, which basically combined gives you a measure of durability. There's another very important measure that oftentimes is overlooked about durability. Now, like I mentioned, there are no free lunches. If you keep on increasing your cement content, there are other things that happen. It's not just that my cost goes up, or if my water to cement ratio decreases, that the paste becomes thicker, it becomes more viscous, it has more yield stress. Of course, these are all consequences that we deal with, that to live with. But more importantly, what happens is, if you start increasing your cement content, the paste would shrink more. It would produce a lot more heat. These would then produce unintended consequences of cracking because of shrinkage, because of thermal effects, right? So how does our code handle that? They prescribe a limit of 450 kgs per cubic meter of cement in the concrete mix. They say, look, this is a limit, okay? If you go beyond this, then expect that you will increase the risk of cracking. That's what they say. So it's a commonsensical provision which addresses that durability issue when it comes to concrete, right? So these are all things that are already inbuilt in our codes, and most of these are prescriptive in nature, where we're putting limits. We're saying you will not do this, okay? At the core of it, at the background of it, is this fact that we expect, if you start increasing your cement content beyond 450 kgs per cubic meter, expect heavy cracking in concrete because of shrinkage, and it happens, okay? Now, so that is as far as how we've addressed the strength issue and the durability issues in our mix design, the first box, right? Now, the next two boxes. The next box is the one that's actually quite tricky when we start getting into workability, okay? Now, workability, fluid flow behavior, we need to understand what are these, right? What is workability? Well, if this is the technical description of it, which basically says that for a concrete defined as a composite, the characteristic that is indicative of the ease with which mass plastic material, that means at some level, it is not that it is made of plastic, but the behavior is plastic. That means if I actually was to somehow force it to move, it would still move. Okay, this goes to the definition of concrete as defined being plastic or solid. Okay, when we say concrete is plastic, at some level we expect it to be a fluid when it is forced to flow, and that when it is deposited in its final position, it is able to conform to the final the fine forming detail. What is implied by that? Suppose I put concrete in a rectangular box. I expect concrete to fill every corner of that box. It has to flow, fill that. That is how I define my workability. If it doesn't fill by itself, well, if I force it, then it should fill. Okay. Now, how do we, if we were to look at it alternatively, what would be the alternative description of it? What we're looking at is the work or the energy that would be required to fill a form. How much energy do I have to put into this material to get it to conform, conform here? How much energy do I have to get to put into this concrete to make it conform, right, with my requirement? And conformity with my requirement is the entire form should be filled up thoroughly, completely, without any air gaps, right? Now, how do we measure flow? Well, the most common measure is this slump. That's what we all use. We are all very familiar with this. But remember one thing, please, that slump is a static measure. What do? We fill a cone, we lift the cone, we let it come to rest. It is a static measure. It, in a sense, doesn't really tell us anything about the flow behavior. Why? Because when we are measuring it, it is already in a static state. It is rested. Okay, but what is peculiar about the shape is if you actually contrast this with what you get with water. Suppose I was to do this with water, what would happen? The minute I lift the cone, essentially you would get a flat surface. Water cannot create or cannot sustain these level differences. So what then allows this concrete to have this level differences? The yield stress. Concrete is a material that has yield stress, right? Now, what would be a good measure of workability? I would say that perhaps this is a good measure and a derivative of this that we are using in printing lately, which is actually called the VB test. What we do in here is that we take the cone and of concrete. When you lift the cone, of course, and there is a container here. When you lift the cone, it's not going to fill the container. Then what do? We measure the energy that it takes, right, to make it fill the form, this container, right? So we would actually be vibrating the concrete. When you're vibrating, what are you doing? You're inducing energy. You're putting energy into the concrete, which agitates the concrete and gets it to flow. And in doing so, it will fill the container. So what do I get from here? Is actually a measure of work that I'm putting in to get the concrete to conform with the my requirement, fill the form, right? Now, what happens when it goes from here to here? It doesn't want to go by itself. And we'll see the reason a little later, but we force it by putting energy in there, right? Now, if concrete is workable, I put less energy into it. If it is not workable, I have to put a lot of energy. It'll take a lot of time because I count the seconds that it takes to agitate the material. A lot of work goes into it before I can get it to fill this form. Now, what happens when it goes from here to here, when I'm forcing it to fill the form? At some level, if you think of concrete as made up of aggregate and paste, then the aggregates would move relative to each other. They have to. Because if they stay in the same configuration as they were when they lifted the cone, then there'll be no movement possible. How will the movement happen? When the aggregates are moving relative to each other. Okay, so these aggregates have to move relative to each other. How easily can they move relative to each other? There are, of course, always the causal effects. The causal effects are, you'll say, well, if the aggregate has a high surface area, or if the surface is rough, they will basically stick to each other, they'll not move. Yes, given. That's one characteristic, right? So you have the primary effects which impede the movement, and then you have the secondary effects. So what we have to look at is the primary effect that would prevent this fellow from filling this form, right? Which basically happens when the aggregate move relative to each other. What stops that from happening? And if that effect is something I cannot manipulate with my primary levers of the proportions, then I have to bring in admixtures to facilitate that. Okay. Now, this is the idealization. I'm going to revisit this just for a few minutes. If you look at concrete, I can look at it as if it's made up of aggregate in a fluid medium that is shown in the light gray here. The aggregate is shown in orange. Now, what scale of representation should we use? What should I call this fluid medium? My one choice could be that I consider concrete as an idealization of coarse aggregate in mortar. So what happens then at that scale of idealization, all the oranges here are coarse aggregate. The gray here becomes the mortar. So what happens then? My fluid medium becomes mortar. Why is that important? If I have to get this fellow to flow, the rheology of the fluid medium becomes important. That means then if I'm looking at that scale of idealization, I should have the fluid behavior of mortar in my hands, right? The second level I can also think of is some coarse aggregate, some of the coarse aggregate or some of the fine aggregate that we use become a part of the gray fluid. Okay, and some of the fine aggregate are considered as a part of the orange dots, the aggregate. Now, this is also done. One place where this is done is when we do SCC, self-compacting concrete. Those of you who've done self-compacting concrete know that we pack it with fines. What happens then? We actually take the fines and count it towards a fluid, right? Although they are aggregate, we count them towards a fluid, and the fluid behavior of that fluid medium, which is now paste and some fines, it becomes important in controlling the flow behavior of concrete. And the third and the most generic argument is where all aggregate, right, fine coarse, are sitting in a paste medium. So the gray here now becomes paste, and the oranges become all aggregate, which is coarse and fine, right? So this is the primary level of discretization that I can adopt, where basically everything orange is all aggregate, everything gray is paste, cement paste, right? There's also one more level of idealization. I will not get to that here, but that can also be done, where within the cement, I can look at the cement grains and also look at that as solids and treat only as water as my fluid, but then that becomes a little trickier to handle. What I need to do is understand the role of this fluid medium, whatever level of discretization, and the solids in controlling the flow of this material. Okay, and I also have to bring in economy into my concrete, right? So these are two things that I want to do. How do I control these things? What are the levers in my hand? One is the relative content of fluid. How much fluid medium do I need? Okay. And for now, let's look at just this level of discretization. What do I mean by that? Cement paste is my fluid. All aggregate are my solids. Okay. Now, I'm interested in controlling the flow behavior and also try to adjust the relative content of fluid in this solid medium. And this becomes important. The relative content of the fluid medium, the relative content of the paste becomes important from an economy perspective, because I want to minimize my cement paste in the concrete, right? Now, so let's look at the aggregate. What is it that we expect from our aggregate in concrete? The aggregates are treated as inert fillers. Basically, they are inert fillers. So what is their job? Pack the volume, right? So what am I hoping to achieve with the use of aggregate? Minimize my cement content or paste content, right? That is the primary role of aggregate. What else would I expect from them? I would expect dimensional stability. I want the aggregate themselves to be dimensionally stable, right? Stiffness, toughness, and wear resistance, and all of these properties essentially come from the aggregate. So I need something, some filler that is strong and durable, right? And it should basically be I address this issue where I try to reduce the cement demand. I want to pack my volume with this inert filler as much as possible. Okay, so that I can reduce my cement content, because by its very nature, I expect it to be an inert filler, right? Just packing the volume. And typical concrete, 60 to 80% by volume is aggregate. This is from years of experience. This is where we are headed to. In fact, now we are starting to get this number starting to creep up a little bit more. And economy, of course. Aggregate are cheaper than cement, right? So it makes sense. Use more of the cheaper material, hack the volume, right? Reduce your cement content, okay? And in the process also provide stiffness to the concrete and strength and toughness. These characteristics would come from aggregate. So now with my first objective, which I want to minimize the cement content, I have to look at this packing. Broadly, how would we look at packing? Suppose I was to pack a unit volume. I pack in solids in there, and I look at the solid volume as a fraction of the total volume. That's what I want to maximize, this packing density, which is basically the solid volume divided by the total volume. If I achieve a larger number, that means I've managed to pack more solids in there. Remember, whatever is not solid in here is basically paste. So if I go to concrete at the basic level of discretization, all the solids here are the aggregate. The light gray here would be paste. If more space is available for light gray, more the paste consumption, concrete becomes more expensive, right? So my objective with this packing would be to play around with the aggregates, decide on how do I maximize my packing density. That is what I'd be after. What are the rules that we typically follow? Well, whenever we do this packing, typically we fall back on these spherical models, okay? Because while they're not practical, nothing in nature is a sphere, right? And when we talk about aggregate, they are all irregularly shaped. Now, so why this? Well, because they help us understand. That is the basis. So if I look at spheres of uniform size and I try to pack a unit volume, maximum packing that's possible is about 74%. That's the Kepler's hypothesis or conjecture. And that comes when you go with a face-centered cubic arrangement. Okay, that's maximum that you can pack. And if you were to take the same spheres and dump it into this cube and do a random packing, that is try to shake the cube up rather than arrange it in a systematic manner, you would basically be limited to 64%, which means if I was making concrete with this thing, these spheres, I have to expect to use either 26% paste or 36% paste, okay, by volume, right? Now, how can I improve the situation is when I get into polydisperse spheres. What is a polydisperse sphere? Here we have a mixture of different sized spheres. So we are not using a single sized sphere for a good reason. The reason is that in polydisperse spheres, what do I expect? I want to arrange my spheres in such a way that I step down in sizes. I start with a certain size, start decreasing the sizes with the objective of maximizing my packing efficiency. I want to basically minimize that light gray space that you saw in the previous slide with the objective of reducing the paste content in the concrete. Now, so here, what is the role of the smaller aggregate in this? The largest aggregates would form like a primary structural framework, if you want to think of it, right? And within the gaps of the larger aggregates, you try to fit in your smaller aggregate. So if I now try to play this game, what is important? What is important is I have to have the right sizes in the right proportions, right? If the sizes are off, I cannot achieve good packing. If the proportions are off, I cannot achieve the proper packing. Both have to hit the right numbers, right? So we follow this thing called hierarchical filling. Suppose I was to give you different size spheres. You take the largest one first, hope to pack the gaps with smaller and successively smaller and successively smaller. And you basically try to maximize your packing. And what is important here? The sizes and the proportion of each. So suppose I start with a certain spherical size here. I have several options to fill the gaps, right? Starting with the simple, if I take the simple bubble diagram here, I have several options that are available to pack it up. Now, suppose I take my largest sphere here. I can go with this as my next arrangement, or I can go with this as my next arrangement, and so on. I can basically play around with these spheres. But if the proportions are off, so let's say I look at this particular arrangement here. This is my largest spherical size, followed by this, followed by this. Suppose I have too many of this size particles, what will happen? Packing will not happen smoothly, right? And we'll see a little later, there's this thing called the loosening effect that comes into play and becomes counterproductive. So what happens then? I have to make sure that my aggregate sizes are all available in the right proportion. And that brings us into this concept of grading. That is, if I have aggregate available in the right sizes, in the right proportions, then I call them as well graded. Now, what do I expect from a well graded aggregate? I expect that these would pack well. Okay. Now, a few other things to remember here, and that is when I'm talking about packing efficiency, I'm trying to maximize my aggregate content. Now, when we're dealing with regular concrete, we do not take it to some crazy height. We just try to leave it at some point so that we can minimize the cement content. But when it comes to some of the specialized concretes, like say UHPC, we take it to an extreme where we pay a lot of attention to packing. We pack it down to the micron and submicron scale. Here we restrict ourselves to packing up to perhaps some millimeter level scale. But two important things to remember is, suppose and this is just a numerical example, which is very simplistic, to explain two things. One is, suppose I start with a square and try to pack it with circles. Right? It is not at all realistic in a real sense, but helps understand the concept. And the concept is, am I better off starting with a larger sphere initially and then pack the spaces between these with smaller sized aggregate, or start with a smaller size to start with? Where would I get a better packing efficiency? Now, heuristically, you can understand from here that you're better off starting with a larger size. If your initial diameter is large, you can actually achieve a better packing efficiency, because the larger sizes would basically create a skeleton with larger sizes, which I could then subsequently pack with smaller sizes. But of course, grading is very important. But here the role of the larger aggregate size is important in achieving the larger packing of aggregate, larger packing efficiency or higher packing efficiency. The other thing is, what happens when I increase the diameter of a sphere? Well, the volume of the sphere scales as d cube, right? Whereas the area scales as d square. So when I go from here, say, and come to this point here, what have I done? Even if the volume was same for these light blue circles, what has happened for this fellow? The surface area decreases, right? So when I deal with larger spheres, my surface area becomes smaller, right? So I'm able to achieve a larger volume with a smaller surface area. This is another thing that we need to remember. So if I start with a larger initial sphere diameter, right, I will be able to achieve a better packing efficiency, and B is that my total surface area that I have to deal with is going to be smaller. Two things that we have to bear in mind. And of course, the aggregate that we are typically dealing with, we are classified in IS 383, which is the parent code for aggregate. Right? Here we break them up into two sizes. The coarse aggregate, which are basically the larger aggregate, which are either crushed stone or gravel, or uncrushed stone or gravel. The uncrushed stone, the nice smooth stones, have now disappeared. Most of our aggregate is coming from crushing, which is a very violent operation. And basically what we end up with, something which has a very irregular shape, rougher surfaces, and this is what we have to deal with. So where are spheres and where are these particles, right? But whatever we learn from spheres still teaches important lessons. And those lessons that we learn from packing spheres still carry over here. And that is important to remember. Now, grading, well, ASTM, this is a curve from ASTM where they basically give two bounds, upper bound and a lower bound. And if your aggregate size distribution, the particle size distribution, fits between the upper and lower bounds, we consider those aggregate to be well graded. What does that mean? Well, if they're well graded, we expect that the proportions are available in the, or the sizes are available in the right proportions. I expect that packing is going to be good at some level. Now, why is this not precisely a line? Why do I get a band over here? The reason I get a band over here is because I'm not dealing with spheres. These are irregular shaped. So, and every time I crush aggregate, I'll get a different shape distribution. It's not going to be the same. And remember, packing game is all about packing the volume. So the shapes matter. So I cannot give you a precise mathematical relationship. What we typically give you are these bounds, upper and lower bounds. And we say, well, if it fits in those bounds, we expect the aggregate to be well graded. IS 383 gives us similar bounds. We basically have, depending on the largest size we start with, we get these bounds that are given, and we say that, well, if it fits between those bounds, then we have well graded coarse aggregate, right? Again, just to reiterate, what do I expect from well graded aggregate? I expect them to pack well, right? The next size, fine aggregate. Okay. Now the question is, why do I need two classifications of aggregate? Why do I need fine and coarse? Remember, it's all about packing. Okay. If I only use one size sphere, there's only so much volume I can pack. How can I pack the remaining volume? I need to bring in smaller aggregate that will go and sit between the gaps between the larger aggregate. What are those fine aggregate? These are the fine aggregate, right? So what do we call our fine aggregate? It is anything that is smaller than 4.75 millimeters, right? Or majority of it, but for 5%, passes through a 4.75 millimeter sieve, is called a fine aggregate. Previously, we used to get this naturally available sand, which we used as fine aggregate. This has become a luxury, at least in the southern states, we don't get this anymore. In the northern states, perhaps sand is still available. Not sure, but I think it's still available. What we are making do with is this crushed aggregate. So what do? We go back to the crushing process which produced coarse aggregate, only crush it finer, and then call it fine aggregate. But the game is the same. What I want to do is achieve maximum packing. So look at packing of the coarse aggregate. After I'm done with the packing of the coarse aggregate, there'll still be a lot of gaps left between the coarse aggregate. And those I hope to fill with this finer aggregate. Right? Now, when it comes to fine aggregate, this is how 383 deals with. We actually put it into zones. Now, the question is, why put it into zones? Why not deal with it like we did in coarse aggregate? Why not just have one master curve or something which says, if it passes this, then it is well graded? Now, the reason for this is that a lot of times when it comes to finer size particles, it's very difficult to precisely control the size distribution. I cannot really precisely control how I'm crushing it. The second thing is the origin of fine aggregate. It started as naturally available sand, in which case I had no control over the size. Whatever I got naturally, whatever size distribution was available, I used it. So in that case, then it was convenient to basically put it into one of these zones, right? Now, why these zones are important, I'll explain in the next few slides. So the whole idea is, if you take fine aggregate, you basically try to see which of these zones it fits into based on its size distribution. And basically, we have these 4 zones that go from 1 to 4. And if the fines are increasing, the fine content is increasing, basically you're going from zone 1 to zone 4, right? It becomes finer and finer as you step into zone 4. Right? So when it comes to coarse aggregate, we insist on some size distribution because at some level I can control it. I'm crushing it, I control it. Right? This invariably, if I'm dealing with naturally available material, then there's only so much I can do to control the size. So I live with it. What do? I say, well, I'm going to put it into a zone. And what is the game that I'm playing here? It's always about packing. Remember that. Right? So this is the game that I'm trying to play. Okay, so if I take, let's say, coarse aggregate and fine aggregate, again, whenever I illustrate, I go back to spheres, knowing full well that this is not reality, but the lessons I learn here can be ported into my real life. Now, what would happen if I try to pack coarse aggregate, which are well graded supposedly, with fine aggregate, which have their own distribution? Well, if I try to pack them up, I expect the smaller aggregate to go and pack between the gaps of the larger aggregate. And that's a winning game for me. So if I look at percentage of voids, and let's say I start with naturally crushed aggregate, this will start decreasing as I increase the percentage of sand up to a certain point, right? It'll hit a minimum and then it'll start increasing again. So what happens after this point here? I've achieved a minimum. I cannot give you a mathematical description of this fellow. I mean, I cannot tell you just by looking at it, okay, this is the mathematical equation you can use to come to this number here. It's empirical, right? I come up with this from experiments, from experience. But I know the fundamental theory is this, which comes from spheres, circles, which I can describe mathematically. So, and then after a certain point, what happens if I keep on increasing the sand or the fine aggregate? It starts making space for itself. And in the process, what happens then? The void percentage increases again. So there's a certain minimum that I get, right, of the percentage of voids, which when I have the right proportion of coarse and fine, right? And that minimum percentage would depend upon this crushed aggregate, what I'm starting with, and what I'm filling it with. Okay. So coming back to the packing models, I'll describe how this plays out in the code a little later. The spherical packing models would help us understand the basics, okay, as to what is the cause and effect. Okay, we've understood two things. One is, if I want to make an informed choice about packing, I have to go with hierarchical packing. That is, I cannot go with spheres of one size. I need to stack my sphere sizes. There'll be a certain optimum. If I overdo it, not going to help either, right? Then maximum aggregate size plays a role. How? If I start with a larger initial size, I hope to hit a larger volume of solids, which means I improve my packing density. And that knowledge I gain from playing with spheres is going to be smaller. Now let's see how this plays out in our IS 10262. Packing is addressed in this table here. We don't realize it, but it's built into the table. How does it play out? Well, here what we do is we decide the proportion of coarse and fine aggregate, right? So if you look at it, starting with the nominal maximum size of aggregate, you presume that these aggregates are, which are coarse aggregate, are well graded, which means they themselves pack well. Okay. Suppose I start with 40 mm size and I'm given zone 2 sand, then I know 0.71 would be the volume fraction of coarse, which means 0.29 is the expected fine that would give me high packing, right? Now, why is it given in a table form? Remember, this fellow here, the fine aggregate, is not in my control. I get some size distribution. So what am I trying to do? I pack my coarse aggregate, then bring in the concept of hierarchical packing, pack the gaps between the coarse aggregate with the smaller sized fine aggregate, and I've come up with this table here. Okay, but this table is empirical. Nobody can derive this table from you. The lessons to take here are coming from what we learned from the spherical packing models. But this is built into our code, where basically the whole idea is that you want to pack as much solid in the form of aggregate as possible in your concrete. Okay. Now, this is typically how it plays out. That is, if I actually look at the maximum aggregate size, you look at the percentage, this is the total volume. You see that I can actually increase my aggregate content in the concrete, decrease the paste content, starting with a larger aggregate size. Now, you may be wondering, where the heck do you even see something like a 150 millimeter aggregate, 225 millimeter aggregates in dams? Okay, even in highways, it's not unusual to see a 45 millimeter or even 75 millimeter aggregate being used. Okay, so what am I gaining with a larger sized aggregate? Larger volume of aggregate, smaller volume of paste. Then why is it that we don't use this in our normal construction? Most normal construction is done with this fellow here, which is 20 millimeters. Why? Sorry? Because we have to fill a form. Most of our structural members are slender, or they're basically thin. And if I consider a 200 millimeter thick web or a beam and try to force fit at 150 millimeter aggregate, it's just not going to go there, right? So I have to pack it. That's the reason why we are sliding down this here because we are making our members smaller, thinner. So what happens then? We are going down this path, and as a consequence, what's happening? Okay. Now, think about what we are doing in printing. Typical nozzle size is 50 millimeters. So what? You think this will work? Even that is too big. So what happens? Now I start coming down here. Then what happens? The paste content goes through the roof. And that is reality. What we're using as concrete and printing has a very high paste content. Okay. Right. Now, last few slides. So let's look at what happens when concrete is at rest. Let's try to understand what a slump and that third lever that we haven't pressed so far, which is aggregate. We've understood packing. We've understood strength. So I'm going to adjust the water to cement ratio for my strength. Packing for economy, right? So that I use minimal cement paste, and we follow a certain packing procedures that come from packing, right? The other thing now is concrete at rest. Where is it at rest? How do we measure it? When I measure a slump, it's at rest, right? So, so if I look at concrete now, going back to my basic definition where I said these are aggregate, this is cement paste. What happens in reality is when you mix the concrete, the aggregate get coated with this paste layer. There's a thin layer of paste that forms around the aggregate, right? When you whip this aggregate in mixing action, what happens? The aggregate are churned along with the paste. So all the aggregate get coated with a layer of paste, just about a fraction of a millimeter to a millimeter thick. Now, this paste layer will always be present on the aggregate. So why is that important? Well, my paste demand increases with surface area. So if I now give you concrete which has a smaller, largest size, what will happen? The surface area would go up, which means my paste demand would go up, right? So if I'm trying to balance packing and the paste demand for whatever reason, then I have to expect this. Now, where is the paste demand important? So when we look at concrete at rest, so we know the slump test. Follow the sequence. We fill the cone, we pull the cone out, it comes to rest in this position. Suppose I was to take a snapshot of this here. This is what it would look like. Going back to my fundamental definition again, these are my aggregate. Now these aggregate are coated, right? This is that film of paste that's formed around the aggregate. They're sitting in a paste medium. This gap, it's not like there's air there. This light gray here is the paste, right? Now, if I now look at these aggregate, it looks as if these aggregates are precariously perched, right? Something is holding them there, otherwise they'd simply slide out, right? Now, if you look at this, what's happening? You have essentially this paste layer that's between the aggregate, right? Now, if you look at the stress state on this paste layer, what would you see? You would see actually that the paste is subjected to a shear stress, right? Now, what would happen if this paste had a high yield stress versus the paste has a low yield stress? What do you think would happen? If this paste has a high yield stress, it will be able to withstand a higher shear stress, right? Which means it's going to hold this aggregate in position and allow you to create a larger height in the slump. What happens if this yield stress is low? It will simply shear off. So what will happen? This configuration will not be possible because internally the fluid, the paste cannot sustain that level of shear. It's going to give way, it's going to slip, it's going to shear off. And what will happen then? The concrete will settle even more and you'll get a higher slump. So what ultimately determines the slump of concrete? In addition to all the other factors that we have, yield stress of the paste. Okay, remember, because this is again a static condition, it's not a fluid condition, it's not a flow condition, right? So now coming to fluidity, how do we control the fluidity? Remember that these aggregate are coated with a layer of paste, right? And it is the paste content that controls the fluidity. Now, the way that the code controls this is by regulating the water content in the concrete. Okay, there's a table that's given here, and this table is based on what we call the paste demand. Paste demand for what? Paste demand to coat all the aggregates, right? There's a certain minimum amount of paste that's required. If I go below that, I will not have enough paste. Now, the way the code regulates it is by the water content. They stipulate water content which varies with the aggregate size. And you notice what happens here. When you go from 10 mm to 40 mm aggregate, the water content requirement actually decreases. Why? Surface area. Okay, so the effect of surface area is built into this table 4 of the code. Okay, intuitively we should know that this comes from packing the theories that we learned from spheres. Okay, although we are dealing with irregular shaped aggregate, and there's an elaborate explanation of that, which says that basically water content is influenced by a number of factors. They always try to hide behind a lot of factors, but most important factor is the paste content. And what controls the paste content? Because you're already stiffening up requirements on cement and other things. So basically they're regulating the water requirement here, and basically an increase in the aggregate size will reduce the water demand. Water demand for what? Flow. To induce a certain flow behavior of concrete. Why? That is controlled by the paste content. Okay. Now comes my last lever that I want to press, which is I've done everything. Now I want to control my water demand. That is, I want to make concrete flow with less water because I have other constraints, right? If I try, there's already a limitation put on the cement content. I want to achieve a certain strength, which means I have to use a certain water to cement ratio, right? Even if I maximize my cement paste content in there, the paste itself has a very high yield stress. So what will happen then? If the paste itself has a very high yield stress, this is what I end up with. It's not going to slump, right? So when I lift the slump cone, basically it sits in the original shape. How is it able to keep the shape? Between the aggregate, the paste has such a high yield stress that it doesn't shear off. It's going to hold on to that to the aggregates in the position. So you end up with a nice stiff concrete. How do I get this thing to flow? I've already pressed all my levers. Here come the admixtures, right? So I can basically use an admixture, right, to reduce the water demand, right? So I can basically maintain the same slump, okay, with a lower water content, or increase the slump, right? Basically, what am I doing? I'm artificially playing around with the demand of water for a specific requirement, which is flow requirement, right? If I take regular cement paste, suppose this is the yield stress of the cement paste, what would happen if I added a specific admixture, which is a superplasticizer or a high range water reducer? What does a high range water reducer do? What does a superplasticizer do? It reduces the yield stress of paste. It doesn't affect the viscosity, it reduces the yield stress. So what would happen? Remember this curve here? Yield stress of the paste would drop if I added some admixture to it. And my concrete would basically start flowing. I've not increased the water content. I've added an admixture. Small quantity that changes the flow behavior of paste. Suddenly now, my static condition, this is favored, right? If with this yield stress I was to achieve this, this will not happen. Why? Because in this configuration, the shear stress between the aggregate, the paste cannot sustain it. It will just simply shear off. Now, another condition of rest, which is what happens when we vibrate it. So we're dealing with concrete that looks like this. The minute we apply vibration, look what's happened. It just flows like a fluid. So what changes there then? Again, it was at rest. If you look at it, I just agitated it. So what happened when I agitated it? Well, let's see what we get with. So I'll just play this video again just once. Right, so this is concrete and then it's being agitated. Suddenly you find that it becomes fluid, it flows and it fills the form, which was our basic definition of workability, right? So why would that change? Going back to my static condition here, this is an aggregate covered with the paste layer. Now, what happens when I agitate it? The aggregate will have relative motion. All the aggregate will try to move relative to each other. Each one of them is moving. What is happening in the process now when I've agitated? This paste layer between the aggregate is getting sheared, it's getting agitated, right? It's getting sheared, okay, in a dynamic condition. So what kind of condition am I creating in the paste layer here? It's like a dynamic condition, right? Now, going back to the basic rheology of cement paste, what did we expect from cement paste? It had a yield stress, right? That was when it was at rest. That's what gave me this shape here, right? That was this fellow. The minute I agitate it, what happens? Now I'm introducing a gamma dot. I'm trying to basically produce a dynamic state. So what happens? This is shear thinning liquid, right? It starts loosening up. And that basically starts producing this relative movement. It flows really easily, fills the whole form. Okay, so this is the role of vibration. Okay, and in some sense, if you really understand this, cement paste is our friend, because the yield stress is what gives me this, allows it to keep that shape in a static condition. It is the once it starts to flow, the more I agitate it, the easier it gets to flow, right? And that property I use when I'm trying to vibrate it until my form, right? The last thing I want to talk about is pumping. What happens when you're pumping aggregate, when you're pumping concrete? So when I pump concrete, all these aggregates are making a mad dash. They're rushing through. They're being pressurized from here. And I'm applying the pressure on the aggregate. I'm not on the concrete. I'm not applying it on aggregate itself. So I'm trying to force this entire concrete through a pipe. What happens there then? The aggregate, basically, each person for himself. What is happening? The aggregate are trying to move whichever way is conducive for itself. What forces the flow of the aggregate? What are the stresses? And the aggregate tries to minimize the stresses on itself. That's what it's trying to do. In doing so, suppose this is the flow of concrete and the aggregate are all moving relative to each other. Okay. Now, the aggregates are all coated with this layer of paste on them, right? And as I'm pushing this, what's happening? The paste is also trying to move through these gaps between the aggregate. How can I get this whole thing to flow properly? Well, I have to facilitate movements of this aggregate, which means the rheology of the paste becomes important. And I have to allow some extra paste so that that paste can also move quickly. It's like a lubricating layer between this aggregate, which also will basically flow through the between the aggregate and facilitate the movement of the aggregate. Remember, the aggregate flow is in this way. What do I mean by saying aggregate flow? If you look at the aggregate as a bunch, as a whole, there's a total movement in this direction here, right? And individually, the aggregates are also moving relative to each other, right? And there is also movement of paste here. How can I make this job easier? Well, I can make this job easier, and this is actually codified, which says that if you actually have concrete that is to be pumped, increase your paste content by 5 to 10%, or decrease the coarse aggregate content by 5 to 10%. Why? So you increase the paste content that allows for this movement of the paste between the aggregate. Okay. So basically, this is the fundamentals of concrete mix design. We play with our aggregate, content, packing, paste content, composition of the paste, how much water to cement ratio. When all else is done, bring in some admixture to control the final outcome, right? And fundamentally, it is the rheology of the paste that determines the rheology of the concrete. In what sense? If the yield stresses of the paste is high, we expect a high slump from concrete, which means it is able to hold level differences much easier. It starts behaving like a solid. Higher the slump, what happens? That means it's going to flow more, right? That is our understanding, right? Um, and we have to have enough paste to coat all the aggregate. And that's a game that is played by the surface area. Okay. All of these things are built into our codes, although in empirical forms, because exact mathematical definitions cannot be developed for something that is not spherical. Okay. So final, when all is said and done, this is typically what we end up with in concrete. We have coarse aggregate, pack the gaps between this with fine aggregate. Then we have cementitious material that go and pack the gaps between these two. The whole objective is to minimize this content here, to bring down the cost and maximize these fellows in order to achieve better economy. Okay, so I think that is my last slide. I went probably 5 minutes over, but probably open the floor for questions. Any questions at this point of time? Yes, no, maybe. Early in the morning. Sorry? Slump and yield stress relationship. Okay, fine. So you understand what is the yield stress of paste, right? At some level, we say, well, it is that initial resistance to flow. Unless you overcome the yield stress of the paste, it's not going to flow, right? So now what I have is, suppose I go back to my this here, right? So this is, now I'm looking at the concrete scale. Now at the concrete scale, I'm looking at aggregate, which is coarse and fine, with paste in between. And when I fill the slump cone and I pick up the cone, what happens? It comes to rest in this position, right? Now, suppose I take this fellow here, some part of this, and zoom into this. What do I see? I'll see an arrangement of aggregates. These are in a static condition. Somehow they are holding their position. And I have paste filling the gaps, right? And it's not like this deeper color here is a different paste, and this is the same paste. It's just that I've demarcated that coated aggregate with that deeper color. Now, if you look at, let's say, one of these aggregates and you pull it out and look at the what is happening on the aggregate, right? That aggregate is in a static condition, right? There'll be forces that will be pushing it out of position, right? But somehow it's able to hold on to that, right? Then if you look at, let's say, two aggregate contact, what's happening here? We have the liquid here, which is the paste, right? And that would be subjected to a normal stress, some normal stress, because the aggregate will be in contact, right? And there'll also be some shear stress that would develop there. Okay. Now, what prevents this aggregate from sliding in this position? It's if this fluid here is able to withstand a higher yield stress, it's going to block that in place. It will not allow it to shear. Okay. If that liquid had a low yield stress, what will happen? The minute I apply some shear stress to it, it will shear, it will flow. It will not allow the aggregate to be in this position because it cannot withstand that much shear. Okay, so what happens? Then the aggregate will move, continue to move, right? And they'll find a more favorable position, which is not possible with that. So then it basically, the slump then increases. Okay, so if I increase the yield stress of the paste, I expect a smaller slump value. It will not slump as much. Then I should be able to keep higher level differences in concrete. It starts behaving more like a solid. Why? Because what it takes to induce flow in cement paste, that stress is very high. Okay. Admixtures will not reduce the viscosity of the paste. Only one. Super plasticizer, as we call it, or high range water reducer, is designed to reduce the yield stress, not the viscosity. Okay. And there's a lot of confusion here, but high range water reducers are intended to reduce the yield stress of the paste. Okay. If they happen to reduce the viscosity, and they don't reduce the viscosity, but if they happen to change the viscosity, it's an unintended consequence. That's not what they're designed for. They are not similar, right? Viscosity is after flow starts. Yield stress is while it is static. Okay. So what is yield stress? Suppose I take a fluid, apply some shear stress, low value of shear stress. It will be able to sustain that shear. It will not flow. It will basically remain static. Okay. What is your viscosity? Once I overcome that initial resistance, once it starts to flow, the resistance to flow is viscosity. Okay. Two very different things. Right. Any other questions? Yeah. Efficiency with spheres, you can play these games. I think numbers are there. Like there are enough mathematical theories where you can maximize it. Okay. But when you deal with irregular sized particles, sky is the limit. And when I talk to people who work in packing theory, and I said, look, we are able to hit 80% packing and get only 20%, even with normal concretes, they're shocked. Because achieving that with spheres is very difficult. Spheres are notoriously difficult to pack. When you start dealing with irregular shaped aggregate, sometimes you get much higher packing efficiency than you would get with perfect spheres. Okay, so when you're dealing with irregular objects, yes, that we mostly rely on empirical packing rules, right? There are certain theories, but then we use them as a guide. Some level of trials have to be done to basically match, because exactly spherical theories would lead us in a certain direction, which are pointers. And then when we're dealing with actual powders and actual particles, which are not exactly spherical, we'll have to do some trials and exactly try to fit it to that. It will not be exact match with this. Well, you're getting into UHPC domain. So I'll park that question here. It's not directly relevant to what we're doing. Yes, it is an issue. And UHPC has been shown to be to fail in a lot more catastrophic manner under fire. So yes, that is a concern. But I wouldn't blame the packaging for that. Okay, it's just that particular brand of concrete UHPC, which is packed to such an extent, and you have very high cementitious contents, and all these factors combine to give you that kind of a response, specifically in UHPC, not in all other good, well-packed concretes. Okay, right. Any other questions? Absolutely, absolutely. That's where, if you read IS 10262, it says, please do your trials. They only give you guidelines. They'll say, look, that all the tables, charts, they'll say, look, this is rule of thumb, a guideline, but you do your own trials. Okay. And that's because the code is, or they're smart enough to realize that aggregate from quarry to quarry, they'll vary in surface area and particles, shape, sizes, everything. So yes, developing exact science for that is not possible. We cannot develop an exact mathematical relationship. This is just a heuristic or a simplistic understanding of this. This is what I expect, I should say. If I decrease the yield stress of the paste, I'll expect it to flow better. I'll expect it to come to rest in a static position, which has lower shear stresses in the fluid. It's as simple as that. Okay. All right. I think, yeah. Correct, yeah. No, remember the three boxes that we had, right? The very first one was strength and durability. That was for hardened concrete. That is never to be compromised. This is the flow behavior. Okay, so whatever I do here should not affect that. And remember, how do I grade my concrete? It's in some M gradation, isn't it? M30, M35. That is strength. 28-day strength, hardened strength. This is the games that I play when it is fluid, when it is plastic, and all that. Right? All three boxes have to be ticked. Okay, and I have only so many levers in my hand. I can control the water content, I can control the cement content, the aggregate content, and the breakup between coarse and fine. Right? And then if all else fails, I bring in some admixture to help me a little bit. Okay, but yes, you cannot compromise on that strength or durability. Those are the hardened properties. Okay. All right. So I think if there are no more questions, I'll stop here. I think I've done enough damage already. And probably, what is the next thing on the thing? Do we? Okay. So we'll ask Professor Narayanan.
We'll continue the same vein of thought of particle packing with respect to mixture proportioning. Now, what I'm going to do is kind of walk a very tight rope. Okay. So yesterday we did a lot of rheology, introduction to rheology. You kind of understand what is yield stress, what is viscosity, um, what causes a fluid to flow, what keeps it flowing. Remember all of those ideas, right? Starting to flow keeps it flowing. And then now we introduced in the morning, how does particles come in, and when you have aggregates and cement paste coating the aggregates, do all of that. Now we'll have to tie all of this together in some fashion to see how we can create a mix that is printable, right? So now, if I don't know any of this, if I have no idea about particle packing, if I have no idea about rheology, can I still print? What do you think? I completely refuse to come to this class. I don't care. It's so boring to sit inside and listen to all these people. I don't want this. I just want printing. Can you print? You can print without any control. But can you gain control after printing a lot? You perhaps can. But then that will be shooting randomly, hoping that your bullet will hit the target once in a while, right? You will still win. Can still show your win. Look, I knew nothing about it. See what I printed. You might be able to do it, but that'll be once in a blue moon, only when all the stars align and not when your client and the customer wants. Correct? That's not what we want. So we want to kind of bring this understanding together so that again, even after that, like IS code says, like every code says, you have to do your trials and make sure that whatever adjustments you have to make, you will have to make. So I'm going to start putting in some theory behind all of these different disparate things. It's going to be a little wilder ride, so prepare for that at least until lunch. We're going to do multiple things. Okay, so going back to printing, if you have forgotten what that is from yesterday, you will have a pump that pumps the concrete that goes into the printer, and then you um, print it in whatever shape that you want, or you have a mixer and then you can directly put it to the printer. You can pump it whichever you want for using any of those materials. So this is your basic process that we start off again, and you can do all these different shapes. You can do structural and just refreshing what we did yesterday and today morning. So this is what we have in our plan of action. What do we need now? When you have a mixture that you need to print, and if you are printing through a nozzle, and if you're continuously printing a large amount of material, you need to pump your concrete through a pump to the nozzle, correct? You have to get to the nozzle. So your mix has to be pumpable. When the mix comes to the nozzle, it has to be extrudable through the nozzle, right? And once it is extruded, you have to be able to build it up, correct? In none of the, in your regular concrete, well, was it pumpable? Yeah, it's kind of pumpable. What do I do? It's not really pumpable the way I want. I add a little bit of admixture, add a little bit of water. That's fine. I make it pumpable. I got it. It's not really flowing. What do? I get my vibrator, vibrate the whole thing. I just want to fill the form. You have multiple levers that you can play. Your tolerances, your room for error is much higher. Right now, you have zero room for error. You are playing this very coordinated dance sequence where you see all these dance sequences where all the dancers do it in, otherwise it look very ugly, correct? Same thing. The first dancer, the pumpability dancer, will have to coordinate with the extrudability dancer and the buildability dancer to get what you want to effectively get. And this has to be coordinated. Easy? Great. It's great and easy if you're doing it in a computer and modeling this. Okay, if you actually start to do this, it starts to get more and more complicated, and that's where we need to have an understanding. Now, is an understanding guaranteed that you will get it? So I want to give you an example. So this is a social science research that they have done. Basically, what they did is to see how much of understanding versus practice balance is achievable. So what they did is they put 50 people in a room, right? From morning to evening, showed them videos where people are throwing darts. Right? You've seen throwing darts, right? In those circular things, and you have to throw in the bullseye. So the whole day they watched people throwing darts. By the evening, they gave them a questionnaire. And everybody said, no problem, we understand this, we can throw darts. Right? Because you've seen it the whole day. You think, okay, I understand it. I see the technique. I see them, how they put their hands, keep their hands, focus, concentration, watch it. I can do it. The next day, they take them to actually throw darts. Right? What percentage do you think even hit that outer circle? Less than 10%. So, have they understood it? Absolutely. Are you able to do it? The other example is I learned swimming through YouTube. Correct? Of course, yes, I know the technique well. Butterfly swimming, what does it mean? Jump at a certain angle, go into the water. That absolutely. You throw them in a river with YouTube. That's it. Right? You'll have 5 more people have to go and bring them out in a immobile fashion. So the understanding that you get, you might know all of this. Will you be able to do it? That's the thing. That's in concrete technology, knowing is great. Being able to do it is a different thing, and that's why you will see a lot of people who know nothing about particle packing. I have seen actually people who can discern, who will see the aggregate, who will just walk into the ready mix plant, see the aggregate bins, walk around the aggregate bins, and tell the aggregate proportions. I've seen people who do that. Just looking at no sieve analysis, nothing, but they are not spring chicken like you. They are not 20 years old. They are 60, 70-year old. Why? They have done this for 40 years, and at 40 years, they can do it. Right? What we are trying to do is shorten that span, get you to be able to do that in 10 or 15 years rather than 40 years, right? So that's where this whole thing comes in. So keep the right perspective. This is not going to make you solve all these problems tomorrow, but you will get an understanding. And once you do enough of it, you can accelerate the process of achieving the right results. This is not, you know, you're not going to solve all this tomorrow. 3 concrete mix designs doesn't make you a concrete rocket scientist. It'll take time. All right. So that's where we are going to go in. Printable mixes, we talked about that. You need to be able to print them up and build it. I talked about mortars plus aggregates, pre-placed aggregate concrete concept where you can build up things like this. You can do all these shapes. You can build up things in whatever fashion you want, depending on what materials you have. So here are a few things that we are trying to connect everything. So this slide, pay close attention. From whatever Dr. KVL has told this morning, plus what we heard yesterday, a lot of things are going to come here in one slide, and we will go in different directions in this slide as we go through. Okay, so what we want is we want things to be built up. Eventually, this is your aim, right? If I want a 1-meter column, I need to be able to build up a 1-meter column. This is your aim. In this, here is your extrusion process. Assuming that you have a pumpable mix, you have done all of that. You have an extrusion process. You want a certain viscosity. You know what the shear rate is. Shear rate comes from pumping, correct? And then the extrusion at the tip of the nozzle. You know what that value are. Hope that you have made a good estimate of that from your laboratory experiments. Does it make sense? Is that idea clear to all of you? Okay. Once having done that, what do I want to get it build up in time? With time, I want the stiffness to increase, not the strength. Of course, as stiffness increases, strength increases. But we don't want to be characterizing strength because at early ages, you can't calculate a strength. Right? You really cannot calculate a strength. Whatever, I mean, people will say, oh, this is a green strength. Yeah, for lack of anything else, and strength is what we love so much. Yes, it's okay. But what we actually want is a stiffness, because remember, in materials, if you're talking about solid mechanics, there are only two fundamental material properties. They are stiffness and Poisson's ratio, right? One is how stiff you get, which means what is the deformation for a certain stress in the direction of application of stress. And Poisson's ratio will tell you what is the elongation in the direction perpendicular to the application of stress. Those are just 2 points. And if you actually look at it, both of them are deformation criteria. They're not stress criteria at all. They're deformation criteria, right? And with 3D printing, what we want is to control deformations, which means it makes common sense to go through the deformation criteria. Does it make sense? Okay, so you want the modulus to go up with time. Now, I can have the modulus gradually increase with time like that. Is it enough for me? I want it to be quickly increasing with time. So, here is a concept that we are connecting from everything that we have heard so far. If I want modulus to be quickly increasing with time, what is the best way to do it? Okay, if you are talking about cement hydration, I can make the modulus go up as the cement gets more and more hydrated. Does it make sense? I increase the hydration of cement, which means I have one particle of cement, infinite amount of water around it. As this particle of cement hydrates, my stiffness will increase, correct? But then that's a slow process. So what I want is already set the system up in a way that can get a quick modulus. What is it? How can it be? So I have one particle here, one particle here. The combined modulus should increase faster. What do? The glue should happen faster. Make sense? Which means I need to make sure that the particles are packed well enough so that the cement paste around it quickly hydrates and creates network so that the combined modulus of the system goes up higher. Is it clear? You see the importance of particle packing? The particles have to be packed well. So that is what you want to get the modulus higher. And then once you get the modulus, of course, you have shear stresses that are happening. You want it to be built up in a way so that you don't have off-axis stresses building up and causing buckling failures, off-axis failures like that. So that's what you want. Now, if you look at a mix, so in this is yield stress, that is plastic viscosity. I'm just using these two parameters because yesterday we learned to measure these two. Yes. Stiffness, elastic modulus. Okay. The reason I did not say any other modulus is if you're measuring a shear stress, I can't tell you that's not important. Then it becomes shear modulus. If it's shear strain, shear modulus. But if I'm building it up, I'm thinking about axial stresses and axial strains. Now, you can always ask, is shear not important? Or won't I do off-axis failure? Yes. If that's the case, shear modulus. But if you know elastic modulus, can't you calculate shear modulus if you know Poisson's ratio? Straightforward, they are linear relations, right? So that's a straightforward relationship. And that's why I said modulus. If it is axial strain, elastic modulus. If it is shear strain, shear modulus. All right. So these are the two terms that we learned yesterday, correct? These are the two, yield stress and plastic viscosity. Now, I put in a big band of where I can live. So if I have an extremely high yield stress with a very low viscosity, I know I can't print it, I can't extrude it, right? So forget it. If I have an extremely high viscosity with a low yield stress, yeah, I can really pump it, but I can't build it up, which means those are out of the picture. I kind of come up with a band like this. Now, within this band, what do I want? If I have a low yield stress with whatever plastic viscosity that I can consider, low yield stress, which means a highly flowable fluid, correct? Yield stress is that stress that is required to initiate flow. Lower that value, faster it will flow. Correct? Right? Which means that's where it is. Okay. Can I build that up then? It'll flow faster. Can I keep building up layers? Probably not. Minimal buildability at that state. Now, if I increase the yield stress a little bit more, I can start to make it much more buildable. I now want to introduce to you one more concept, which we have not really covered, but I'm sure you are able to extrapolate from what we have learned. If yield stress is that stress which is required to initiate flow, that's what we also saw that, right? Because you have that yield stress and then beyond that the flow starts. If yield stress is that which is required to initiate flow, we also talked about the idea that that is what is required to break that network. Break the network of particles so that it will start to flow. So, which breaking the network meaning what? Removing the contacts between particles, because it is a particle contacts that create shear stresses. This movement between particles is restricted by those contacts, correct? So if I start to break the contacts, if I start to move particle contacts away, which means automatically lowering the yield stress. Everybody good with that? So I want to get to a point where I want to break that particles with the bond between particles. So I want to get to a point where the mix is not too stiff, yield stress is not very high. The mix is not too wet, viscosity is not very high. I want to be in a zone where there is enough yield stress and there is enough viscosity. There is enough yield stress to initiate flow. There is enough viscosity to keep flowing. Correct? So that is your impossible condition that we have to satisfy. Not impossible, we can. So that's the intermediate buildability condition. Now, if I have an intermediate buildability, yes, I have my yield stress and plastic viscosity controlled in such a way that I can start building it up. But then once it gets to a certain height, the yield stress is not high enough to hold the layers that are below. Right? There is not enough stiffness to hold the layers below. Intermediate buildability. What I want then? I want it to go higher yield stress. Now, I can increase the yield stress higher and I can increase buildability as much as possible. But what is the downside of increasing yield stress? Hmm? Which you need more force to initiate flow. So yield stress increasing after I build the layer is great, but yield stress higher at the moment of extrusion is not very good. The fact that you can do is you can make the mix in such a way that you can add admixtures, delay the open time, do all of that. But all of those gets very complicated, as you can see from this picture. And this tells you only half the story. Yield stress is not the only thing. You have other parameters also, which we will talk about. And then as you get to a higher place, this blue zone is actually a good zone. A certain yield stress with a certain viscosity will get you good enough buildability with delayed collapse, good enough buildability and extrudability. But you further increase the yield stress, your material will get stuck in the nozzle. So this picture, try to keep it in your mind. Now, what does materials do in this whole thing? No, if you have a certain yield stress and plastic viscosity, you add superplasticizer. Dr. Subbu said this earlier. Superplasticizer is supposed to lower the yield stress and not the viscosity. You see that in that picture there? You're lowering the yield stress. You're not supposed to. Superplasticizers are not supposed to do anything to the viscosity, because superplasticizers by nature does nothing but to separate the cement grains farther apart. They do nothing but deflocculate the cement grains. They do not add extra water to the system. They cannot bring in more viscosity in any form or fashion. If you have to change the viscosity, you have to add a viscosity modifying admixture that changes the viscosity of the solution, that changes water to honey. or honey to oil or whatever, right? Otherwise, superplasticizer simply spreads the cement paste farther apart, giving you an illusion that this is actually flowing better. By spreading these particles farther apart, what are they doing? These two cement paste particles are sitting like this. Superplasticizers, because of this phenomena called steric hindrance, some of you would have heard in your classes, steric hindrance simply breaks this apart. They just go away, which means the contacts are broken. When the contacts are broken, yield stress comes down because you've broken the network. That's all what you have done. Silica fume. Now you add silica fume, what happens? Why am I doing this? When you add silica fume, what happens? For a certain dosage, you might see viscosity dropping a little bit, right? You will see the flow becoming easier because silica fume particles accelerate the flow at very low dose, 1%, 2%. But when you get to 3, 4, 5%, they do the opposite effect. They start to collect all these particles together, start to clump. You will need more admixture. So depending on what you want with yield stress, you can play around with silica fume. Water, of course, you don't want to do this, but that's what water will do. You don't want to add extra water for all the reasons that you know. And of course, aggregates, depending on what you have, does all of this. So what is printability? Printability is buildability plus or extrudability plus buildability. You should be able to extrude through the nozzle and build up layer by layer. What do we need for that? Everything that we have talked about earlier, right? You need the paste to have the ideal yield stress and plastic viscosity. You need the aggregates, if you are having aggregates, to be able to be spaced and particles to be packed in such a fashion that you give stiffness to the system, and then you should be able to print it, and then you should be able to build it up well. We talked about coating thickness when we talked about paste thickness. You can find the coating thickness based on simple fluid mechanics equations that uses viscosity, density, the particle sizes, the velocity of flow, all of that. You can find the ideal coating thickness for different applications. We'll work on that a little later. Now, you have pretty much, to get a good yield stress and plastic viscosity that you want to flow, you want a certain amount of paste coating the aggregates, right? And that's what you heard in the morning. Your codes will do all of that empirically. By specifying the minimum cement content for workability and a minimum or maximum water cement ratio, they are simply specifying a certain paste volume. And depending on your aggregate sizes, you can find out based on surface area what is the thickness of the paste. So what you're doing is a paste thickness, and here is a relationship between yield stress and the excess paste volume. As the excess paste volume increases, as you increase the dynamic yield stress of the paste, that is an indication that you have excess paste volume. So again, mixed design will also have to account for the fact that how much of paste volume you have in excess than what you want to coat the surface of aggregates. Because any excess paste is wasted opportunity, is wasted resources, is wasted money. So if you want to mix optimization, that's what you do. Okay, we talked about conflicting demands about stiffness and flowability. Again, stiffness or modulus. You want the modulus to be higher and higher and developing fast so that you can build up your layers and you can build the stuff faster. One of the biggest advantages of 3D printing, if you look at people who are touting this technology, will say that, oh, you can do very fast construction, correct? If you want fast construction, you better build things up fast. And if you want to have better buildability, you want the material to develop its stiffness faster. Not stiffness while it is sitting in the mix and the nozzle, but stiffness after it has come out of the extruder. So that's what you want. But in the extruder, you want better flowability so that you can get a cohesive mix that's coming out. So, this one that you see here is good. This one, very good. So this is very nice and pumpable. But what happens with buildability? Nothing. It's extrudable. It beautifully, nicely extrudes. You'll be very happy to extrude it. But then if somebody wants, can you extrude the shape? You will say, you know what, whatever shape comes out is the shape that you should buy. That's not probably going to work. This is fairly good. You can do whatever you want. This one, lots of people are putting in lots of effort and struggling to get it out in some fashion. Finally, if you give the product something like this, of course, you've lost your money. And this one, of course, it is not even extruding, right? It extrudes whenever the extruder thinks it wants to extrude. You're not getting a continuous extrusion. So you have the whole variety of this. And if this is what you want, this is probably that conflicting stiffness and flowability demand that you want to satisfy. Okay. So how does rheology and packing build into all of this? Now, in the evening session on today, we'll do a demonstration and you will be able to play around with a few things. We'll do packing. Again, the software is not as complete as I would have wanted it to be, but it is in a shape where you can actually pack particles. You can visualize the pack of particles. Avinay is going to give you a bunch of data sheets with different size distributions that you can play around and see how it packs. And then there are calculations that I'll show, which eventually these people, they have promised me that they'll get this app working and running soon. And we will send it to you because all your emails are there. We'll send it to you so that you can download it and play around and know all the particle packing characteristics. You can do all of that. So eventually, we hope we'll get you there. So you have all these mixes and all these materials have different size distributions, right? Cement and fly ash and limestone all have different particle size distributions. You can have then different workability based on this. They'll have all different packing you can do. So you can optimize the proportions for maximum packing, optimize the proportions for the flowability and the extrudability that you want. And then these two requirements you can match in some fashion. And, we haven't really done it specifically for 3D printed mixes, but we have done it for UHPCs in a complete fashion and published to get rheology and packing based complete mixture design criteria, because UHPC's mixture design is more of a straightforward way of doing it compared to 3D printing, but the same principles will apply. Now, binder type. So if you want to start with packing, you talk about binders. What type of binders, right? So it'll be a good time to talk about binders that you will use. Most of the time, your 3D printed concrete will have a high binder content, correct? You are talking about 800 to 1,000 kilograms per meter cube of cement. Extremely high value. You don't really have to do that. You can drop it by 50% straight away. You can get to about 50% replacement of cement with some other materials if you know the way to control particle packing and rheology, right? So a few things that'll be handy. And let's do some thought exercises here. I give you a bunch of different cement replacement. Let's assume that you have all the cement replacement materials that you commonly have, okay? And if I tell you, you can't change the water content in your mix, but I want the yield stress to be dropped. I want a lower yield stress. Your water content has to be the same. I want a lower yield stress. I'm giving you cement, fly ash, silica fume, slag. What material will you use?
Flash.
Why?
But it's like flash is more of a
Assuming that particle sizes are in the general range of cement, they're not extremely fine, not extremely coarse. Why fly ash? What will the shape do? Spherical shape, what will it do? Let's talk in terms of what we have been hearing yesterday and today. In terms of, so what is yield stress? It is a stress that is required to be overcome to initiate the flow. What will fly ash do? What will a spherical particle do to initiate flow? It will reduce the friction between particles. The smoother particles, the ball bearing effect will start to make it flow, roll better. The resistance to flow is lowered. Fly ash will do a good job. So, given a certain yield stress that you have to achieve to get there, by replacing cement, fly ash is a good option. Correct? Now, what if I want to increase the yield stress? I accidentally added quite an extra amount of fly ash. Now, I want to increase the yield stress. What particle will you add now to increase the yield stress? Slag, maybe. Why slag? Very angular particles, right? So it might be beneficial, but its angularity is very comparable to cement. So it's not going to really do too much different from what cement does. What's your next option? I can add aggregates. Yes, if I want, I might add some sand. I might add some angular coarser particles, right? So I might make it into a mortar to get your slightly higher yield stress. Okay. Now, if I want to control viscosity, what are my options? Does any of these particles change the viscosity? No. Right? Does admixtures change viscosity? Yes. Which admixture will change it? A viscosity modifying admixture will change the viscosity. So if I have to really change the viscosity, and that's why a lot of 3D printed mixers, you will see people using viscosity modifying admixtures because they have to control the viscosity in some fashion, right? Yield stress, you can play around with particles nicely. Viscosity, you have to use a viscosity modifying admixture. So now you have all these different options that you can play around. So you reduce the cement content, you can play around with all of these. And with strength, when you replace a certain amount of cement with some other materials, will you lose strength or will you gain strength? Whatever answer you're going to say is going to be right and wrong, correct? Yeah, that's how it is. You will say that fly ash, then you can ask me at what age? How much of fly ash? Are you reducing the water? You can ask all these questions. But generally, if I simply replace cement with fly ash, at 28 days, what will happen? Generally, I will have lower strength. So what do I do to control that? I don't want a lower strength. What do I do? Water to cement ratio, but we have to look at water to cement ratio slightly differently here. Right? Don't say I will reduce the water cement ratio. You can say that I will increase the particle density, right? Because particle density, your yield stress is what you want to maintain to make it extrudable and buildable. What you want are particle contacts. I want now to play around with the different sizes of particles, and that's where limestone powder is suddenly a wonderful additive for 3D printed concrete. You will get, because of its finer particle sizes, the ability to get it in different particle sizes that you want, and the fact that it really doesn't interfere much with cement hydration. It'll stay as a filler, it'll do some fine filler effect. You can start to play around with particles. So really the idea is that using binders. Now I've put in Metacalin also. Really don't try a clay-based material in printing unless you really love clays and you have designed the mix for an LC3 or a clay-like mixer. Otherwise, the cohesiveness of that will make extrudability a really, really difficult task. It's not that's not possible. The water demand also is going to be very high. When the water demand goes very high, you will either have to use lots of admixtures or lots of water. Both are not good. Lots of water not good for strength. Lots of admixture not good for economy of your mix. So again, few things to remember when you look at all those binder types. Now, coarse aggregates incorporation. You can incorporate coarse aggregates. When they say coarse aggregates, it's typically less than 10 millimeters. Right? You're not talking about 1-inch aggregates. No, none of that. Less than 9.5 mm aggregates. And so there's a certain zone in which you have an coarse to fine aggregate ratio that you can print, which is a function of your mix optimization, particle size, and all of that. And you can look at that. Now, if I'm really looking at particles, and this is more of fundamental material science ideas, what are the factors that I have to look when you pack particles? So I'm sure you have seen in one of your basic material science classes particle packing ideas, right? Simple cube, body-centered cube, face-centered cube. All of you have done that, right? A body-centered cube, for example, has a packing factor of 0.68. Face-centered cube has 0.74. Face-centered cube is or a hexagonal closed packing, which is another form similar to face-centered cube. Hexagonal closed packing or face-centered cube both have an atomic packing or a packing ratio of 0.74, which means if I take a box and take same size spheres and I pack them in the form of a hexagonal closed packing or a face-centered cube, I can pack 74% of the volume of the cube with these particles. The remaining 26% will be empty. So if I have only spherical particles, which is what we will do to idealize like you've seen in the morning, if I have only those spherical particles, what do I need to increase my packing fraction? I need to add Smaller particles. If you keep on adding smaller and smaller and smaller particles, you can get to 0.905. That is a theoretical absolute maximum gymnastic particle volume fraction that you can get. 0.905 is what you can get by packing all these particles, different size particles, right? But those are spherical particles. That's what you get. When you pack those particles now, if you have, say, cement, fly ash, silica fume, limestone, different types of particles with different size fractions, right? Then the nearest neighbors are going to be different. Hydration changes when the nearest neighbors are different, right? So when you have a limestone as fine filler, when you have a filler effect that is happening, and when you want these fine fillers to do nucleation, you want them to be distributed as much as possible, closer to cement particles to hydrate and all of that. So you can do a few of these microstructural terms: number density, coordination number, and mean centroidal distance. Number density is the number of particles per unit volume. As the size goes down, number density goes up. Correct? So you can do a certain number density. Coordination number, number of nearest neighbors within a certain distance from a particle, which means if I take a cement particle, how many nearest neighbors do I have? And who are my nearest neighbors? Right? If my cement particle has all the nearest neighbors on reactive particles, then my cement has to work hard in that area to do it, right? So how do we distribute those particles? And then mean centroidal distance is distance from the surface of a particle to the surface of its nearest particle. Again, these are all mostly for control, hydration control, but we can use it for packing aspects as well. So here is plain OPCs. I want you to look at this carefully. This is just the particle size distribution of plain cement. So all the different particles. I throw in a few more limestone into cement, right? 70% cement, 30% limestone. All these blue particles are limestone, and limestone has smaller size distribution than cement. What happens to packing density of this system compared to this? Definitely going to be higher. Here is a system with 70% cement, 15% silica fume, and 15% limestone. Silica fume is even finer than limestone. What happens to packing density of this system? Even finer, even higher, most closely packed than this, right? And you see here, what have I done? If you simply look at the cement grains, I have spread the cement grains farther apart. I have reduced the amount of cement in the system. Why is it important to reduce the amount of cement in the system? It'll be cheaper, but think about 3D printing. When you're 3D printing a wall with extremely high exposed area with a large amount of cement, what are you going to get? Higher shrinkage cracking, correct? You're going to get one of the most important problems with 3D printing is shrinkage cracking, which we will see later. So to control shrinkage cracking, your best possible option is to control the amount of cement, which means you have to fill it with some other particles, maintaining your extrudability and buildability at the same level. And here is what's packing in a unit volume in 3 dimensions. You will see all of this in the evening, I hope. Okay, now let's get to the aggregate story a little bit. And here is where I want it to be, you to understand. You've seen this in the morning slide also. Here is packing density. Here is a fraction of aggregates. Remember, in the morning presentation, what Shubhu showed, this graph was like this. You saw that? This is, oops. This is packing density. What he was showing was a volume of voids, which is 1 minus packing density. So this graph was like this. And you said there was a minimum value where the voids are minimum. The same thing I'm saying, like a minimum value where more voids are minimum, I'm saying there is a maximum value for packing density. The same thing for a certain combination of aggregates. How do you get that is the whole idea of doing packing. Okay, so here are some packing parameters. We'll come back to that later. You've seen this picture earlier also in the morning, in slightly different form. So when I have all similar size particles with one particle that's trying to go in, it tries to loosen the system, right? So if you try to put in certain amount of sand into aggregates, it's actually initially loosening it before you start to fill that thing back up. So there's something called loosening effect where a smaller particle goes into, again, this is the same thing that happens in crystals when you have defects. It's called substitutional defects. For example, if you make steel from iron and carbon. Iron is a vacancy defect. That steel is, sorry, carbon is a vacancy defect that goes into the crystal structure of iron, changes the crystal structure of iron. So if you remember your steel phase diagram, I'm sure you won't have to remember it, but if you remember it, you will know that steel, pure iron at room temperature, it is a body-centered cubic crystal structure. If you simply heat pure iron to get to 700 degrees Celsius, close to 700 degrees Celsius, BCC changes to an FCC structure. Simply by heating, your crystal structure changes. FCC has a higher packing than BCC. Now you heat even further, the atoms, particles rearrange, reorganize, you get back a BCC structure, right? So lots of these metals do that through temperature changes. And when you add carbon in, carbon is an interstitial impurity in iron. When you add carbon in to create steel, you change the crystal structure in so many different ways. You change the packing of the iron crystals, Fe crystals. So that's very similarly, you have loosening effect. Now, if you have something that is all these small particles lining along close to a large particles, there is a wall effect. You remember interfacial transition zone in your cement hydration story? That's a wall effect basically. Calcium hydroxide sticking along the aggregate particles and forming a zone of higher porosity because you really can't fill things along a boundary well. That's wall effect. You see that with aggregates as well. And then you have wedging effect, right? This guy trying to squeeze in through and create more distances. And as an function of interparticle interaction, loosening effect and wall effect creates reduction in particle density or packing density. This is what happens. Again, these are all simulated values that we have done. Okay. Remember this picture yesterday? How does this relate now? What was this? Viscosity as a function of volume fraction and sizes. So yesterday I told you we are going to get back here when we talk about packing. So here is as a function of sizes. So smaller spheres, you get larger viscosity. Larger spheres, you get larger viscosity. Somewhere in the middle, you have a lower viscosity, faster, easier flow. So it's not just one size that does it, it's a combination of sizes that does it. And again, here we saw that when you increase the shear rate, you kind of take away the particle effect. I'll come back to this later. That is, so I'll do this compressible packing model, very similar to the packing that you have heard in the morning. We are going to throw in a little bit more of mathematics into it. There are several different models for packing. You can have monodisperse, polydisperse, you can have packing that's based on only packing densities, packing that's based on size and density, so many different varieties. But this is one kind of a packing model that is computationally more easier to implement. And that's why I do it, so that when I give you the app finally for particle packing, it'll have this model. So what it does is to take into account what's called a compaction index, which is simply a number, a scalar number, which depends on size distribution of aggregates that facilitate better packing and the effort involved in packing. Right now, you pack particles, it doesn't come free, it comes with expense of energy. If you want to pack something more into a system, you have to give it energy, correct? You have to vibrate it, you have to rod it, you have to compact it, something, correct? Just by taking a bunch of particles and putting in a volume, will it compact well? You have to vibrate it, you have to let it go into the right spaces to fill it, correct? Same thing with the concrete also. You vibrate your concrete to get it a better density. So you need to provide energy. So this K is an indication of both the distribution of particle sizes and the energy that you give. And through experiments, they have come up with lots of those numbers. you can use a value of 9 for extremely well packed particles. 9 is a good number for extremely well packed particles, irrespective of the size of the particles. If you don't want extreme well packing, for example, if you're doing pervious concrete, all of you have heard about pervious concrete? Very loosely packed system. You do a number like 5 or 6. Right? So again, this is not for concrete alone. You can use it for any multi-size particle system. Okay. Now, in that, you have a few terms. Here, you have y sub I represents the individual packing fractions of the aggregate. So, assume that I have number 8, number 4, 3/8, half an inch, all different size of aggregates. I sieve them separately. Assume that I have sieved them separately and put 4 different clusters. Now, typically, what you have in a ready-mix concrete plant are at least 2 different coarse aggregate gradations. Have you guys gone and seen a ready-mix concrete plant? And if this, have you seen their aggregate piles? You have at least 2 aggregate piles, if not more. If you're doing much more controlled concrete mixtures, if you're doing UHPCs, you may have 4 or 5 different bins. Otherwise, you'll have 2 different size bins corresponding to 2 different sizes, and you have a fine aggregate bin as well. So if you use different aggregate sizes, y sub I represents individual packing fraction of the aggregate. What do I mean by that? If I take number 4 aggregates alone, now, when you sieve those aggregates, what does number 4 aggregate mean? All of you have done some sieving of aggregates at some point of time? What does number 4 mean or number 8 mean? Those are the nominal maximum size of the, that's what you say, right? In mixed design, nominal maximum aggregate size. What does a nominal maximum aggregate size mean? A nominal maximum aggregate size of number 4 is everything that is passing the sieve right above but retained on that sieve, correct? So if I have that alone, I will have a size of different size distribution even within that nominal maximum size, correct? So if I take all of that and do a maximum packing. Now, have you done a maximum packing? You probably have done in your soil mechanics class where you tam the soil to get the density of soils. Same idea in concrete also, in aggregates also, you would have done it. You can take the aggregates, put it in a vessel, put it in 3 layers, stamp it 25 times each layer, and find the weight of it, and based on that find out what's the maximum packing that you can do in a certain volume. Have you done that? Guys, kind of get the idea of what I'm trying to say? So you find individual packing density. So if I take a well-rounded, really rounded aggregates, and I've tried to pack a volume, assume that's number 4 aggregates, really, really rounded for argument's sake. Okay, I'm trying to pack into a cylinder, number 4 aggregates. How much can I expect my maximum packing density to be? I gave you the number a little earlier. 0 point? No, this is number 4 alone. 0.74 maximum, right? So if you do the experiment and get the answer as 0.78, you better go back and redo the experiment. You're wrong. It clearly says you're wrong. Unless the aggregate is really angular and has all of that. But generally, you know what kind of upper limit that you're looking for, correct? So you find the maximum. Now, if I go to number 8 and do the same experiment, what's the maximum number I could expect? Same, right? Because number 8, it's only the size that has changed. The shape is still the same size. So you get 0.74 is a maximum that you can get. You typically will get 0.65, 0.66. Generally, if you do aggregates, that's what you get. So y sub I is all of those values. If I'm using 3 different aggregates, y sub I is y1, y2, y3. Good. Beta I is a residual packing density, which is the packing density of a mixture consisting of only the aggregate class I, which is your dry rodded unit weight. You can use a dry order unit weight for that class of aggregates. And virtual packing density, gamma I, is a theoretical packing density when class I is dominant. There are ways in which you can do a theoretical packing density. You can either do it computationally or you can do it through a series of experiments and minimize the results of all the experiments. So this involves quite a few experiments to do. And then you get, you can solve this. So this is gamma I, which is beta I over this big function where Aij and Bij are the loosening effect, wall effect, and the effect of fibers and all of that. You can use based on the aggregate sizes, you can get the loosening effect, the wall effect. So that gives you gamma I. And then you can use an optimization method, a Newton-Raphson method, for example, for those who have done a numerical methods class. You can use that to optimize the value for and find the value of gamma I based on this. And then if you have fibers in it, your fibers will also perturb the volume. Fibers are long. They'll also try to move the materials farther apart. You can account for the perturbation volume. All of it said and done. Here is, so if I'm using, these are the different aggregate sizes, 1, 2, 3, 4 different aggregates, sand, fibers, all of that. So here is your simulated model. Again, I'll eventually give you, I promise, in the next month, the software that will do all of this for you free. So this is what you take the volume fraction of coarse aggregates and you start doing whatever fraction of, so this is about 800 simulations of so many different combinations. Okay, no experiments, simply your software will do it. And then I will do the theoretical pack density. You see, at about 0.6% volume fraction of coarse aggregate, I get my maximum packing density of aggregates. Maximum packing density of aggregates about 0.72 or so, which means I can make a system with 28% paste. You see that? That's your minimum paste content that I want to pack the system. Similarly, for a different size distribution, my maximum volume fraction slightly changes. And then my experimental versus predicted to show that my model is good. So this is your packing density calculation using what's called the compressible packing model. Exactly based on theory of how particles pack. And if I do some examples based on 3 different sizes, a fine, intermediate, and coarse aggregates, increasing packing density from 0.65 to 0.82. What does this point? So among this, do you think which one will have a 0.82? Oops. Fine, intermediate, or coarse? Which one will have a? Don't try and say an answer quickly. If no answer is also a good answer, right? The idea is to identify at what time there is no answer also. Can I say among this one, which is the one that is 0.65, which is the one that's 0.82? Yes or no? I don't know any other information. I say coarse, intermediate, fine. So one is very coarse, one is very fine, the other is in between sizes. I can't, right? It could be either one, it could be anyone. I don't know. It could be depending on what do you mean by intermediate? How many sieve ranges have I covered in the intermediate, correct? Now, likely you can make an educated guess and say this 0.82 consists of a larger size range. That you can say, correct? Because if it's only one size, I should be closer to 0.74. Because I have a higher value that I experimentally determined, one, you can simply tell the guy you're wrong, right? But telling somebody that he's wrong without proof also is not a good thing. But then you can say that maybe that range has a larger sizes included. You get the idea? So you between 0.65 and 0.82, and I do a lot of simulations, a lot of experiments here, and I say that's my optimal value, which is 0.7, 0.80785 or something, and then 0.79 is what I get using the compressible packing model. So the model actually does pretty well for lots of different things. All right. So that's the idea of particle packing, which we will come back again when we talk about extrudability and buildability. Should we stop now or Coffee break? We can stop, right? All right. So we'll stop now. Oh, any questions? Any, or we'll come back and do some questions then. Because I'm not going to get through what I'm supposed to get through until lunch. So we'll do some questions and we'll stop somewhere in the middle. Okay. So we'll have a longer day today. We'll leave you only longer later.
Yeah, you have to take still things.
They have to sit and pretend to be awake. I have to sit and pretend to be.
I'm not going to get it. So let's break. Coffee is arranged. We'll reassemble when 12 o'clock. Yeah.
We'll start. Everybody here? Okay. So continuing from where we left, we're talking about packing effects, how that affects rheological properties, and how eventually, we haven't seen that yet, but how eventually we will see how all of this will affect extrudability and buildability, which is basically your printability criteria. Yield stress and slump, you heard this in the morning. Yield stress is an indicator, or slump is an indicator of yield stress. So for different materials, if you look at yield stress as you add more and more materials, again, many of the concepts we talked about, you can see here, right? If I add 30% of limestone and replace cement with that, and limestone is much finer than cement, see my yield stress increases, right? Why? The number of particle contacts have gone up. As I go with smaller and smaller sizes, the number of particle contacts have gone up, yield stress has gone up. Similarly, so everything on the right side of OPC here are systems where cement has been replaced with particles of smaller sizes, right? And then with metakaolin, you'll see the yield stress really, really going up. Why? Not just particle size effect, but also the effect of clay, which has the ability to hold on to the water and not allow water to the rest of the mix so that it'll become much stiffer. So with metakaolin, that's what you see. With all these mixes, all of these ones, which it is simply the effect of the more number of particles, more number of particle contacts, more energy required to break the flocks, more stress required to break the flocks. Correct? That's what you're seeing. And then if you do yield stress as a very quick and slump as a very quick measure of can I print or not, this is what you get. At very low yield stresses, you really can't print. But at lower slump values and higher yield stress, you get some stable printed shapes. Again, trial and error way that you can get it, and you can relate yield stress to slump. Packing and printability, going back to the same idea, how do we now start to quantify packing and printability effects? So here are a few printable mixes. Again, the idea being that OPC with some other replacement of materials to get you better buildability, better shape stability, and all of that. There are now 3D printing systems that are called 2K systems. So 1K system is basically your pump and one extruder. You extrude that one material. Now we have 2K systems that will allow you addition of accelerators or whatever admixtures just before the nozzle. Right? So why do you need that? You want it to be extrudable. For that, you want a low enough yield stress so that it's extrudable, but then you add an accelerating admixture at the tip of the extruder nozzle so that when it comes out, it'll become quickly buildable. The yield stress goes up because the accelerator accelerates cement hydration. Remember I told you, if I have two particles and cement grains in between, the one way to increase the yield stress is to get acceleration of hydration, get more hydrated products formed, correct? Replace the water with more of hydrated products, correct? So you get, again, remember, for any unit volume of cement that you take, or cement when you start before hydration, after hydration, you get twice the volume roughly, correct? All of you know that, right? A unit volume of cement hydrates to twice its volume when hydrated completely. It's not hydrating completely here, but you see how the volume has increased. That increased volume fills up the space, increases the stiffness, and be able to hold the shape much better. So that's the benefit of adding an accelerator at the tip of the nozzle just before it comes out. You don't want to do it ahead of time. You don't want to do it while the material is within the extruder, because it'll get stuck in the extruder. Addition of reinforcement. Again, a material design of 3D printing has a lot to do with fiber reinforcement, not because we can't print without fibers. We can absolutely print without fibers, but the fact that we have no other really credible way of reinforcing this material. So is there a better way that we can at least get some tensile strength built into your printed material? So fibers are added. And if you look at random shape of fibers added, you get through it. You see these fibers aligning along the direction of printing. The fibers will start to align along the direction of printing. So when you print a layer, you will have short fibers aligned along the direction of printing. Like we talked about yesterday, you're now getting an anisotropic composite material. The concrete does not have same properties in all the different directions. Depending on the direction of testing, your properties are going to be different. Not much in the compressive property part with fibers, but with respect to tensile properties, flexural and tensile properties, which is something that we need to think about. Types of fibers, you have lots of different types of fibers that you can use: aramid, glass, textile, cellulose, polypropylene, lots of different fibers. Effect depends on the type of fiber, quantity of fiber, aspect ratio, which is length to the least lateral dimension of the fiber. Print parameters selected, how quickly you're printing, how many layers you're printing up, all of that. And then the material composition. So again, fibers, we'll see more of that when we talk about mechanical properties, but fibers also influence the properties. In the fresh state, fibers influence workability. All of you know that, right? When you add fibers, workability is influenced. Changes yield stress, changes cohesiveness, shrinkage, cracking, surface finish. All of those properties are changed by fibers. And if you have an improper mixed design, you will have settling of fibers, improper bond, stiff mixtures where you can't print, etc. Printing fiber reinforced mixes, just to give you a few examples. Um, Remember the wall effect that you saw with aggregates, where things will get stuck onto the wall and create a different packing closer to the wall? Same thing here also. You will have fibers there, and in between you will have fibers all randomly aligned, and then depending on the size and the effect. But as you come through the nozzle, effectively, if the fiber dimension is anyway close to the size of the nozzle, you will have aligned fibers. If the fiber is extremely small as compared to the nozzle size, you will still get random orientation. In regular concrete, when you throw in fibers, you are relying on a random orientation, correct? You expect the fibers to be randomly oriented so that your concrete gets the properties equally in all three directions. So here are some examples of fiber effects on the hardened state. Compressive strength, flexural strength, you can see that, and we'll talk about some of these things as we go through. Plain versus fiber reinforced. Compression, really fibers don't do much in compression at really small volumes. Very high volumes when we use UHPCs, ultra high performance concretes, where up to 3% by volume of fibers are used. Then you will start to see increase in strength. This is about 0.3%. You will see almost no effect in compression, but you will see effects in tension and flexure. In the hardened state, again, you see here fiber dispersion, of how the fibers are dispersed in the, so when you're testing in flexure, how the fibers are distributed. So if your fibers are in this direction and you are bending it in this direction, these fibers arrest the cracks, and therefore the flexural strength will be higher. Whereas if you are in this direction, cracks can really go in between fibers, right? So you really have no increase in strength. Again,
Out of the fiber, which is good for tensile strength.
steel fibers, obviously, right? Steel is, because steel has better tensile properties, it'll be better. If you want crack reduction or load, polypropylene is perhaps good. But aramid fibers are also very good, very stiff fibers, but they're much more expensive. But steel is perhaps the best and most commonly used, so you can use it evenly. So again, for flexure, if you have a beam that you're testing in flexure, and if your fibers all aligned in this direction, a crack that is going in this direction, assume that you have a beam like that, a crack that's going in this direction will find a fiber, and you'll find all the effects associated with fibers, crack blending, crack deflection, all of that, and therefore the toughness will increase, the flexural strength will increase. Whereas if you print it in such a way that fibers are aligned like this, a crack can go right here. You might not see any influence of fibers at all. If you have normal kind of casting of concrete, you expect the fibers to be in all different orientations possible, all different directions possible, which means statistically there is a chance of finding a fiber everywhere, and that's why the properties are increased. In this case, the properties are much more increased because you're absolutely certain to find a fiber on the path if you have fibers aligned in that direction. So everybody gets the difference, right? So printing direction matters. This is simply to say that printing direction matters. How you print, what direction you print matters with respect to testing. Now, if you print a slab and cut a piece of beam to test, the direction of testing matters. So when you say that I got so and so flexural strength when I used fibers in my 3D printed mixture, what you have to specify absolutely is what was the direction of testing. Because you're dealing with now an anisotropic composite. Any of you who have taken continuum mechanics stress analysis class will know that now your stress tensor will have 9 components. We simplify to 3 components. If you have x, y, z directions and you do sigma 1, sigma 2, sigma 3, now you will have 1, 1, 1, 2, 1, 3, 2, 1, 2, 2. You'll have all those 9 components. So make sure that that will have to be accounted for. Of course, you can remove a few of those because they'll be very similar, but generally it'll be what is called an anisotropic composite. Target demands in what we want, again, things that we have talked about earlier. Rheology, important. We talked a lot about rheology. Extrudability, we are starting to talk some of that. Stability, we need it to be stable. How much time? All of those, there is viscosity, there is static yield stress, there is dynamic yield stress. All of those will have to be accounted for in some fashion. Now, will we be able to account for everything all the time? No. But like every good optimization, you should get 2 of the 3 correct. Right? One of the 3 probably won't work. None of the 3 absolutely is a disaster. But at least 2 of the 3 parameters that you want, you should work, and you should be able to pick up which one you want. So if I'm just looking at there's a very, very simple conceptual diagram to show, because right now, you know only about yield stress and viscosity, correct? That's what the rheology that you know. You know static yield stress, you know dynamic yield stress, you know viscosity, what is that printable region in which this works, and this will in turn help you to find what is that mix that satisfies these given criteria. So if you are doing 3D printing, like many of these ready mix companies, if you ask for an M30 mix, they will have a standard M30 mix. When you go and ask for an M30 concrete, the guy is not sitting there and starting to proportion M30 concrete. They have an M30 concrete ready based on the cement that they use, the aggregate sources that they have, all the conditions that they have an M30 concrete optimized and ready to go. So next time you go on M30 concrete, they have it. They'll have M35, they have M40. Only time they may have to do a new one is when you ask for an M100. Because nobody asks for it all the time, then they'll have to design it. Similarly, if you are in the process of printing concrete regularly, if you want to print a complete house or a complete building, you will have that mix ready, and this will be a good place to select what that mix would be. And of course, you would tweak accordingly. Today is 40 degrees, tomorrow is going to be 30 degrees. You will adjust the parameters accordingly. As a concrete engineer, you would know how to do that, right? The admixture dosages, the cementitious content. You will adjust things a little bit here and there, but you will have some kind of a standard recipe, like restaurants, right? You go there, they have, I mean, not that when you order, they'll have 200 things in the menu, but really there are no 200 things, right? They have a bunch of standard things that they mix. Similarly, as an engineer, you have some of those standard things, all based on what parameters you choose to control, what parameters you choose to test regularly. The reason why viscosity and yield stress is easy, because you can test for them regularly, you can do it easily, you can do it quickly, you can have a database. Again, quality control is all about having data. Quality control is not about, oh, I can do it today. I just did something, it came out well, I'm going. No, it's about keeping the data, making sure that you can be consistent in how you do it. And these kinds of measurements help you consistently make those mixes. And that's why. So, yeah, yes.
We have three parameters. If we are looking at these three parameters, are we basically looking at the buildability and explodability?
No. You are, so basically what you have done is, and that's where we are getting into, what you have done is, I have created a mix, I have characterized this, I have printed it, I have printed a few combinations, I have found these combinations to be good enough to print. And because my materials are not changing, I'm saying that this plastic viscosity, this yield stress, this dynamic yield stress is good enough for me to keep as a baseline. And then that's my starting point. From there, you may tweak, you may do different things to improve upon things, but that's your starting point. I may build up, I may get only 1.5 meters. To get 2.5, what do? I have a starting point now from which I change to get to my different buildability.
But see, we have something to learn from the conventional concrete where we evolved in design process where ultimately we use to design concrete on the functionality.
Correct.
So can't we learn from that? And I don't know if there is any round robin exercise going on, whether there is going on, and number of parameters. I just want to know.
So there are round robin exercises going on for basically not much on the workability things, because everybody, like I said, all printing is dependent not on the material but on the printer too. So when you do round robin, how do you really standardize everything? The cobalt printer is different from an icon printer, is different from somebody else's printer. So what they do is this very generic terms like plastic viscosity, yield stress, you can quantify that. And then for the typical printer, how much of extrusion pressure do they apply? What is the length that it travels through the nozzle? What is the shearing action of your screw extruder? Based on all of that, you make changes, you make these changes accordingly. So you can't generalize it that much, but you can definitely start from a certain starting point. That's where all these tests do. So none of this will take you to the final point, but it will take you to a landing station from which you can play around and get your own mixes. And I think as long as printers are of different families and types, that's pretty much the best you can get to. And what you eventually will do is, of course, you will standardize your mechanical properties, your final performance differently, because that's your eventual thing. But from a workability, rheology point of view and buildability point of view, it has to be a printer dependent thing. Does it? Okay.
Sir,
Yes.
I have some with sir, very helpful. But I can reject the paste for innocent for the plastic is cost because there is a magnetic.
Yes. Good question. Good question. So if you measure this for paste and you do the printing, you can relate the buildability and the extrudability to the properties of paste, assuming aggregates to be a dilutant to the properties. So you can use the paste qualities. You can do, so I have a plastic viscosity of the paste that goes in, because I really can't measure the concrete. But you have concrete rheometers available, but it's very difficult. The variability in concrete viscosity measurements are extremely high. So you do the paste measurements, you do your concrete mix or a mortar mix, and you can do mortar rheology too. Not that difficult. All these measurements you can do on mortar sands also. But if you want to do concretes, you can do this mortar rheology, you can actually do the printing of it and see how the rheological parameters relate to it. You will have to do a few trial and error exercises to match it. But once you match it, you have a baseline to start. But otherwise, you really can't do it. Now, the other way some people say is that no problem, I will give you models to do this. But rheological models, which we will talk tomorrow or day after, are also kind of a hit or miss thing, right? But there is no way that none of this will work without you doing trials. And with 3D printing, you have to do trials with the printer that you're printing with. I do a trial in a lab in my little desktop printer and I take it to the field. Yes, the yield stress in my lab mix was 80 Pascal. And I go and that 80 Pascal paste, when combined with those aggregates, and I got a workable mix. You can keep that as a standard reference, but you can never say that that's a yield stress of that paste, that concrete. It's a different value. Right? So again, it's complicated. It is confusing. It will be like that because we really can't have one measure that goes into the entire spectrum. And that's where knowledge and understanding of what is yield stress, what is viscosity, how can you change it? So if you know that I am able to extrude, but I am not able to build up. Think about a case, right? I did this measurements in the lab. I got a yield stress of 80 pascals, a viscosity of say 300 centipoise, whatever that number is. I did that. Now, who is that? Okay. So if you get that, if you have a plastic viscosity and yield stress that you have from your paste, and you're able to print that in a certain way or extrude that in a certain way, but you're not able to build up beyond layer 5. What does that tell you? What does that tell you? What should I change? Maybe the yield stress has to be changed, right? I'm not having enough. Now, you can also look at what yield stress, dynamic or static? Question to be asked. Maybe both, maybe not, right? But then if it is not building up, it is actually giving you some questions as to why this space is not able to hold its shape and able to hold its weight. You have to adjust some rheological parameters. How do you do that? Again, that is purely in the realm of you as engineers. You might choose to say that I can do it with my binder change. I don't want to do anything else. I just want to change my binder and I can do it. Or you say that maybe my sand content is not enough. I may have to increase the sand because sand comes with some stiffness already. So increasing the sand content automatically increases the stiffness of your mix, right? And then, but increasing the sand might play around with your extrudability. So again, the point is that there is no one size fits all solution here. You have to understand the lay of the land, understand what these basic parameters are, and build up your understanding based on that and be able to do it. Like I said, what you did with one printer could be a good starting point for another printer. You may have to be. I mean, it might work beautifully well. Who knows, right? It might, you did in one printer, you take it another printer, you're able to work wonderfully well. Who knows? Great. If that happens, you saved a lot of time and energy. If that doesn't, you have the tools to change things. That's the whole idea. You have to know what to change. Okay. So, straightforward answers. What should I change? None of us can say what should you change without seeing the mix and without being able to go to the field and actually see what is happening. And once you see it, you might say, okay, it is extruding, it is building 4 layers. I need to build to 8 layers. What do I need? Maybe I need to change my sand volume fraction from 0.45 to 0.55. Or I need to change my water cement ratio from X to this. It's extruding so well. I don't need to extrude it so well. Hey, maybe I can reduce the amount of admixtures. Correct? All of those are decisions that an engineer makes in the field. And I use this example. If you're a surgeon operating on a patient, you have all the data that you have. You have done CT scans, MRI scans. This is what it is. He is going to go and open. Do you think that's exactly what he is going to find when he opens the body? you might find something else. The surgeon must be able to act on its feet and say, okay, this was not seen in the CT scan, this was not seen in the MRI, but I'm actually seeing it now. He can't say that, look, I did not see it in the MRI, so this must not be there, it's false. No. At that point, what you see, you should be able to make the changes. And that's what makes a good surgeon different from a YouTube learned surgeon. Right? So that's the whole idea. We'll stop now. So I think this is almost done. I probably have, yeah, um, connections with all of this. We'll start with this again. Going back to the same, answering many of your questions here. It's going back to the same thing. We'll come back after lunch and probably finish this up. Any questions? Any clarifications?
The yield stress that you was mentioning, like, again, it depends on the type of technique, like another amusement pattern.
Yes. Yeah, yeah. It depends on whether you're measuring a parallel plate or a cone. But the character, that's why the protocols that you talked about yesterday, you have to have those protocols lined up and be able to say the yield stress I measured using this technique under these conditions is corresponding to whatever it is. It has to be really, I mean, otherwise, what are we trying to do? We are trying to reduce the number of trials and errors, and we are trying to make sure that scientifically what we are doing is correct so that we can translate it as fast as possible. If you don't have those protocols lined up and if those are not correct, you may have to do extra results to do extra tests to do all of that. Other questions?
Like the cement as it hydrates, its volume is going to.
Yeah.
So, does it not affect the overall packaging?
So every packing calculation is based on the unhydrated state. Is based on water hasn't touched it. So it's all a dry packing. But what you do is you can do it in two ways. You can take a certain volume and say, pack me the best to this volume. Okay. So that is what you typically do to get you the maximum packing fraction. Now, if you want to do post factum analysis, I have a water cement ratio of 0.4. I used a cement of this particle size distribution. Tell me what the packing fraction is. At that point, you take a volume and say 0.4 water cement ratio corresponding to volume, find out what that water cement ratio. You say that volume is unfilled. How will I fill the remaining volume? If I have that much of cement, how will that fill the remaining volume? So that becomes so in hydration studies, that's a model that we use because hydration is always with respect to a certain water cement ratio. Whereas for particle packing, to understand what's a maximum packing fraction, we'll just say, here is my volume. Tell me how much is a max I can pack, because the lower the water, the better. Especially for UHPC, my water cement ratio is 0.18. Right? So I want as much packing as possible. Even then, remember, as much packing as possible will still get me only 0.75, 0.76. I have 25% void while my water is only 0.18. What will I fill the remaining with? Right? That's a challenge. If you want a higher strength, I want to actually pack it with something as much as possible. And when I know that I have only 0.18 of water, I want really, really low amount of other stuff. Right? All right. Anything else? If not, we'll come back and continue this. Thank you.
Okay. We do have ID room. See the signal, ID room.
Check my ID.
IT Madras works, I know, because when I was in IT Madras, I used EduRoam. The first time I used Manu's account to log into EduRoam. It works. It's, right. The only issue is with the software. I think some of them it's not working.
Let them come and fix it. I think I mean I can. The four of them can go around and help everybody.
Yeah.
If we start, let's say around 5 minutes. Next break is 4 o'clock.
Next break is to yeah. No, what I'll do is maybe I'll do 50 minutes, give a 5 minute break, and then do another at 4 o'clock. After 4 o'clock, they can do the
We'll take a coffee break.
yeah, and then they can
Yeah.
yes.
Coffee break at 4. 3:30.
Whatever she says. I think at the end of the day now I've no point fighting with these people. I think they're Yeah, another 5 minutes. Let a few more people show up. Until people show up, any questions that you got while you were having lunch, while you were thinking about 3D printing, while you were eating lunch? Hopefully not, right? No. Any questions? Anything to confirm, clarify before we go further? We are still in the world of rheology. We haven't left it. We'll probably do it today, and then tomorrow we'll start with new topics. Maybe midday tomorrow-ish. But this is one of those topics where it's quite a bit of importance for 3D printing. Any questions? Any confirmation, clarification from anybody?
But we are kind of impacted fibers from now. Again,
No, you can't test rheological properties with fibers, right? So what you do is you have to infer that the addition of fibers based on theory that we said because of the loosening effect that fibers do. You have to assume that your properties are going to change, right? So you have to make that assumption and then adjust appropriately because fibers are you cannot test rheological properties with fibers unless you're doing rheology of concrete, which I said is complicated. So fibers are required for a certain purpose. Fibers are required for a certain hardened property that you can't otherwise control. Therefore, we will have to make sure that whatever fresh stage property you have to change accordingly. So it becomes an inference that you have to make because you need that for later age properties. You can't design for fibers. You can, of course, know that having done this, this is how my yield stress will change. This is how my viscosity will change. So maybe here is the change in the mix modification that I have to make. All right, it's getting 2 o'clock. We'll start. Let the others come in. So we will continue with the idea of rheology and rheological modification. So a few things, right? So we ended last session with the idea that yes, you can do all the rheological tests. You typically will do the tests on pastes. And when you have to do concretes or when you have to actually print, the printer also becomes part of the problem or the solution. So you have the mix that you have tested, you print it, and you evaluate what the correspondence are with the properties and the printing. And that's why I gave you the example of a ready mix concrete guy who will have an M30 mix made. So similarly, you know that this is printable, but then depending on the situation, depending on your material, your printer changes, depending on environment, you make whatever minor changes required to ensure that your structure is extrudable and printable. Is that idea clear to everybody? That we are relying on a rheological measurement as your fundamental measurement to go with, for which you make correspondence with the field printed material made out of this paste. The rest are all correspondences that you're making. So that when the paste changes, you know how else it's going to change. Right? And that's how you make those changes. So now what else can you do to change the rheology? So here is one method people have tried where continuous CO2 injection. I mean, it is touted as a method to utilize CO2 in curing. I mean, people love to use CO2 in whatever you want. So if you inject CO2 into the nozzle, as the mortar comes through, you have CO2 coming in. That will create some precipitation of calcium carbonate. You will get so if your material was not completely extrudable, you will get more of CO2, calcium carbonate precipitation, get a little more rigid mix to come out of it. That's the idea. That's theoretically what it is. But the amount of calcium carbonate that's going to be formed is very, very, very small. This is a nice laboratory experiment. It's very difficult to see it actually working in practice efficiently, but nevertheless, one method that people have looked at. There is a CO2 flash mixing where you inject CO2 at the auger, at the nozzle, and then you extrude the filament. Again, same idea that you get some calcium carbonate precipitation. And here is how it is. Calcium carbonate reacts with calcium hydroxide. You form some calcium carbonate. CO um, carbon dioxide also will try to, because of the gaseous state of CO2 and the way it changes the solubility of ions, it will make a little other rheological changes as well. Nothing huge. And then if you have a 2K printing system where you can have another material that's added, you can control material deformation collapse, you can add calcium hydroxide like an admixture, you can get stiffening and setting faster. So lots of different methods, again, depending on how you want to use it. Extrudability, we talked about, what is extrudability. So that's a ram extruder, that's a screw extruder. This is the most common type that you see where the material comes through and extrudes and then comes out of the nozzle. And then you get print whatever shapes that you want. Buildability is the process by which you build up layer after layer. And again, we talked about what properties you need for that. Challenges, and here is where we are going to get into the next set of lectures. Optimal yield stress, structural recovery, thixotropy. You heard about it yesterday. We'll talk a little bit more about thixotropy. But how about structural recovery? So buildability is a function of both yield stress and thixotropy. Material thixotropy also plays a role in how well you can build up the layers. So the way to look at is, so this is actually a nice schematic of how we can think about what are the post-printing requirements. The moment you print what you want, right? Your yield stress, you have an initial yield stress. You want the yield stress to build up, or you want the load that you want to be resisting keeping on increasing as you add more and more layers, right? And your rebuilding kinetics also has to increase so that the load that you have to take care of is taken care of by the development of kinetics in the material that eventually leads to formation of material strength. So this is like an envelope. You never want this stepped line to go beyond that blue line. You see that? You want this to be lower, or rebuilding kinetics, and how much ever yield stress that you have generated should be higher than the stress that's added on layer after layer, right? You have to be within that zone. And if you're really, really good, you want that to be very close so that you have very optimally made those. You don't have excess strength in it. You don't have excess properties. You have designed it really well. That's the optimal way. That's what we will talk about. Again, coming back to the same picture I showed you earlier, because the next set of slides I'm going to talk about is in the realm of extrudability and buildability. So we will start with this one more slide. I'll just skip that. So this is about, we talked about particle packing, material design for printability. And now what we're going to do is really rheology apply to 3D printing. So lots of you asked questions. How do you relate whatever you have to what is printable? Lots of those will be answered now with rheology applied to concrete 3D printing. So everybody comfortable with the idea that the rheological demands in 3D printing are different. It changes from time to time. You need a delicate balance between flowability during printing and strength after deposition. Again, the extrudability and buildability, I really explained here. Extrudability being flowability during printing, and buildability is a strength after deposition, right? So those are the two things that you want. A material needs to be a liquid like pseudo-solid to be pumped and extruded, but must quickly become a rigid structure to support its own weight and subsequent layers. So far what we have talked about, or mostly what we have talked about, are about the characteristics of the material in terms of particle packing, the yield stress, the viscosity, all of it that you test and characterize and keep ready for this process to happen. Now we are going into the process. So if you think about getting ready for swimming, if you are a swimmer, right? You go take a shower before you jump into swimming pool, get the right gear, all of that. Now you're ready to go into the pool and get extruded and built, or however it is, right? So what happens when the process really happens? Lots of preparation, lots of understanding what goes behind packing of particles, what is rheology, how do you test. Now you get into the nozzle and figure out what's happening right there. Okay. Static dynamic yield stress and thixotropy should be controlled through mixed design. So this is what we will talk a little bit more about: static and dynamic yield stress as well as thixotropy. Oops. So each stage imposes distinct, often competing rheological demands. What we need is successful material delivery to the print head, which means if you're pumping it, the material should come to the print head in a homogeneous, nice fashion. It should come through the extruder and extrude it nicely in a continuous fashion, and it should be able to build up steadily without collapse and damage. So that is the entire process that you want to think about. I've showed you this picture. So extrudability, how much time period you can extrude, the open time, how much material will keep the yield stress and plastic viscosity for it to be extruded out, and then how well you can build up and the structural buildup. So here are some videos that, let me see if we can show you those videos. So here is how you are used to seeing concrete generally, correct? That's what you're used to seeing concrete. You vibrate. That's your regular concrete. That's what you want. If something goes wrong, you can vibrate. You can take it off, put it back again. You can reconsolidate, revibrate. You can do all of that. But in 3D printing, what you need is you need it to be extrudable. So this is extrusion. If it's pump, oops, I did. If it is pumping, if you're pumping it, this is how you need it to be pumped. But extrusion will have different demands. So here is pumping concrete flowing through very nicely. But then you don't need just that. You need this as well. You need it to be extruded into layers nicely, and you should be able to build up eventually. So these are the conflicting requirements and demands that we have to think of. Uh, Material delivery phase, particularly when the material is pumped, what do you need? So again, guidelines. All of these, please remember, whatever you see are guidelines. These are not truth set in stone. Your material, depending on your environment, depending on your type of printer, might have differences that you have to work out on your own and set it ready for your purpose. But here are some guidelines. Like your mixture proportioning, you have guidelines. Go do a trial mix and make sure that everything is correct, right? So you have all of these are guidelines for you to do before you do your trial mix. Viscosity and yield stress must be sufficiently low to ensure smooth flow while preventing segregation or blockages. Very high viscosity, it'll flow very quickly. You don't want that because you don't have time to build up the strength after that, so you don't want that. Very low viscosity, you will have difficulty flowing. Very high yield stress, you will have difficulty extruding. Very low yield stress, it'll just come through. You won't be able to develop the strength to build up. So higher yield stress is desirable to maintain the shape of the extrudate and avoid collapse. Structural stability is essential to prevent immediate collapse. Issues look for excessive layer spreading or drooping. So if you have a layer and you put another layer on top, you don't want it to spread out and droop too much. Things to look for. Again, like I said, guidelines. Okay, let's look at some examples. Hopefully these videos will work. Okay. Oops. Why are they not working? Oops. It came and then it went. Maybe we should close it and reopen the slide set. Yeah. Yeah. Open it, close it and reopen it. Close it completely and then maybe reopen it. So, and post extrusion, that video also doesn't work. Right, post extrusion. So, at before extrusion, whatever yield stress and plastic viscosity. Post extrusion, once it's extruded, you want the mix to rapidly gain stiffness, allowing it to support the superimposed loads. That determines whether the structure can maintain its shape throughout the entire printing process. And then that is important because once you have extruded, and it has to retain the shape without drooping, without changing its shape, because that determines what the entire structural stability and properties of the build-up layer are, right? So it's important that once you extrude it, those properties are all efficiently maintained. So here is a summary of a lot of different characteristics. Again, everything kind of a summary of everything that we have talked about with respect to rheology. Buildability, you have to retain the shape and form after being extruded or deposited. In terms of rheological characteristics, what do you need? Static yield stress should be more than the supported load calculated using failure modes. We'll show you a few failure modes as we go through to see as you build things up, how are they likely to fail, correct? So if I put one layer and I put another layer and another layer, if the bottom layer can't take the weight of that, it'll just collapse, right? The bottom layer will just slump and collapse. If I'm able to build up, but one layer here thinks, you know what, I'm not really able to take my load if I try to fall down. Have you seen all these cereal boxes that are kept stacked up in your grocery store, one after the other? The top one is just turn one on the side, give it a slight deformation, everything else will fall down, right? The collapse, yielding collapse mechanism, the buckling mechanism. So which ones will control? We'll talk about that using whatever failure modes. Extrudability, you should have it flow smoothly through the printing nozzle without clogging. Yield stress is an important characteristic there. Flowability, degree of flow that you have. Literature shows empirical correlation between yield stress, viscosity, flowability. So you can use some of that to determine what you will need. Pumpability, yield stress and viscosity that you know from regular concrete. That's what we use a lot of. The segregation resistance, yield stress and viscosity is related to segregation resistance. Thixotropy, we'll talk more about thixotropy. Removing applied shear stress and shear rate used to calculate what's called the hysteresis area, which will describe the thixotropy of the mix, and workability, yield stress and viscosity. So again, yield stress and viscosity explaining so many different things, but context matters. In all of this, it's context that matters. When are you measuring? What level are you measuring? And are you translating it to the field for whether it's extrudability or buildability? So get this big picture under control. So printability, both extrudability and buildability, is governed by yield stress and plastic viscosity. Like a broken record, I've been telling this all the time, right? Buildability and extrudability related to yield stress and plastic viscosity. Why yield stress and plastic viscosity? Because that's easily measurable you can have a protocol to measure it. Once you measure it, you know what that means, and you can use all the parameters that you get out in your printer to be related to these parameters to get your black box ready, which you can change as and when you need it. The whole idea of doing this is to make sure that you control your processes and create some kind of an evolution to how you do this, so that the next mix doesn't have to go through all of these again. Right? You have a database, you have a set system to design and develop this. So here is time dependence. What happens if you mix immediately or extrude immediately? Not bad, right? The mix that you have is able to extrude even at 30 minutes. So you can say that this mix has an open time, or a time that it is extrudable between 30 and 45 minutes. What happens at 45 minutes? Is it extrudable anymore? No. So at about 30 minutes it's extrudable. Now, if I make a lot of mix and my printing rate is very slow, and I'm not able to print this entire mix either because of printer constraints or because of layer size constraints. Somebody told you I need a really well defined, very tolerance controlled structure, very fine, needs to be very smooth. You need to have thin layers so that it's all very nice. Then you make a mix and it'll take a lot of time to use that mix, right? Which means how much time can you use the mix that you have mixed once? And now your question of how fast you're able to print. Now you'll know that you might have a mix that's extrudable if I print at 10 millimeters per second, but that same mix will not be extrudable if I do 25 millimeter per second. Can you think of that? I do it very slowly, it'll come out. I try to print very fast, it'll break. Now you're the question of how much does printing time, that is printing speed. It is a function of layer thickness. A thinner layer might extrude even if it is printed slightly faster, but if you increase the layer thickness, that might break. Now you see now the material properties, the printer properties. Now we are introducing one more set of variables, which are the printing parameters. It is not just the printer now, whether it is screw or ram or auger or whatever way. Now it's about, or the nozzle size, it's about how fast are you trying to print, how quick are you trying to build up. You get now the third variable in this process. So what's the first variable? All the material properties. Second variable, everything that has to do with the printer, the nozzle size, the printer screw, ram, whatever kind of extrusion process you have. What's the third variable? The printing process. So material, printer, and the printing process. For printing process, open time becomes an important issue. When can you actually print? So this mixer now at 45 minutes, it's not printable. So now what you do is at 60 minutes, I'm not able to extrude at all. So what I do, I take it again and remix the whole thing. I can do a little bit more. So now in your mix, am I ready to take that risk and say, let me mix 1 cubic meter. I know I'm going to extrude only very slow, but in 40 minutes, I can remix once more and put it back in the extruder head. Are you willing to take that risk? You may, because if you're not saying that, no, I cannot, then you're throwing the material away. Right? Now, what you need to know is, are you able to do that? Do I know the properties well enough to do it? If I can remix and do it. Again, just as an example. There are several other ways of doing it, but just as an example. So it's one way of thinking, how does the printing process influence? Tomorrow we'll see more about this in mechanical properties, about layer sizes. I printed a size of 10 mm versus 20 mm. How does mechanical properties change? Same material, right? Do you think it'll change or not? We'll see. Suspense. I showed this. So can mini slump test be used as an indicator of yield stress? As in the morning you saw that yes, slump is an indicator of yield stress, so you can do that. Now, what is yield stresses? We have talked a lot about yield stress. I want to make sure that we get this very correctly. Yield stress is generally defined as the stress required to initiate the flow, right? Now we are going to do two different variants of it. Typically, what you tested yesterday, you typically did a dynamic yield stress or static. Which one did you do? You did static. We did it with time. Constant shear rate. Okay, so you did a constant shear rate. You did a static yield stress, which is a good indicator of how much buildability you can get. The dynamic yield stress that you do on a strain rate growth test, for example, if you build up from a strain rate of 5 to 100 and you take the up or down ramp and take the slope, when you get the dynamic yield stress, that is a stress that you find to maintain flow. A suitably low dynamic yield stress is required to be pumped smoothly through the mix. So pumping requires a suitably low dynamic yield stress. Building up requires a suitably high static yield stress. And static yield stress, so a stress growth test where the material is slowly sheared until flow begins. You measure the static yield stress, and a flow curve test where you do the strain rate ramping up measures the dynamic yield stress. Again, protocol differences, you're measuring two yield stresses which are, so if I do shear rate ramping, up curve, down curve, I do the straight line, I come here, that's my dynamic yield stress if I do a shear rate curve. Whereas if I do a shear stress as a function of time, wherever it gets to maximum is a static yield stress, and then the flow continues unimpeded. So that's the static. So this is for buildability. And if I look at torque versus time, I needed to overcome a certain resistance of the material to be able to make it flow. And then once I do it, the material flows at a constant torque or stress. That's your dynamic yield stress, whatever I need to overcome. Good. So two different terminologies. Now, thixotropy. So now we get to the idea of thixotropy. Again, you heard this yesterday. This is the time-dependent reversible changes. It could be change in yield stress. It could be change in viscosity. It could be change in storage modulus. Any time-dependent change in a rheological property that is reversible is called thixotropy. Includes structural breakdown and buildup. So if I remix, I showed you this example of I remixed the mix again and it was able to extrude. What happened when I remixed it? It's a behavior, thixotropic behavior that you're seeing. When I remixed it, it's able to go back to the properties. I can redo it, which means my material is thixotropic. A non-thixotropic material will not allow me to remix and get my shape back. And if I try to remix after an hour and a half, you might be able to remix, but nothing will come out. You cannot extrude. So the material is thixotropic only for a certain time. And that time-dependent change in properties is called thixotropy, and it influences. So one of the most important applications of thixotropy is in pumpability and formwork pressure. Self-consolidating concretes, for example. When you have concretes that flow like water, it influences the formwork pressure much higher than a solid. Because if a solid, it's all the weight is going down. If it is a liquid, it's acting, it is applying a lot of pressure on the formwork. So if your formwork is not very strong, a liquid-like material will fail. And you should have heard examples of grain silos failing when you put in a different grain than what the silo was designed for because of the differences in pressure that was not designed for. So again, the idea of formwork pressure. So thixotropy, what you do is, if you do a shear stress as a function of shear rate, one of the ways to do it, so you do the up ramp, down ramp, and the area between it, and you find out what shear rates you want to decide, use it. The area is between the up and down ramp. What are you doing when you go in the up ramp? So I've taken a cement paste and I'm shearing from 5 per second to 100 per second in a ramp rate. What am I doing while I'm doing it? I'm breaking down that structure, correct? See that? So slowly at 5 per second, my shear rate is slow. And then the next ramp is 10, much faster. 20, even faster. 100. By the time I get to 100, I have broken down my structure. So my up ramp is an indication of breaking down of the structure. And then I keep some rest time and I slowly come down. Right? I slowly ramp it down, which means with time, I'm now not disturbing it that much. It means what am I doing then? Building up. So if it is not building up at all, I'll come back along the same line, right? Along the shear stress versus shear rate, I'll come back along the same line if I'm not building up. But if I'm building up, you will see that difference. You will see a structure building up. The area under it is called generally a simplistic measure of thixotropy. There are better ways to measure thixotropy as well, but this is one way of measuring thixotropy. This is a short-term thixotropy because I am doing whatever instantaneous. I mixed it. I'm doing my test instantaneously. That is thixotropy at time 0 or time whatever very short. I can do the same test after half an hour of mixing. After an hour of mixing, after 2 hours of mixing, the build up and the breakdown will be different, right? The area that you get under build up and breakdown will be different depending on the thixotropic qualities of material. If the material has a higher level of thixotropy, you are able to build it up much better. Is the idea clear? I'll show you some more examples as we go through. So, thixotropy enables the dual contradictory requirements of pumpability and extrudability. Pumpability, when subject to a high shear stress during mixing, the material's internal structure breaks down, resulting in low viscosity and good flowability. So, we talked a lot about breaking down of the structure yesterday when we talked about yield stress, right? So, now that is low viscosity, good flowability, prevents blockages, continuous smooth flow. Good? That is when you are doing a high shear stress during mixing. Immediately after extrusion, when the shear stress is removed, remember when it comes out through the nozzle, there is shear. And at the moment it comes out, the pressure drops. There is no pressure, no stress at all. Right? When that happens, the material is at rest and its internal structure is starting to build up. So, what are we building up? We are building up yield stress. We are also building up, we are recovering viscosity. Right? So, we can do both ways to do the test. So this leads to a quick increase in static yield stress, allowing each layer to be built up to support the weight of subsequent layers. So here is one example, a pre-shear, a rest time, ramp up, ramp down. So ramp up is breakdown, ramp down is build up. Structure is breaking down, structure is building up, and you can do, so these are mixes with some little bit of graphene added to see what the effect is. You can see this is OPC, and this is the thixotropy of plain cement paste. When you have a little bit of limestone added, when you have fly ash added, when you have fly ash and limestone added, you can see the effects of adding of these materials on thixotropy. So this is short-term thixotropy, primarily colloidal flocculation. It's by, because at very early ages, you really haven't formed hydration structures. It's basically the flocks building, coming back together. You've tried to break them up, they're coming back together. So it's basically flock building up very early ages. With time is when hydration starts to pick up. What happens after extrusion? The mixer needs to rapidly gain stiffness, often achieved through tuning of thixotropic behavior, allowing it to take the superimposed loads layer after layer. This process is called buildability. You can use two different tests to characterize thixotropy. One is viscosity recovery test. The other is static yield stress or storage modulus evolution with time. So remember, again, I'm going back to what we said earlier. We have a bunch of tests that we talked about yesterday. They are all material characterization tests. You never bothered about what the printer is, what the nozzle is, all of that, right? Yield stress, plastic viscosity. From those tests, you derive these properties, which now has some relation to your extrudability and buildability. You see that? Yield stress and plastic viscosity are indirect indicators. Thixotropic behavior are direct indicators of extrudability and buildability. You get some more clarity in the properties that you measure to understand what your material is doing. I'll stop here. Any questions on any of this so far? Yes.
If you're doing extruding, for example, if there is UPC, the initial sitting time of UPC generally around 25 to 30. But what if we do the extrusion after 30 or 25 minutes, then we expect it to last year, longer than that.
Correct.
Ensure that they build each other.
Yeah. So, and that's some of the very important considerations, and that is why generally plain OPC extrusion is very difficult. You always add some other material to it. You pretty much have a supplementary cementing material. You have a chemical agent to change these properties, because if something sets very quickly, you really have no control over it, right? So you do add some other material to delay setting, to ensure that the material stays flowable for a longer period of time. Those are all mixture design characteristics that you have to think of. Pretty much plain OPC printing is non-existent for several reasons, this being one of those. Other questions?
But then we are going into years. Isn't it possible that interface between the 2 years or different kind of data?
We'll talk about interfaces and failure tomorrow. So we'll do the fresh state. We'll slowly build up like kids become old. We'll make sure that we are young enough now. We'll get old tomorrow, day after. Other questions?
So can we use initial test concept of
Not for thixotropic behavior, because what happens is mini slump, you can do it of, well, you can kind of do it, but the problem is the variations are going to be so small that you can't pick up anything. So you can take the test, do a mini slump, you can remix it after half an hour, do a mini slump, you probably will get the same value. It's not sensitive enough to pick up those differences, because yield stress by itself, yes, but this is not yield stress alone, right? It is that change between the yield stress and the up and down ramps. It is that little difference in the area that we are looking at. So some of the interparticle interactions, you might not get it. Yes.
What are the questions you recommend for website conditions? If you are going to be mass production.
I have seen, I'll get there when I've seen a few of those. I haven't done any of those, I can tell you that. I haven't done any of those, but I have seen a couple of companies doing a few tests for these. We'll get there. Other questions? All right. So we'll talk about viscosity recovery test, which is a sequence, and this is a very simple test. And what you do is a sequence of steps in your rheometer that mimics extrusion-based printing. So what is an extrusion-based printing? So this is called a 3-interval thixotropy test, where you do a stepped-up ramp-up pre-shear. You're pre-shearing it initially, right? And then you are determining, and for approximately 80 seconds, so this is homogenization phase. And then you do a low shear rate, very low shear rate. You see that? 0.01 per second for about 60 seconds. This is the viscosity of the fresh suspension before printing. Right? So this is what is the characteristic of the material ahead of time. And then you immediately ramp up very quickly. You get to a high shear rate of 100 per second. What is that? The mixture that was sitting in the extruder is now suddenly being extruded, right? Shear stress is very high. Shear is very high. You extrude it under a very high shear, and that is mimicking the extrusion process. And then very constant low shear rate of 0.01 second after extrusion, it is at rest. To mimic that, a very, very low shear rate. So this is called 3 interval. You can see those 3 intervals, right? Pre-shear to 1, 2, 3. First interval is the basic characteristic viscosity. Second interval is the extrusion process. Third interval is the rest. how well are you recovering the viscosity after this process? Because you have decided a certain viscosity that you wanted and designed the mix for that viscosity. After this process, are you still having that viscosity? If you're significantly losing the viscosity, you have a problem, right? So here is how the results will look like. So here is your initial viscosity, you extrude it, and then you go back at rest. It's recovered all of that viscosity at a low shear rate. You've recovered those viscosity, which is because at high shear rate, you have really no low viscosity. Shear thinning, remember? You have a shear thinning material. So at high shear rates, the viscosity is very low. It's just flowing nicely. And then you put it at rest, the viscosity is recovered. So most of it is recovered. You see that? You had about 95% of the viscosity. Notice that this is logarithmic axis, but you have 95% of your viscosity recovered. That's a reasonably good one. Again, here also, your viscosity is recovered. That's one test. Again, a nice qualitative test for you to say what will work or what will not. This is for printed foams, very similar idea. Okay, so what are the implications? High shear rate that simulates extrusion reduces the viscosity by several orders of magnitude, enabling the flow through the extruder. Right? Flow requires low viscosity. High shear rate enables that flow. Further imposition of a very low shear rate reorganizes the particle structure flux, but impedes the complete recovery of viscosity because you're still mixing at a very slow rate. So it's not complete rest, but you're getting there. And theoretically, a material can be considered to maintain its shape if it recovers its initial viscosity after the extrusion process. That's what you want, right? After you extrude through, your screw extrudes your mixture, it comes out through, it has to come out shape stable. If that happens, you can say that this is a shape stable material. Viscosity recovery rate greater than 95%, appropriate build generally indicates appropriate buildability. That's what you do. Now, you need structuration. Here is how we use thixotropy here. You need each extruded layer to maintain its shape under super. It's not enough that you just put one layer and that layer stays like that. The next layer has to come on top of it. And when does the next layer have to come on top of it? Pretty quickly, depending on how quickly you want the structure to be built up, right? If you don't want to build a single story, it takes 6 months to build a single story structure, you pretty much have, at least a couple of feet built up during a day, or 3-4 feet built up during a day, depending on what your design is. So you want this next layer to come on top immediately or very quickly. And as these layers progressively develop strength and stiffness, how these properties are developed becomes important to understand. How do you design your printing rate, right? Then only you will know. The extruded layer, how quickly can it take the next layer will tell you when my printer can come back to this location again. How much time do I have? Lots of time this is done through trial and error. You do it several times. Now we are trying to put in some math behind it so that you can reduce the number of trials. Again, the entire idea is not to give you a foolproof methodology where you can close your eyes and print tomorrow. This is only a process flow chart. Like doctors will say, eat well, exercise well, don't drink, don't smoke, do all of that so that you will live longer. Is there any guarantee for that? No, right? You might do all of these and you might not. So, but can you go and blame the doctor? No. So these are all general knowledge that we know. We have to do it. And these are all processes to follow. When a process fails, you can come and ask why my process fails. Now, if all of us do all the things that doctor says, eat well, exercise well, do all of that, and if all of us get sick, now we can go and ask the doctor, looks like you're wrong. You don't have the right idea, right? But if 2 or 3 of us randomly go, you can't really question. So the process is what it is. What I'm saying is that you might follow all of this and you might still fail. That's part of it. you have to correct the process and go. But if you're consistently failing by following the process, you should understand that your process is wrong and you should fix the process rather than saying that none of this works. Because it works, people have done it, you've shown this, right? But this is only setting up that right process. So as it develops strength and stiffness over time, you have to see how the printing paths change. What are the deposition rates? What's my printing rate? What's my speed? What's my nozzle speed? I can't decide my nozzle speed on my own. My printer has to support that as well. Printer has to be able to do that. And I need to be able to deliver enough material consistently, retain the shape, do all of that in a way that is consistent. So structuration refers to the development of mechanical strength in the material over time. Remember, thixotropy is the ability to regain the properties. Structuration is a big brother of thixotropy, which quantifies how mechanical properties develop over time. Thixotropy simply tells you, have you recovered your viscosity? Have I got my static yield strength enough to do it? Structuration tells you, has the structure developed enough mechanical strength to take the next guy sitting on top of me? Clear? So again, two related terms in the broader sense, but in terms of doing the calculations, different, because one is directly relating to the stiffness or strength that is in the structure. Now, you can go back and trace all of it to the interactions between the particles and the hydration and the reaction of particles. At the end of the day, that's where everything converges to. But for the time being, we would just ignore that part, knowing that you're all hydration experts. We would not get there. So it's a critical time-dependent property that allows each extruded layer to support the weight of subsequent layers, essential for ensuring buildability. You see that how structuration now is related to buildability? Only if you have structuration in the layers can you ensure buildability. And buildability also is a very fluid term, because for me, if I'm building a little toy thing in the lab, 4 layers of buildability may be enough. Whereas if I'm building a house, I may need to have 4 layers of 5 mm thickness versus 20 layers of 20 mm thickness. That's where the difference is, right? So you have buildability is a very qualitative thing depending on your application and your printer and all of that. So static yield stress, under a constant shear rate, the shear stress of the paste progressively develops to a maximum value with time. So when you do a constant shear rate with time, you get to a maximum value, after which it reduces to an equilibrium value. The peak shear stress is a static yield stress, which is a minimum shear stress required for the material to transition from rest to flow, reflecting the internal structural strength. Whatever is the internal structural strength required to transition from rest to flow. So this is some examples of static strength. You can use the that's growth hydrates. I'll skip that. I'll show you here. This is time. This is how much of shear time in seconds you have done. And at different time, you see the shear stress evolving, right? So static yield stress is measured at regular intervals. Pastes are pre-sheared at high shear rates for some time to homogenize. Static yield stress and a constant shear rate is applied for a small time. And then you find out what that, all of you see those peak values in all of these cases here? That's the static yield stress at each of those times. And you find the static yield stress that allows tracking up of the structural buildup. So now we are doing it with time. Now there is a question. How much time will my rheometer allow me to measure this? Right? Depends on the capacity, the torque limit of your rheometer. So if you do a rheometer that has slower torque limit, you might say that, you know what, at 15 minutes, all my calculations are ended. After 15 minutes, don't ask me what it is in my printing. You go find out on your own, extrapolate. But then you need the rheometer to tell you at least to a time where you can think you will print a mix. I mixed it. Do I need an hour to print it? Can I do an hour, 90 minutes worth of measurements? You need to have, again, that's again measurement related uncertainties. How much of time do I have to measure? The static yield stress, actually, if I really have, like I said, remember, rheology, even rocks flow, even rocks move. So if I really have an infinite torque capacity, I can keep on measuring static yield stress even after this thing apparently has set or hardened. Right? But I don't want to do that. I want to do it until at least I'm able to extrude and a time at which reasonable buildup of strength happens. So this is one way of doing it. Now, where does it come from if you're interested? Combination of colloidal interactions. All of these are flocks or colloids or cement particles are all coming together as colloidal grains. Particles flock together and the particles bridge by formation of reaction products. So that's where all of these static yield stress is coming. Again, like I said, particle bridging is a function of how far away the particles are. How far away the particles are a function of? Function of packing density of particles. Packing density is a function of particle size and size distribution. Now you go back and trace it all the way back to what we talked in the morning. All of this is just one big interconnected family, just that the relatives don't know each other at different points of time. There's long lost cousins. But you go back and trace your origins to pretty much the same place. Flocculation lasts only a very short time after mixing, after which structural buildup is dominated by formation of reaction products. If you have done any course on cement hydration, you would know that flocculation is very early. The once the reaction and reaction products form up, it is structural buildup after that. Okay, so here is again, you can use now this is a good way to document it. Your static yield stress as a function of time will be a curve like that. You can model that curve as a constant plus a thixotropic factor times some classic times a rust time, a characteristic time, etc. And this A thix is called the structuration parameter. This is related to short-term thixotropy and early age structuration rate. So this parameter is related to the early age structuration rate. So as soon as I have a mix, if I print, if the structuration rate is high, I can come back and put the next layer faster. If the structuration rate is very low, I may have to do more time. So in the real practical world, once you know the structuration rate, it will give you indications as to how you can plan the printing path. Print path planning is also an important thing that people that print multiple structures, larger perimeter structures really think about. If you're doing a house and all with several walls, you think about which wall, what path to take to come back, and that's a function of structuration rate. How much time would you like to spend between point A and point A when the printed nozzle comes back to that location? So this is a good way to do that. And then suggest the potential for rapid qualification of binders, streamlining the evaluation process. Again, the idea is that you have to have some baseline to see which mix I can print, which mix I can't, which one I want to make changes in. All right, so this is all about rotational rheology. I will stop here for a minute before we get into same ideas with oscillatory rheology, a little more intuitive ideas on structuration and strength development. Questions? Is a lunge or the topic or both?
Living lunch.
Only the lunge, yeah, I know. Can only be lunge. We should have starving courses now. Everybody good with these basic ideas? Again, you can all notes will be available for you. So you can, but again, the fundamental idea is that these are all connected. These are all several different rheological parameters. You may not have to measure everything for all the projects, all the works, right? You need to know which one you want for what application. That is something that you have to do it. To your question on how do I know buildup. So one of the methodologies that I have seen is some non-destructive testing using ultrasonics. using ultrasonic scanning is one of the things that they have evaluated the structuration rate so that they know how quickly they can build up. There's a handheld ultrasonic scanning thing that I don't think it's accurate. It's as accurate as your contact ultrasonic sensing. This is non-contact sensing, so it'll be a little less one. But I have seen Icon guys, not Icon, Cobot guys use it for build-up rate and say that, and they say that they haven't. So I asked them if they have published it. They haven't. It's all their internal stuff, but they use it to determine the whole idea of printing path. When can I come back idea? So they say that this mix can come back because they use aggregates too now. It's important for them to do it very quickly and rapidly. So they do use non-contact ultrasonics. One way of doing it. I'm sure there are other ways people are looking at too. Other questions? I think it should be made mandatory that everyone should have asked at least one question before you get the certificate, right? Or you can have pre-planted questions. All right. How much time do we have? You said 3:30, right? 45 minutes. So let's do a 5-minute. I need my throat break. 5 minutes. Yeah, that's all I need. I need only half an hour. If you don't ask questions, we'll go even faster. We can finish in 15 minutes and have coffee. Well, I've given you too much of incentive now not to ask questions.
So, can you explain the influence of aggregate skeleton on structure?
Influence of aggregate skeleton on structuration. So structuration, if you look at the way we define it, it is a mechanical property development because of the reaction and network formation in the cement paste, right? So it's a strength indicator at that point. You can't really bring in aggregates there. But I'll show you the way to bring in aggregates is to look at storage modulus. Because aggregates, you can easily use, you have seen all these equations that you've used to find the elastic modulus, whether you can use parallel model, series model, bunch of models using volume fractions, right? So with aggregates and elastic modulus, it generally becomes a really easy volume fraction problem, even though it's not exactly like that. So if you look at volume fraction of aggregates and elastic modulus, if you look at say a parallel model where you say E is equal to E1 V1 plus E2 V2, right? If you do this, you will get something like this. Or if you do 1 over E is V1 over E1 plus V2 over E2, you will get something like this. But the actual data lies somewhere in between, right? But that's okay. You get indicators using either of these models, using volume fractions and the elastic modulus of the individual phases, you get some indication of the composite stiffness. So stiffness, you can't use this for strength, right? You would never use volume fractions for strength. But stiffness, this can be used. Therefore, you don't use yield stress because yield stress or static yield stress is a stress parameter. You don't use a stress parameter, but you can definitely use a stiffness parameter. So using oscillatory rheology, if you find the storage modulus, then you can use G prime and your volume fraction of aggregates to come up with what will be the influence of aggregates on structuration rate. Don't use it with static yield stress, use it with storage modulus. Same measurement, very similar measurement, but you can do it very easily. And that is why I keep saying that aggregates is a scaling problem if you to use the right measurement. But if you use yield stress and try to scale, you'll be all over the place. You will never get it. But with storage modulus, it'll be a nice scaling problem to use. Storage modulus. Hmm? Yeah, stiffness is so storage modulus is the so if you look at um, complex modulus is your storage modulus plus imaginary part of the loss modulus. So this is storage modulus. So you can either use this alone, or if you're really creative, you can use square root of g prime square plus g double prime square if you are really creative. But the problem with using loss modulus is, you remember yesterday I showed you the transitions. The linear viscoelastic range is where your storage modulus is like this and the loss modulus is like this. Beyond the linear viscoelastic range, your things kind of change. So if you start to do this, you don't have this much of difference because these things are kind of overlapping. You kind of, the balance will go away. But if you just do this, you will see some clear differences and you can keep that. But either way is okay. Really doesn't matter. But it's so easy to just pick this one value and use it, right? All right, ready to go back and do this? Yes.
You mentioned that there is no rebirth. It follows the same path. Like, why does it follow the same path? There is no rebirth.
Did I say it follows the same path back? It should not follow the same path back. It will not follow the same path back. Because if it is so only if it is it has the same structural property as it was going in the up ramp, in the down ramp, will it come to the same point. If it does not have it, it won't. So it should not. Now, if it has not changed at all, you are getting a material that has no structural change at any shear rate. It'll follow the same curve. Like your elastic modulus, your spring that is extended coming back the same way, right? If there is no structural change, it will come back the same way. The changes are because of structural changes. That happens because of your shear rate differences that you're imposing. Right? So it should not come back. So sorry if I said that it'll go to the same point. No, it should not go to the same point.
Also, like, alternative materials or any cases like that can be higher. The second round can be higher than the initial one.
I don't know. Have you seen something?
So, yeah, and I think basically it's about
What are they? Yeah.
that the material is not completely broken down. That makes it better.
No, but you remember we looked at one paper where you were trying to write that paper on cement pay on shear rates, right?
Like,
Carbon blacks, yeah. So yeah, you can have antithixotropy also, but that's not what we are talking about. We don't want that. Other questions? All right, so we'll get into oscillatory rheology, or the idea of evaluating storage modulus. Yesterday, we talked about applying a small oscillatory amplitude, right? A sine wave function at a very small frequency so that you are not damaging the structure of the material. You are just evaluating the material as it is. That's why oscillators, so small perturbations in strains or stresses. You can do shear stress sweep, strain sweep, or frequency sweep. All the examples I showed you was stress sweep. You're sweeping from 0.1 Pascal to 1000 Pascal or whatever that range of stresses is at very small frequencies, very small amplitudes. You can do the strains from 0.01 to 10%, 100%, 1000% strain at very small values. So you're not doing any breakdown, any structural damage. So a few conclusions that we have seen from our work. Higher storage modulus enables the printer layers to better retain stability and carry on superimposed layers. Should not be a surprise. Higher stiffness, you can carry more load. That's what your structural mechanics have told you all the time. Lower value of phase angle represents a more solid or elastic behavior. So phase angle is the ratio between G double prime and G prime, which is called the tan delta. That's your delta is your phase angle. So lower value of phase angle, lower value of tan delta represents a more solid or elastic behavior? Yeah, because this has to be lower, meaning this has to be lower. The loss component has to be lower, which means it's more solid, right? So again, it comes directly out of that equation. Critical strain, which signifies the end of linear viscoelastic regime. If you remember yesterday, you have the curves going like this, correct? This is your linear viscoelastic range. This is your solid-like behavior. The end of this plateau range is your critical strain that you can kind of indicate as the strain, that is the deformation capacity of the specimen. So at what strain would you deform, which is an indication of how much load you can carry before it strains too much. So critical strain can be used for that, because when the critical strain is higher, means interparticle connections are much stronger and there is more bridges. Critical strain is lower, the solid will tend to become a fluid, tend to move and deform much faster. So you can use oscillatory rheology as some indicators for material delivery, extrusion, layer buildup, and all of that. Here are a bunch of examples where graphene was used in 3D printed concrete. You can use storage and loss storage modulus, G prime, and the G double prime values here. The phase angle goes down as the material becomes more and more solid. So adding more and more graphene gets more rigidity to the structure. Phase angle goes down. Critical strain goes up because material behaves more solid. So again, all these parameters telling you roughly the same thing, but different ways of measuring it. Again, influence of binder composition, different binders, OPC versus fly ash and limestone, different water cement ratios. You will see how the storage modulus and loss modulus changes, phase angle, critical stress, critical strain, all of that. So it's very similar ideas.
Saturation,
Hmm.
we can add slag. Mineral addition, we can add slag.
Yeah. So if structuration is that early development of that network and strength. Once you have it at rest, the building up, right? Whatever does it slag or whatever accelerating admixtures will do it, and that's why sometimes you add this at the end of the nozzle so that it gets quicker. Anything that accelerate hydration, if you pack the particles much better, it'll do the same thing. Slag can react faster and do so. Lots of these materials can do it. So whether it's by particle reorientation mechanisms or by hydration, you can do all of that.
If you add accelerated,
So that's why these 2K systems, right? So you can't add accelerator along with the mix. So as the material comes out of the nozzle, you spray the accelerator.
just spray.
Just spray, yeah, spraying of the accelerators. No more. No, you can't mix anymore, right? When it's coming out of the nozzle, you can only spray. So basically what you're getting is your surface layer being kind of stiff enough to carry it. It's not completely happening because it's only accelerating on the surface. But that's good enough to retain the shape and be able to carry the next layer. Storage modulus evolution with time. So if you do a small strain test, you can do storage modulus as a function of time, and you see how this is only about for 30 minutes, 1800 seconds. I think I have another picture that goes to 180 minutes. You see how storage modulus starts to evolve with time for different types. So this is OPC. Those are the other mixes with other materials in it. But you will see that storage modulus start to increase with time. And that you can see the same kind of equation that I showed earlier for thixotropy. Right? Very similar kind of equation. The only thing is the constants are slightly different. So you can have the storage modulus as a function of time expressed by this equation. So where C is the amplitude of flocculation recovery, which means how much of the structure is recovered with time. Lambda residual is the residual structural factor after pre-shear. But this is the rate of G rigid is a rate of structural buildup due to hydration. So now this will be different depending on what materials you have in the mix. With fly ash or slag or silica fume, this value will be different, and you can find all these constants. You can simply fit this as a function of time. You can get all these constants that will give you an indication of how the storage modulus is evolving with time. Now, once you know how the storage modulus is evolving with time, you can play around with simply the fact that Storage modulus of paste is what you have determined, or mortar if you did the mortar test. Any inclusion is nothing but inclusion modulus added to the equation. And you can do that and get the values. Again, flocculation recovery after pre-shear, structural buildup due to hydration. So higher value of C means flocks are capable of recovering faster after imposed pre-shear. Higher lambda value indicates a more interconnected structure. Faster buildup results in lower theta. Higher value of G indicates a faster structural buildup due to hydration. So all of this again as indicators as to how your structure builds up. Another example of storage modulus buildup, all the values that you see. And then this is your till 30 minutes. If you have a rheometer capable of shearing a paste even beyond 30 minutes, right? Or if you cheat the system by dropping the water cement ratio or increasing the water cement ratio and make the mix work for a longer time, you can do whatever you want. You can do this for much longer. So here we cheated it from 0.3. It was only getting up to 30 minutes and the machine said, I can't do this afterwards. So you do a 0.45 so that the mix remains fluid and the system can measure for longer time. You get storage modulus as a function of time. And you can see here from 30 minutes to 3 hours, your storage modulus increases by more than 2 orders of magnitude. Very quick structuration rate, right? Which means what? How much you can carry at 30 minutes versus how much you can carry at 3 hours is much higher. So in that 2-hour gap, so you don't have to wait till the next day. In that little 2-hour gap, you have 2 orders of magnitude increase, which means you can actually play the system really well to find out when you can start building up. So this is an advantage of understanding storage modulus evolution. And then this is something that we have done where we're looking at oscillatory rheology as one test that can do top to bottom of everything. So you can do storage modulus can tell you indicators about dynamic yield stress. It can tell you plastic viscosity. It can give you indicators of static yield stress. It can give you hysteresis or thixotropy. It can give you structuration. Again, within all of this, we'll have to take with a grain of salt. Within the range of parameters, we are trying to see if there is one test. To your question again, if there's one test that rather than doing all of those, I don't know if it is certain, but I think at this point, I believe that oscillatory rheology is something that can cover a lot of bases with respect to understanding how a mix will behave. Again, there might be other tests. I'm sure there will be other tests. There will be other ways of doing it, but at least in a very nascent field, rather than measuring 200 different parameters, if there is one test that I can do to do early age meaning immediately after mixing, and to find some indicators of buildability, at least oscillatory test is one of the mechanisms that you can use. Not by itself, but by doing time-dependent oscillatory rheology and getting some storage modulus evolution, all of that. So generally, some indication of what it is. Now, we have done some really interesting work on rheology hydration link and how do we do that. So, and how do we actually measure it? So we brought in one more test, which is an easier test to measure. So you do rheology, you get all the rheological parameters, you get hydration. Hydration and rheology are connected for all the reasons that we talked about earlier. Rheology is about particle linkages, particle connections. Hydration happens much more when the particles are connected more, and when the particles have started to develop the interconnected network and hydration proceeds, rheological characteristics go down. So you can really get a good relationship between rheology and hydration. So if you look at storage modulus as a function of time, you will get a curve like this. And if you look at storage modulus as a function of cumulative heat at that time, you will get a curve like that. They look fairly similar if you have a decent enough eye to look at it, right? So you have storage modulus as time versus storage modulus versus cumulative heat. So cumulative heat maybe some way to measure it. So if you look at doing it, so here is your induction period, right? Nothing is happening. And this is all dissolution, so we really don't bother too much about dissolution. That's anyway happening. Acceleration is where you actually start to produce your hydration products, and your initial set is somewhere at the early part of your acceleration curve in your hydration curve, if you know that. So if I do that, so that's your heat release, that's my cumulative heat. And then if I subtract my heat at the onset of acceleration, and then here is my G prime plotted as time, and then here is G prime over G prime naught, some randomized normalized value and a normalized heat, they fall along a straight line, right? So this is the idea that you can relate rheology and hydration. You can obtain indicators of rheological measurements from hydration or vice versa. What we did is went in one step further and said, both these measurements are difficult. Even hydration with an isothermal calorimeter and doing all of that, putting all of this, rheology, putting the paste in the rheology is different. Can I do something even more easily? And one of the easier measurements to make is an electrical measurement, just to measure electrical conductivity. So the question is, can electrical conductivity tell us indicators of rheology and hydration, including storage modulus? So what happens? Here is how it is happening. It's just a schematic curve. That's your hydration curve. So the dissolution, induction period, and acceleration. So here is where acceleration starts. Here is your storage modulus evolution, almost nothing until acceleration starts. Remember, storage modulus also is network has to build up, acceleration has to happen. So that also happens in the acceleration range. And here, look at electrical conductivity. You have initial conductivity increase because all the ions are dissolving in the solution, but then the conductivity starts to suddenly drop when the reactions and the acceleration start to happen. Everything has some kind of a fluctuation in that acceleration window. So if I can pick up rheological changes and hydration changes and easily measure conductivity, hey, maybe conductivity is a quick and dirty measure to figure out how rheology and acceleration changes. And unsurprisingly, actual results also are like that. So here is your heat flow curve for OPC and some other mixes. And here is your electrical conductivity that changes with time. Here is your heat flow for another set of mixes. Here's your storage modulus as a function of heat, total heat minus heat at acceleration. So just at the onset of acceleration. And that, look at storage modulus versus conductivity minus conductivity at the acceleration state. So this and this are extremely identical, and I can plot it fairly consistently. So cross property estimations is something that's a very interesting field, so that you measure one and you infer so many other things from it. Interesting way to see. So the reason why electrical conductivity is very appealing is that there are a lot of applications for which conductivity is used already. So for durability, one of rapid chloride permeability, all of you use RCP method for durability, right? Rapid chloride permeability is nothing but a conductivity method. It's a glorified conductivity method, which makes things actually worse and wrong, in fact, by putting in very high voltage and things like that, right? So RCP is an actual conductivity method. And in the US, we have gone away from RCP method. Now we simply do, why waste 6 hours and 60 volt of potential? Don't bother, just take a DC measurement, a 2-point or a 4-point DC measurement instantaneously and move on with life. That's good enough. And they are now relating that to all durability parameters. There's an even ASTM standard for electrical conductivity based measurements of durability. So electrical conductivity can do durability very well. There is a whole sort of studies where electrical conductivity is linked to hydration, kinetics, growth of products, all of that. There are sensors, electrical conductivity sensors that have come in to measure hydration, simply looking at changes in conductivity over a period of time. So it's not impossible that if you are interested, if you have enough sensors, it's not impossible to actually track buildability and extrudability through electrical conductivity. That'll be a very interesting thing. I want to do it, but I'm too bored and busy with doing other things. So I haven't been able to do it. But that'll be an interesting work to do if you can measure, because once you track rheology, which you can, once you track hydration, which you can, there is no reason why extrudability and buildability cannot be inferred from conductivity measurements. Maybe not simple conductivity, but maybe some impedance kind of measurements. Maybe using, there's no way that you cannot. That's my feeling. I haven't really done it, but I will have to do it at some point of time when my students are happy enough to do more work. But this is something that is probably from a testing point of view, from a quick quality control point of view, because electrical conductivity, electrical impedance measurements are becoming quality control tools very fast, and it's very cheap too, or reasonably cheap too. So that's one place to go. You said 3:30, right? It's only 3:15, so we have enough time for questions. I think I have. So here is a recap. Everything that we have done so far in one slide. If you have been dreaming so far, at least you will hear the highlights. So a lot of rheological tests we have talked about, right? Today's quiz has all of this, right? All the rheology tests in this quiz. So we'll know if you have paid attention. So a host of rheological tests to cater to specific performance aspects. So let me do a quick quiz before a quiz because we have time.
Just you don't have to test big.
Yeah. We will give you all of those. Don't worry, we'll give you. So by the time this whole thing is done, you have all the notes, right? It's just PDF. You can make it into PDF, and everybody will have access to all.
So you should have access.
Yeah. So don't worry, you have access to all of this. If you want to keep notes and take notes of important points, it's always useful, but don't have to take screenshots. You will have all of this for you. Right. So host of rheological tests for specific performance aspect. So can somebody tell me what all rheological performance measures we did from yesterday until now? We did a lot of it. And no answer to this question will be, I'll have to leave today. What are some of the rheological tests that we did, or performance measures that we looked at? Yield stress. How many yield stresses? 2. Why static? What will static tell you? Gives you an indication of structuration from rest. So it's a buildability characteristic. What will dynamic tell you? The ability to flow or the onset of flow. Okay, so 2 yield stresses. Great, everybody remembers that. What's next? Viscosity. What will viscosity tell you? Ease with which something will flow, right? You can quantify how quickly, how fast, how well something will flow. So 1 viscosity, 2 yield stresses. What else? Storage modulus. What will storage modulus tell you? The structuration, the rate of development of properties with time. Okay, what else? Loss modulus will tell you the fluidity or the opposite property, the damping property of the material, or the energy absorption property, or the softness of the material. Not much use though. Phase angle or tan delta, the ratio of loss to storage, will tell you again how quickly the structure is developing or not. What else? Thixotropy. I forgot that. What will thixotropy tell you? The ability to regain, break and regain, right? Rebuilding kinetics. What else? And thixotropy can be connected to yield stress as well, because you can use it through yield stress. What else? That's it. Structuration rate, which is again how quickly the strength will develop, which can be related to storage modulus as well. So those are all the general rheological characteristics that we talked about. Because now we are going to, so all of this is You can think about 3D printing or not think about 3D printing. If you think about concrete rheology, all of these are important, right? With 3D printing, we kind of related why these are important with respect to layer building kinetics. Now, in the next set, probably tomorrow morning, we are going to look at how extrusion process itself. And remember, I told you all that we talked about are of materials. This has to be connected to what are the two other things? Printer characteristics and process characteristics. I don't know printer characteristics. I have no idea what the printer characteristics are, but I can make some informed decisions about, well, this will be the nozzle, this will be the kind of pressure that the printer will exert in getting the material out. I can do some kind of generic stuff, right? So with respect to the printer, I will simply think about what I call an extrusion pressure. No matter how the extrusion pressure is applied, I will simply talk about an extrusion pressure. Once the material that has put in the extruder has to come out, whether you're shearing it with a screw, pushing it with a ram, pumping with oil, or you're blowing on your own energy, it has to come out, right? We will simply call that an extrusion pressure. And we'll use the most simplistic method to quantify that extrusion pressure so that we understand what that mechanics is. With respect to printing parameters, we will look at the printing speed, how fast you are printing, the layer build-up rate, how quickly you want to build up the layers. And then as process parameters, we will look at layer heights also, layer widths and layer heights, layer geometry. That is for tomorrow morning. Right? So right now you have a good handle on all these parameters. Now we will put all of those in a jar, blend together, and then put it through an extruder and get extrusion pressure, velocity, again, pressure velocity relationship. So we'll go through some very basic physics that I'm sure you've forgotten or you didn't want to see. We'll see some of those. I'll show you some very common equations that are used in traditional fields of extrusion, whether it's polymer extrusion or clay extrusion. Some of the very classic equations that relate pressure to flow. Right now we're talking about pressure. So far, pressure was some kind of, yeah, I need pressure to get this out, but in my rheology, in my obsession with yield stresses, I forgot about all of that, right? Now I'm actually going to introduce the idea of how do I exert a pressure? How do I get this thing out? How do I print this? And what are the parameters that are important? There also, it is important that what we are going to see are guidelines and broader parameters. It will change with specific extrusion pressure applied by a specific printer in a specific environment using a specific mix, right? If this is not there, none of us will have jobs. So we should be thankful for the complexity that concrete offers us. This is what I'll tell my first class on concrete. You should be thankful for the complexity. It'll be hard to study the class. It'll be difficult. Why are we dealing with a complex material? You should be thankful because that's giving us jobs. That's keeping us gainfully employed. That's why there are problems. People don't understand why things are failing, why things are cracking. We all will have jobs, right? So it is a complex system, but we'll try to make it simple to go through that process. But again, keep in mind that if you consider this entire topic as walking up to the top of Himalayas, or if you're doing an Everest climb or whatever, all we are doing at this end of the week is telling you that eventually you have to get to 25,000 feet. At 10,000 feet, there is a base camp. You might get water and some refreshing stuff there. And right now, once this week is done, you might get some Sherpas to help. That's all we are doing. Nothing more than that. Okay. So if you think that we are in the Everest, well, you both of us are there. We are there. If we are useful or not, they'll have to decide if the Sherpas are useful. But that's all we are doing, right? The field is vast. There is explorations that all of us have to do on our own. On that note, if you have any more questions, I'll take. If not,
So
yes.
when you talk about this electrical resistivity measurement, so how would we correlate the resistivity with the hydration? Like there were some peaks in the qualitative
Which peak are you talking about? Let me show you.
What is the
Oh, okay. So this is your electrical conductivity. So as you start measuring electrical, as you mix cement and water, instantly the conductivity slowly goes up because ions from cement are coming into the solution. So the solution is becoming more and more conductive. The conductivity keeps going up, right? But then when the induction period is done, when the acceleration period starts, that is when the cement grains are starting to hydrate, the hydration products are starting to form bridges. That is now breaking the connected channels that goes and increases the conductivity. At that point, the conductivity starts to come down. So this is where conductivity starts to come down after your reaction products have started to form. Similarly, same corresponding to that same, because the reaction products have started to form, your modulus have started to go up. That's what you see in the bottom line. And because your reaction is happening, your heat is also increasing. Until then, that's the induction period where nothing happens because of the effect of gypsum that you add in cement. And then you have your induction period. Okay. Other questions?
So is more of a DC based used or is it impedance spectroscopy?
No, this is impedance spectroscopy, and we took the bulk resistance from the arc. Generally, bulk resistance corresponds to, in lots of cement-based work that we have done, bulk resistance corresponds to about 100 hertz DC, 100 hertz measurement, and it's a direct DC measurement. So
100 hertz frequency.
yeah, the RB, the bulk resistance is about 100 hertz frequency, generally.
We thought of doing kilohertz resonance thing where we are like finding it difficult to like getting a field transition, whether it is electric interface.
But you can do, if you do impedance, you will get it, right? Because if you do in impedance, you actually will get, you will get the bulk arc and the electrode arc, and this is your RB value. And once your RB value, you can simply call that as a resistance and calculate it.
But again, the value kind of shifting.
Ratio will keep going this way. Yeah. So that, and so you will keep taking this value, but the frequency that this appears generally doesn't change.
So
Generally, I mean, there might be some changes.
actually this is
Yeah, this is the electrode arc, right? So this is the bulk arc. That's the electrode arc, right? So you want to maximize whatever you get here. I mean, even if that's not the case, it's okay. Even if you get an arc like this, that's okay. You can get that value. The reason why you can't do too much of analysis if you get this is because you don't know where the center of this imaginary circle lies, and that is where you want to have the calculation for the phase angle. So your phase angle calculations will be wrong if you don't know where that is, and that's where extrapolation becomes difficult if you don't have a good part of the arc. So they say at least want a semicircle, but it's hard to get that unless you have, because you know that, right? Your frequency is increasing as you come here and here. If you have only a megahertz, you will only get here. By the time you get here, it's in the gigahertz range. It's difficult to measure.
So is it like we have used an embedded kind of
Embedded electrodes, yeah, because to get good value. Conclusions, further complicating decision making. This happens all the time. When we have all the toys, you don't know which toy to use, right? And then you get confused. So it's important to stick to a certain way. So way forward, different parameters mesh provide valuable insights. Small amplitude oscillatory test or the oscillatory rheology that I told you allows continuous monitoring. So it's good. To fully validate any approach, you need lots of data. We don't have that much of experimental data. Standardization of test protocols is very time consuming, but doing that would be highly advantageous for the industry, paving the way for more reliable standards. Again, all of these are are things that we have to do it. And if many of you are working in this area, you guys are doing it, collectively, we will get to some place at some point of time. That's the whole idea. So, basic rheology, we have concluded. Tomorrow we'll do this not very common field. Now with 3D printing, people are doing it, but in concrete, nobody ever talked about it, which is extrusion rheology. We'll spend an hour tomorrow morning on that to link, again, generally all these different parameters. Good? All right. If no questions, we will break for coffee.
Okay. Good afternoon, everyone. I am Avinath Tripathi. I am a postdoc as assistant research scientist at Arizona State University. I did my PhD from Arizona State University too, under the guidance of Professor Narayan Naithilath. I'll be like in this one, I'll be jumping between slides and app and this and that. It will be a, I hope it's not as big of a mess, but again, I'll try to do it as easily as possible so that everyone understands. We'll not talk about much in terms of like what packing is, what aggregate gradation does, because again, from the morning, I think the maximum thing you have seen till at least lunchtime is like packing, packing, packing. Aggregates gradation, good gradation gives you good packing. You require less space, you require less water. What I'm gonna show you is like again, it's not gonna be that much of a detail, but it's like we are developing this app. This the things that I show you today will help you use this app in future if you need it. Because again, there's few things that you have to learn, like how to use, like how to create the input files and all those things. I'll show you where the apps are at. I think like we send a email out to everyone to download. I know like some people were saying it's taking a lot of time to install some of the apps. I'm not an app developer, so whatever I could do my best, I tried. So in future, if I can, I'll try to optimize the installation time for those two. So to get started with, again, the importance of packing in rheology, and as I do 3D printing a lot, it does have a lot of importance in 3D printing itself. Like a certain mix where I'll show you later on, like I'll show you two different mixes that we print. One is a complete cement based mix that we print at zero point 0.4 water to binder ratio for that, and L30 mix, like a 30% limestone mix, which we print at 0.35 water cement ratio only, water binder ratio only. Again, this all goes down to like the packing, the actual gradations of particles that are present in the system. So it basically changes the amount of water required also. All those like packing density, the graph you saw, like there are certain particle size distribution which you use, you will get a very maximum packing density. After that, it again comes down. I'll not talk about basically optimizing. I'll show you slight things with aggregates, how selection of different particle size does to the fraction to be higher than selecting a very random larger particles. So to start with, the main software will be this. I hope everyone has downloaded it. Sorry that we don't have this for Mac users, because Mac requires us to be a actual professional developer to actually give you out an app, which we are not. So we don't have this for Mac, but we have it for Windows. Again, in Windows also, like you can Mac also, you can download Windows as a separate part and you can use it if you want, or you can use a Windows PC. Hopefully, most people do have Windows. So if you have already gotten the app, I don't know if you have extracted it, but I'm just gonna show you if somebody has not done. I'm just gonna go quickly over it if somebody's stuck in the downloading part. Okay. So because it's in Google Drive, you just have to give it a access saying that it does not have virus. We can nearly 95% guarantee it does not have virus because we developed everything in our place. So it should not have any virus. Just do download anyway. Once you get the download, once you extract all, you'll see inside the folder, you'll see this hydration desktop.exe. You don't have to install this. You directly get this. This is going to be one of the software. Like this is what you are going to be using here. Again, when you run it, Windows protects it because again, we are not registered developers. So they think that it's a malicious software. You don't should not run. Just click more info and you should get run anyway as an option. I hope nobody's having problem till this point, right? So this is the software interface. The things that will have in future is that I had this highlighted. Oh, I think I had this highlighted here. But like we have three different menus. The build MS is the one that generates the microstructure.
The second one, that's the distribute MS, is once the microstructure is generated. This again, I was talking outside also. We plan to develop this as a microstructure generation and then use it for cement hydration. So, is there an issue? Mm, are you guys having trouble to install or something? No, right? Okay. So once we develop the microstructure, again, the way you see, right, the particles are there, waters are on the pores, so these waters hydrate the cement particles, so you can actually simulate hydration in cement. Right now the app, this part is still under development because for some weird reason the distribute ms is not giving us the output file. We have to go back to and check the code, because what it does is, like, once you have the microstructure, distribute ms basically separates out your all the phases inside even each particle, so that actually the hydration phenomenon, the actual chemical reaction that we are giving it to it, like water is touching the particle, right? So it should hydrate a certain way. For cement it should hydrate a certain way. For fly ash, for limestone it should be slightly different. So those kind of things this distribute ms does, but again we are not getting any output from this file, so we will only stick with build ms for today. So for build ms, if you see, there's a choose.dat file. So that's where it goes down to, like, again you will have to type in all the values. So we try to rather make it as an input file, where instead of typing each time you can actually generate it. And we have, like, I'll show you how you generate an input file. But what this that file takes is actually the particle size distribution of different particles. Like, let's say you have OPC in the cement in the system, then you will have the particle sizes of OPC, and you'll have like certain radius particles, this many numbers, based on how much volume percentage of each size is there, depending on the PSD. Like for different, like you will have to discretize this into certain particle size and the volume percentage. You should understand that this is cumulative, while this is not cumulative. This is just between two particle sizes. We are saying, like, if you had a 0.159 sieve and 178 sieve, 159 will retain 0.03 percentage of the total, while 0.178 will retain 0.04 percentage. I'll show you down the line also, like there is a list of shifts we have for most of the things. We have few of them already done, and we have like them defined in the system. So it's basically define the proportion. Now the next thing goes to, like, defining the proportion of the mix. Like, what do you have in the mix? Do you have 70% cement, 30% limestone, or you have 100% cement? Because that basically determines how many different kinds of material you have. Again, that will come into picture later on, because we distinguish each particle as a material. We will distinguish cement to be cement, limestone to be limestone. For particle packing, it does not matter for us to distinguish between those particles. But if we have to use it further in hydration, we need to know which particle is what, because we can't ask limestone to hydrate like cement particles. So for those reasons, we have it distinguished in the system. So again, as a general start, we'll see it in terms of the distinguished particles, so that later on, if it develops further and when we have the hydration, at least you guys know how to reach to the microstructure and basically start the hydration scheme. And the other component is like water cement ratio. This again, you can go get away with not defining a water to binder ratio, because again, if you want to just do packing, it's fine. You can just use the particles and select higher packing fraction till you reach a certain position where the software is gonna say, like, I can't distribute this pairs now, meaning like you are like at the limit of heterogeneous mixing. Like basically, it's a random seeding of particle that it does on a certain volume. So the software will say at a point that, okay, I can't distribute this pair, meaning like there's no space for the pair to be distributed. So that's what the maximum packing you most probably will end up getting. So if you have a water binder ratio, I'll show you in terms of water binder ratio how we calculate all these values in the next slides, because pores are required. Like now you can't have a maximum saying, like, let's say you have 40% is water, then you can't go to a solid volume fraction of 70. That's that 40% you need for water also. Again, there are air voids, different things that get basically when you mix, air voids do form. Again, if you want to account for that, again, you will have to put 40 plus the air voids percent and basically select the rest as a solid fraction. Now, again, it does not matter for the distribution, but it will matter later on when you do hydration, because you want to have as exact of a microstructure as it could be in the system. Because if you have, let's say, 7% porosity, you want to have the system such that there's like 40% for water, 7% for porosity, and the rest for solid. So those kind of things will be defined. Like, again, you as a user will be defining this. So to look at the steps onto what happens and how we do it. So initially we started with the particle size distribution and a volume fraction, right? But because like there will be like 10 to 20 to 50 to 100 different sieve sizes that we can distinguish it to. What we basically do is like we calculate an equivalent volume and we basically shrink everything back down to 2 micron size. Again, you could end up doing like a 2 micron sieve, 4 micron sieve, 6 micron sieve, 8 micron sieve, and actually use the volume percentage as such. But again, it won't be correct that way because let's say you have a 0.02 micron sieve size, right? The volume percentage actually will not be like directly replicated by 2%. So you will have to calculate an equivalent volume. I thought I had the equation there, but again, it's basically like, okay, you have a certain particle size. You are trying to say like, okay, I now want this to be a 2% one. So I'm calculating a volume percentage, equivalent volume percentage, which I have an Excel sheet that I'm gonna kind of try to work with you guys to show that how it actually goes. I'm just giving a brief overview right now, so that when I actually show the Excel sheet, it does not become like, oh, what are we doing? So just to show what goes to the Excel sheet, I'm showing you this. So once we put an equivalent volume for all this, we do a cumulative volume, meaning like anything from 0 to 2 goes to a 2 micron bin, anything from 2 to 4 goes to a 4 micron bin, and so on. We can keep basically do that. And for this, as I said, like this first example that I have in the slide is for a OPC 0.4 water binder ratio mix. That basically that 0.4 water binder is by weight. And when we convert it to volume, it goes to like 0.56% volume of the mix, which means like we have like about 0.44% of the volume remaining. So that's like, if you say you don't want, you want zero porosity, that's the maximum you can go to. So again, I'll talk to you about this later. This will be like a recap when we go to the Excel sheet. There's a selection point where you can assume a particle for volume fraction initially. So for the exercise, this exercise, I started with a 0.44 packing fraction assumption. That's the maximum. I started with this because the end product usually becomes lesser than what we actually assume there. It's either equal or lesser than that. It can't be higher than that. So for this case, when I assumed 0.44, we ended up with, I think it's in the next slide, but with, yeah, I think it's a zero point 0.2 is what we theoretically calculated, and the software does a 70% porosity. But with that, the next thing is to like, now we have volume percentage, right? Equivalent volume percentage. So we can't put equivalent volume percentage. We have to put equivalent number of spheres that take that volume. So calculation procedure is again involved here, where it's nothing else than like the total volume times the packing fraction that you assumed, meaning like you have a 100 meter cube volume, then only 44 meter cube can have solid, which basically is the proportion of the component used. Here it's only OPC, so it's 100%. But let's say if you had OPC and limestone, you have to distribute it between OPC and limestone, right? So that goes into the equation. And then cumulative volume percentage is for the certain size. Now you can do 40 meter cube out of 100 meter cube. But in that 40 meter cube also, the 2 micron cannot take all the 40 meter cube. So 2 micron again needs to have a certain volume percentage. That is like the equivalent volume percentage that we calculated here. That's the maximum volume it can take. So what we do is like we calculate the cumulative volume percentage. And again, this is something that is like a more of an image generation thing, where because you can generate different kinds of image. Here we are selecting a 100 by 100 by 100 pixel image. And the pixel has a volume, like the way you have a volume for your material, the pixelated image also has a volume which is called voxel. So this again, I'm not going to go a lot in detail into the pixel volume, but we have it set up in the Excel sheet right away for the ease of use. So once this is done, you get the number of spheres that you from the Excel sheet. Like these are the numbers of spheres that the software has to try to distribute. So with that, once you have the number of volume, again, because you have now number of spheres, you can calculate the volume. You can calculate theoretically what the packing fraction should be. It always comes out significantly lesser than it actually is. So you see the picture, right? Like you selected a particle volume fraction, you ended up with a theoretical volume fraction, and the software does the distribution and gives you a volume fraction. Like again, I'll show you why it's 70% instead when you selected actually 44. So maximum should have been 56%. Why it goes to 70%? I'll talk to you once I show you the examples. But like for this case, like once we did all this, we saw that the porosity goes to 70%. Means like we most probably have more space to keep more OPC particles in the system. So what we can do is like now we change the assumption to a higher particle fraction. So with trial and error, a point, oh, I think this is wrong, 0.65 is what we selected. For some reason it's 0.4 here. So we said I selected 0.65, which basically gave a theoretical value of 0.3. And when I actually run the model, the microstructure distribution model, we get a 58% porosity, meaning like 56 to 58 is like nearby enough. And I did not go farther than this. Like if I would have selected 0.66, maybe it would have been 57%. But again, you get the picture, right? Like you have the selection criteria. Like you can select the values to end up with what you actually need on this case. So for this, again, these are the calculations for this value. I have these are, I think this is example 1 and example 2 on the example list that I have. So we'll talk about it further in there. But like again, these are the volume fractions, right? If you see repeatedly, I'm giving you in a ascending order, right? But the thing is, the input file takes it in descending order. And descending order itself being like now I'm talking to you in terms of one single particle, OPC. Now, if you have limestone, the descending factor comes for limestone too. Meaning like if you have a 18 micron OPC and 18 micron limestone, you have to select the OPC first, then limestone. Because what the software does is like it randomly sits play points in the voxel to basically have the particle there, meaning like it starts from the largest particle. Because if you have seen there's a very good YouTube Instagram reel kind of video where the professor shows like, oh, you put aggregates, you put sand, and he ends up saying like you always have place for 2 bottles of beer with friends. So that kind of scenario where you actually have to put the larger particle first, so that if you put the smaller particle first, the gap might not be enough for the larger particles to sit in. But usually if you have the larger particle already in, there should be some space for the smaller particle to be distributed. So it starts with the larger particle first and then keeps on distributing the smaller particle. So it goes descending order, not ascending order. So now we have to change the whole thing into descending order. And the other thing is like now is like it has a row input. I'll show you in the next slide. It has like yeah, so this is the kind of input it takes. And this is the file that gives you what to do. But again, we have simplified it further, but it basically requires you to put the radius number of spheres, the radius of spheres, and what material it is. So that needs to go in descending order for all the particles. And again, to distinguish between particles, we have in the system, like, I think I have not made a readme file for this. I should make one readme file where we have each number given for material. Like if you have a material 1, it's cement. In cement also, once you distribute it C3S, we distinguish it as C3S, and 1, 2, 3, 4 basically belongs to cement. 5 belongs to gypsum, 6 is hemihydrate, 7 anhydrate, 8 pozzolanic material, and we have like about, I think, 15 to 20 materials already defined. And obviously we can define more. We can define furthermore. Again, we need to slightly add to. I think one thing that we do not still have is microsilica, which we should define. Neither then we have most of the generic materials defined, like inert materials, aggregates, other like flat aggregates kind of thing also. So these again, like these are basically for the system to know what actually the value is at. I'll show you once I go to the actual Excel sheet. I'll show you 4 different materials that I select for the examples. I'll most probably not go into all 4, but for the sake of, but initially for microstructure, I would say like it does not matter. If you select one for everything also, it will give you the microstructure. Later on, if you want to do the cement hydration model when it is developed, obviously you can't do that just by selecting one, because it will think that the limestone is also cement. So this comes into picture for hydration, while for the microstructure distribution, there's no issue with having all the numbers same. So you see these 3 things, right? We have to have those in sequence. And again, the program itself has few things as like menus to select. Like there's a menu 2 selected for to it to start distributing the spheres. There's a menu 4 selected for it to actually output what the porosity is, what the solute fraction is, and all those parameters. There's another input where I think it's 5, which basically prints all this result into a file. So me trying to tell you all this and somebody trying to understand, it might be very confusing if somebody who developed it already does not tell you. Even with readme, it's going to be slightly confusing. So I'm just gonna not cross up on this that much, but the thing is, like, there's one thing, like how many different types of particles are there. This is very small. I will see the Excel also, so you will have a chance to look at all this again. But like there are 17 different kinds of particles I just defined here, and these you see, like, it's number of spheres, radius of sphere, phase of the sphere, and then again number of sphere, radius of sphere. So it goes on descending order. So now we're trying to ask user to actually create this is an issue, because once you understand it, it's very easy. It does not have much, but there's a high chance of making error, right? So what do? We created an Excel sheet for this also. So I'll most probably jump between this Excel sheet to show you. So this is the first Excel sheet we had, where you have, like, basically if you see, everything is defined on the right, what actually these numbers mean. But again, you have to follow this particular pattern to fill up all the numbers. And again, let's say if you have, like, say, instead of, I think this is defined for 15. Now, if you have 17, you have to add 3 more for 16, 3 more for 17, which again, user has to understand to do that, right? Neither then this will be like somebody who has 17 particle and they can't do it. So this is again something we had. The next thing that we now have, I hope everybody downloaded this. There's a different Excel sheet with the examples sheet. There's 2 Excel sheets within the examples also of the same thing, because I did not want to jump between too many things, so I put that there. So I think I'm just gonna go back to the presentations to show you a few things. Like, the Excel sheet are color coded, meaning that anything green, that is what the user should play around with. Like, a user who wants to actually run a model should only touch the green colored things. Now again, if you select to change the color yourself and it does not remain green, does not mean you don't use those, right? So anything red is something, unless you know what it is doing, it's better you do not touch it. Anything that's green with a background yellow, and this is just for the pixel volume, which again, for the chip size that I have already defined, we have few between chip size that are missing. Like, we don't have, I think we don't have 10, no, we don't have 12, 18, something like those, like the bin size. We have everything in the increment of 2, but there are 2, 4 chip sizes, because when we did it, there's nothing written on it. So we never have the chip sizes on the x-axis. So it never, like, anything between 8 and 10 is not there, then it's not gonna, this Excel sheet is never gonna give you a 10 size, because this is developed such that if you input something that's within 8 and 10 is only when it's going to create 10, because if there's 0% volume, it will just ignore 10. So that way, that's the only place you might have to check. And how to check that is again this, like, we already have the 2 to 50. I think we have from 2 to 50, we already have the pixel volumes in the Excel sheet. So you can just use that pixel volumes. Again, this whole sheet is red because it's not useful unless you have to exchange it to the actual cells. And the folder itself has, like, the Excel sheet. Basically, at the end of it, I'll go through the Excel sheet now after this slide. But the Excel sheet at the end gives you a row of material parameters based on all your inputs. It's like based on your inputs. So if you have 17 things, it will give you a 17 already developed column. If you have 5 only, it will develop for 5. And I have, like, when I made this slide, I had only 8 examples. I think now I have 14 examples or so already in the folder. So at least initially I had 8. So I have written 8 there. So to go to the Excel sheet, so let me walk through this with you. So this, again, as I said, it's a pixel volume thing. So you do not touch it unless it's required later. I will tell you where it's required. So this, to make it more simplistic, I have the mixture definition also here, so that you can define actual mixture here, so that you don't have to worry about calculation. Like, you have, again, I have developed it for only 4 materials. I again in Excel sheet defining floor and material is a problematic thing, I would say. So I have defined it for 4 materials for now. But let's say in the top left, if you see there are few green cells. Should I increase this? So for few of the things, I already have the specific gravity defined. This specific gravity is defined to calculate the volume of the material. Like again, few people do it volume based, few people do it weight based mixing. We usually tend to do mass proportioning. So all this percentage proportioning are mass proportioning. It's not volume proportioning. So you can actually type in like again, I have not defined it as cement or anything because again, material one can be anything. So for us, because I have the 3.15 there, that's cement. And that's why I am writing it's OPC. This is limestone, this is fly ash, this is inert. The inert is not actually inert, but I have it as inert because I had a particle extra that I wanted to show you for just to set up example for a different particle size. So right now I have it set it for 100, meaning like this is the 100 and 0.4. This is example one that I already have set up. Like you have the input file already. What I'm trying to show you is like how that input file is generated. So once this is there, the Excel sheet does the volume calculation. And if you actually go to material one, then you can see this system size is that 100 by 100 pixel that I defined. Now it does you the volume based calculation for water, meaning like you should have 0.55%, 55% volume of water occupying the volume. Means the maximum you can have is like 0.44, meaning 44% is can be solid initially, assuming there's no porosity. Now if you have pores, that's a different story. So and this 0.65 is again the example two. As I said, I selected 0.65 and ended up getting the 58% porosity, right? So this is for that 0.65. If I select this to be 0.44, then everything in the Excel sheet changes. And this is where you get the input deck. Like you have everything copy pastable. Like you have this row that you have to copy paste into a dat file, and that's your input. I'll talk to you about further about this. I just wanted to show that that's that easy. Like everything gets done for you. Now, how can you select? Like, okay, this is defined for OPC. How can you select your own material? You might not have the same particle size distribution as mine, right? So if you see these green columns in the first two, I could hide the other calculation. I have just shown that they're here for just to show you how everything is done. But you can have the sieve size and the volume percentage written on each sieve copy pasted here. You can just simply copy paste your values. Delete everything that's not required in there. So that part is the green part. Everything is red, meaning like you don't touch it unless you know what it is doing. But what it's basically doing is like again those equations that I told you, equivalent volume of each for two. You can go into that and actually check the cells and know what equation is used and cross check if they are like you understand what it is. So and basically does the cumulative for the volume, all the things that you have to do personally by hand, the Excel sheet does for you. And when I say like this is the green arrow thing that you might have to change, but you usually will not have to. Meaning like if you see there's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, there's no 22, right? By chance, let's say your material has a 22 sieve size, like you have a 22 micron size that you actually want to put. And this, you do not have to put personally. This will show you 22 if you have 22. If I change there something to be 20 less than 22 and greater than 20, you will get a 22 value. But it does not update this cell for that. So you might have to update this cell, copy paste from that Excel sheet basically. And once you have this, you can see like this is the total particle packing fraction, that theoretical value I told you guys about. Again, these are not correct. These are just for your assumption and for you to get an idea of like what might need to increase. The end product is always going to be from the software, right? So similarly, based on this, there's material 2 defined. You don't need to do anything in material 2 because once you define the particle volume fraction in material 1, that's what it does. Because there's no material in material 2, it's basically 0, as you can see. It does this thing for 3, 4, and then it basically has a whole sequence where it has to generate input. Now there are few things you have to select here. Those are the many things. Like these are the material definition 4. Again, useful only if we do hydration. If we don't do hydration, for particle distribution, you could select everything to be 1 and you should be okay. The best part will be like on visualization part, if you do select different material numbers, you will get different colors. So you will kind of get idea of like, okay, this is my particle for this is my particle for this. You will get that idea. Even not for hydration, then also it will be useful for that. This again, based on whatever you already selected, it's gonna define for you. Like the way I said, there were 15 pins, 17 pins. This one has 20 different sizes that is required to be kept there. This part, the green part that you see is like dispersion factor is basically how close do you want to your particle to be? Is there something repulsing your particle? Do you want actually to make sure that they are apart? Then you can actually play around with this. I think this goes from 0 to 1. Depending on the numbers, the particles will be placed closer or farther away. Again, calcium sulfate, the gypsum that you want, the type of hydrides and anhydrides percentage that you take. Again, useful for hydration only. Okay, I'm just showing you that for future use, at least you have an idea like, okay, if you want to use this software in the future, then you know that what's going on in here. So those are there. And these two are basically your output file. Like you can name anything, you can leave those names be like that, because these are the files that build MS will give you as a microstructure file, and we'll use that to generate the images. So based on that, like this is gonna be your input deck, right? Just for the sake of this, if you copy this, you just open a notepad file now, paste it, save it as anything.dat. Just make it a dat file when you save it. So once you save it as dat file, I think you already have it with you for this. But once you have it, save it as dat file, then you basically load that file and run the build MS thing. Like it's just a click of a button that you have to do. If you already have the file for example one, it's already the file is run. The images are also there in the example. The microstructure file is also already there. But if you just want to have a try, just choose .dat, click the example one .dat thing that we already have, and just run build MS. So what it does is like once you run build MS, it gives you these two output file. Like if you remember the cells where I said you have to define two files, it's written on the left side of it what the files are. What it does is like the AM file that you was defined first gives you the actual microstructure. There's a P file that you can download, again not required here mostly. It has like the type of phase fraction, like what phase fraction is it, like in a cement, like let's say this is the C2S, C3S, what it does after like actual hydration. Also we can see how the hydration products are formed, and all those things go into that. Those come into picture like only on hydration mostly, but again it for now it does create the P file also. So with these files, this is basically a executional thing, so you can actually see what it does, like what it runs. I'll run the file once I get over with this. Like I'll go around about it. I don't know if it's gonna be good enough zoom that you guys see, but at least if you guys run that, I can talk to you about how it's basically taking on the inputs and what it's showing up on the field. Once you have that, you basically download this am.file, and always I'll recommend you download it on a different directory, because you will generate images in the same directory that the file is. And if you download it in desktop, you'll have 100 images on desktop, which you'll have to manage later. So rather initially itself, just download it on a different directory. And once that directory is downloaded, maybe I'll go through an example first so that we see it in action basically. And I'll then talk to like what the actual images give you. So this is your app, right? So you just go to build MS, click choose .dat. Let me put this here so that I can see. Yeah, so for right now, I'm just gonna download the first example one.dat. And I just loaded that file, example one.dat. I just click run build MS. It does the thing, and basically if there's some error, it will say some error. And that error is going to be mostly when you select a particle fraction so high that it can't disperse the spheres. And in the end, like if you scroll down, you will see here that could not disperse by sphere number so and so, basically meaning that the spheres were so many that it can't distribute within the volume. So that way you just decrease the particle volume fraction and you get the new input file for the reduced particle volume fraction. And like this is the menu. Like if I gave you this software without the input file, what you would have to do is like basically go into this each line. It says like enter the number of particle size that you have, enter the first class, what is the number of first class, what is the radius of the first class, what is the material of the first class, and it keeps on going like that. You have to input it manually if you do not use that. So again, chances of making mistakes are high, and chances of not understanding it also is high. Like in between, you might be like, oh, what did I put? What did I not put? You might means you can maybe you will do 100 micron size for OPC, but there was 100 micron for size for limestone, which you already forgot. So those kind of things, this software, the input deck itself handles. And if you see like the way I told you, like at the end, once the particles are done, it basically selects the menu for outputting the file results. So once you select the output file results, you'll see here down there, once you select that four thing that I told you, right? There was 4 and 5. 4 basically means that you are output asking the system to show the output of the file. Meaning like after that 4, you can see like, okay, the total count, voxel counts are that, of which you will see like there are altogether n number of particles for all this, and you'll see here like there's porosity. So I think this is the one for first example. So you have 72%. I thought I wrote 70%, but I think there's 72% is porosity on this one, and 26% is cement because it only has cement. But if you remember, I defined 0.05 for calcium sulfate, 0.6 for hydrides, and for anhydrides 0.06. That those are like probabilities of a cement particle having a hydride, anhydride, gypsum particles. Basically, gypsum particles are present in cement to for setting and all those purposes. So defining them again is important for hydration. For the case of building microstructure, you can select those all 3 parameters to be 0, and the program will run fine. So it basically does the porosity. It selects it shows how many hydrates it formed, anhydrides, the number of anhydride particles it formed, and in the microstructure you'll be able to see like all this. Once that's done, the number 5 basically starts the program to save the files into the m underscore thing, the file name that we get. Once you have this, it exits the thing with the last. I think the last line on the system is 1, which basically makes asks it to exit and just give the files. Now you click download this thing, and you basically like it's shown on the next screen for me. You can even overwrite the already the file that was generated there in the example 1.5 for the MC150. Just overwrite it, save it, done. So again, this is the program already gave you, but you have a file that you can literally not read, not do anything, right? Like what does it actually contain? You could get the porosity. You could again there is a different system where we can load this and actually get the microstructure parameters and everything right away. Like we do not have to do the calculations. Like again, it's need to be included in this system itself. But right now it is as a standalone system in a MATLAB code. But like again, a user needs to know what they created, right? Wow, you have to have a feel of like, oh, what did this program give me? Oh, I got a bunch of number does not give help, right? Again, that's where the next thing comes up, which is basically these two softwares. Again, these two softwares, because again, visualizing 2D to 3D is a very hard problem. Again, as I said before, I'm not a software developer. I try to develop what I can. I could not develop it 2D to 3D, so that's why I have to use this ImageJ open source software. And this is again it's an in-house developed 2D visualization software, because again we had our own file that we particularly needed to be a certain way. I think this is the software is taking a lot of time to install. I don't know why. The basic knowledge I have from MATLAB is what I use to create this software. It kind of like installed okay on my system. I don't know if it's because like a certain system having MATLAB, it might be quicker. And for a certain system which does not already have a MATLAB installed, maybe it's slower. I do not know that for sure. But again, you guys can see if it installs quicker if it's a MATLAB, but hopefully everybody has installed it. So what this software does is basically it takes the file and it just generates the image slices. It does nothing else. It's just like you already have the file. You can select the file and it will generate you the images. So because it's said to be a 100 by 100 system, we have 100 slices defined right now. again, in future, we are trying to make it such that you can define on the number of slices you want to create actually from it. For a 800 system, you could end up creating 800 slices, or you might want to create just 80, right? Like you might not want as much of a precision. Again, usually the more number of slices you create, it will be more precise, because when you actually view a 3D view, it's projecting based on two slices, like it should be a sphere. Which again, if you have more slices, it will be a more better projection than having lesser slices. Having more pixels will be even more better projection, right? So if you have this software open, what you can do is, like, because it's set at 100, do not put any value other than 100, because it tends to distort the image. Then you can basically select the file that you just downloaded. Did I not get the? It's somewhere open now. Because I don't know. I have, oh yeah, it opened here, I guess. Yep. So the amp underscore C150 file that you already downloaded for OPC, right? You can just click that file, then it will start generating, and once it does, it just says processing complete. Images are saved in the same directory. You already had the images, so again, you will most probably, if you delete it, you'll know that the new images are created. Neither then it just overwrites the previous images. So you will not have, like, if you have already 100 images, doesn't mean you will have another 100. It will just overwrite the already existing image, because I think the way it's developed is like it does image 1, 2, 3, 4, 5, 6, and if there's already a file, it just has to overwrite. It will not do 100, 102 based on that. So once you have these images, let me close this. I think I might need it. I'll just put it on the background. So once you have this done, now you have all these images. This is for example 2. So you'll not have a as packed of a microstructure for example 1, because knowingly I kept more porosity in example 1. I think it's at 72% is porosity right now. So meaning, like, it won't be as jam packed as this is. Which again, if you go to example 2, this is, I think this is example 2. It will be as jam packed as you see in the screen. Okay, you will get a general idea of it. Like, the one thing that you should, again, it's kind of intuitive and not intuitive too. Like, the particle that you see here are spheres, right? They are not circles. So spheres, if you cut at different sections, means like from a 5 micron particle, you might end up getting a 2 micron circle in the image. It's just because it's a different slice. The actual volume is the same 5 micron sphere it is. Now you cut actually at the center versus a side by, the particles look different. So sometimes you might see these particles look like, oh, I did not put as many of a smaller particles. Why are there so many smaller particles in a section? It's just like an outside portion of 5 micron. Think of it as like, right, in a system, if you have 15 micron, when you cut slices, it will give you 1 micron, 2 micron, 3 micron, everything within that. And there are very less number of these particles. So you will not see in most figures, you won't see those large particles. It's in the central figure that you'll mostly see. Once you have these images, again, for visualization, you can use another software. This is like a 2D visualization. You want it everything into one, and you actually want to visualize it. Then this is an open source software, very good. I would recommend the use of this software for a lot of things. Like, again, it has a lot of function. You can actually do contrast images and calculate like the white areas versus black areas to calculate like porosities, calculate different things. Like, it has a lot of functionality. I'm just gonna stick to what I need right now. So I'm gonna show you how to actually load these images. So if you go to file, import an image sequence, because these are 100 sequence images, right? So you just can select that. And once you select that, for the case of visualization, I'll select example 2's result. I already have the results here. So I'm just going to select example 2 so that it looks more proper. Once you select the folder, you can just click on OK. You don't have to check any settings down there. It already updates that there are like this many files. And if it's not an image, it will not load. So you don't have to worry about it. So once that is there, uh, so we have to move this. Yeah. So you'll see that the image is not as pretty as a sphere, because again, with the 100 pixel size, and 1 micron, 2 micron particles also coming in. Few particles look slightly distorted. Again, the bigger the particle, it looks more better. Again, if you do this same thing with 800 pixel or 1000 pixel, it will be even better. Like it will look like more circular particles, meaning like it's again like the cross between like how bigger of a size do you want to generate, how longer do you want to simulate, and what you actually get, right? Like the this is for the process of demonstration, I just selected 100 because it's a small enough size, but big enough that I can actually make people visualize what actually is going there. So if you slide, you have all the 100 images loaded now. You can actually see the particle getting big and small. If you see, that basically gives you an idea that okay, this was not a smaller particle, it's just the slices of the bigger sphere that we see. Rather than that, this, there's even a better visualization on this, which is basically plugins, 3D, and volume viewer. If you go to plugins, 3D, and volume viewer, what it does is like it already loads the 100 slices and tries to create a generic volume. And the best part of this one is if you saw the slider there, right? One thing I'll ask you to do is like basically put this global alpha offset to maximum so that actually the posts look white and the other colors look completely as they are. It's in like 2D gradient and you have like global alpha offset. If you put that to maximum, you see the voids as white and the particles color as more dominant. Sorry? Oh yeah. So if you go to the thing, there's file, import, image sequences. And in that, you just have to select the, in the browse, you just have to select the folder. You just select the folder, it understands what the file inside is. There are already 100 plus one image file plus one actual input file, right? There are 102 files. That's the count. You see that 102. But because 100 of them are only image, it just ignores the two. So you don't have to worry about ignoring. It just does it for you. So once you do that, once you load, it's plugin 3D volume viewer. Again, you'll most probably get like tutorial of how to use image a lot in online. Like again, this is a simple specific thing that I'm showing you here. It has a lot of functionality. If you start using it, you most probably end up using image for a lot of your activities. Like you will find that this is very useful tool to use. So once you have that, you see this volume, right? You see the distributions, like this sphere was cut from this side because it has to be cut at 100. You see that those all the stacked images are such that it basically has that particle, like cut all the sections kind of viewable, like all the corner stops are like there are like corner edges and all those things visualized. If you see this sphere, it was cut from this side on this side also to basically fit in there, all those. And the way you had only slices in one direction initially when you load, right? If you have here, if you see this, you have slices in all three directions. This is your slice on, I think that's X direction. The middle one is your Y direction. You can actually have all those slices if you see. And even you can have the same slices on Z direction for this to visualize actually like how the particles are distributed and everything. You see the red color is defined for OPC. There you see some blue colors, right? I only defined one thing. But I did not actually define one thing because there were anhydrides, hydrides, basically gypsum, right? If you put zero, there will be only red. For calcium sulfate and all those things, if you put zero value, you'll only see red particles, meaning like there's only OPC. Again, because it's very important in hydration part of it, we have it defined. When I ran this simulation, I just kept the values there for OPC. So hydrates and anhydrides are present. Those are the blue circles that you see there. I think anhydrides are cyan color, not blue. So you'll see like two different colors for hydrate and anhydride. So this is basically to view, like to understand like what you actually generated, like what the microstructure looks like, what it looks like. Again, you can play around with the images software. You can do a lot of things, like you can have black and white, all grayscales and all those things, all different things that you can do. Again, I'm not going to go into a lot of detail into what you can do in image. Rather, I would move on from this. And I think, yeah, so these were the things as such, right? Like I think I told you up to this point, like viewing volume. Now I have a bunch of examples already set for you. I have tried to describe what the each example is in the folder name as much as possible. Again, there's a limitation of what I can describe also, I guess. So I have tried to be as detailed as possible. But if you see, this is basically the OPC particle only with high porosity. If you want to run a model that was like normal porosity, means like I already increased the volume fraction such that we have very less porosity. That is like the 58%. Because I have 56% volume already occupied by water, that's why I'm going at 58%. Now, you don't want to account for water. You just want to see like if I compact OPC, what happens. Then you can end up increasing the volume fraction more and more to a certain extent that the system itself says, okay, I can't generate anything more. I'm done. So that's a point where you can reach up to. So the next thing I told you, like despite me selecting 65% is the volume porosity is 58%, all those things, right? Why is that the case? Like we talked about all the volume packing and everything, like how we can pack the best we can pack everything into a higher volume fraction like 0.7, 0.8, right? The thing is like this software does not try to mechanism where it selects some randomized sheet and at that sheet it creates the sphere. Meaning like let's say for the maximum packing, what you have to do is like for a bigger circle, you have to touch the other circle right away on the side and keep on jam packing everything so that they are like touching each other and there's no gap, like literally no gap possible, right? This software does not do that. You can actually use the whole thing, but it basically has a randomizing kind of assuming that in the generic sense you will not have a compacted. Even if you do a concrete mix with the perfect particle size distribution, everything such that it could have jam packed into a very high dense system, it will not do it that for you because again there's randomness in nature, right? Like in actual computer system getting randomness is hard, so it does a randomness with a certain sequence, so you'll usually end up with the same value. You'll end up having the similar kind of microstructure. It will not differ much, it will not differ significantly, but it will not, most probably it will never give you like the jam packed volume, like where there's no literal gap. Like even if you open the images, you can see from the images that the gap between particles to particle, right? What it started with is just putting a, it opened here, but if you see each image, what you can see is like it started with putting a larger particle and started surrounding it with smaller particles. Now there was no space to put some particles also. Now let's say if I added maybe 1 micron particles, it has more space to put 1 micron particles, right? So I can add material to as like a 1 micron particle only, and I could keep on adding it till like it jam packs, kind of showing you like let's say you want to, you already have this OPC. Now how do you want to pack it? Maybe start with a 4 micron particle. Maybe you can get a material that you can sieve it to such that it just has 4 micron particle. You start adding those 4 micron particle into the system. Now again that jam packs it. Now start adding 3 micron particle, 2 micron particle, 1 micron particle. You can keep on adding to this particle. But again, the system already defined the particles to be somewhere, right? So it won't move that particle to add just another particle. Even if it has a zero point 0.5 gap there, 0.5 gap here, it won't move it towards the right to put that 1 micron particle there. If it has a 1 micron particle left, space left, is only when it puts it. So it's kind of like a more randomized rather than a very jam packed, like what is the theoretical limit you can reach. It's not, it does not take it to the theoretical limit. So again, I have this as for the limestone one. This is one of the other printable mix that we had. This is L30, meaning like 30% limestone, 70% OPC at 0.35. So if I went with the calculations for this, I had the calculation somewhere. I had it written on a paper, but I had to basically in this, the volume percentage of water was 52%, I guess, 51, 52% by volume. Like in OPC, because I had to go 54, right? Because I had to go 0.4 percentage, 0.4 water binder ratio. I was at 56, sorry. I was at 56 percentage volume. With L30, I am at 52 something. So I again, for this also optimize it such that this is a general value that I selected initially. and then I kept on adding to it so that I can reach the limit where the software starts saying like, okay, I'm done. This is the maximum I can do. Now I can't put spares. Meaning like this is kind of like pushing the limit. I think I have still some limit you can add up to. Sorry, this is not the limit that I pushed to. Sorry, this is the limit where I pushed it up to 56%, 46%. Because 52, again, I wanted water to be there. So I'm just pushing it to the limit so that I'm reaching that volume fraction of water is still there, like the porosity to include that water. The one where I tried to push the limit is like, again, I have like OPC, then I have like OPC with, I think I put like one with three materials, also fly ash, yeah. OPC, like cement, limestone, fly ash. Then I have one with cement, limestone, fly ash, and an inert material, showing that with four materials. Like to generate this, you can keep on checking like the values. I can even provide you the values what I use to generate the actual input file. But again, you can keep on increasing the particle fraction. You generate the input file, you run the input file, you check the output. Now, if you keep on want to adding to the actual porosity, again, that's the thing. Like if you want to jam pack everything and see what I can get to the maximum, you keep on increasing till the software says like, okay, I can't put spares, any more spares. If you want to push it to the limit that you want porosity for water to still be there, you just move it such that you check the porosity. Like if you remember, I showed you at a point it just has a force selection and it starts giving you porosity value, solid fraction, amount, number of cement particles, number of anhydrous, number of limestone, number of inert materials, and all those kind of like in a list. So you check those values and you put it to a porosity such that you have the porosity to accommodate that water. This, I think, like, yeah. So 9, 10, 11, 12, 13, 14 is what I, when in the morning, like when aggregate packing, everything came up, I thought like I'll put some of the aggregate packing in there to kind of show you what it is like. I'll most probably get the paper, okay? I think I had this here. I did this sitting here listening to the lecture, so I do not remember all the values I kept here. So like if you see example 9, that's only 2 micron particle. Like again, just for example, I wanted to create that, and to show you for that, same for aggregate. So in that same folder, I created a file called for aggregate. It's the same Excel file that I showed you before to create the input file. But for the ease of showing you, what I did is like, again, you don't have to have all this particle size. Okay, you can just type to 100%. But whatever I already had, I just removed everything, and for 2 I put 100%. And when I put 100%, it creates me number of 2 micron particle sizes. Again, remember, it's not making the 2 particle sit side by side so that it fills up everything. It's not a 50 elements in a row, 50 elements in a column kind of thing. It randomly is sitting. Meaning like it starts at a point, it starts distributing at random points so that it creates a microstructure. So it won't reach the maximum limit of 2 micron particle. But with the random seeding, you can start playing around saying that, okay, what is the packing limit I can go to? So we started with, I think this one starts with 55 and still could not do 55. So I had to go 50. So I started with a 50 particle. And this does not have anything else than the particles. So what you end up getting is 50% in the porosity itself when you actually run the build MS also. So if you put 50% and if you run this model, you'll actually get 50% porosity in the build MS. Now, similarly, for material, I think I did it material 1 when I did it. If you have the input file, if you run the input file, I think the input file has everything as material 1. I did not put it as aggregate. I just put it as different materials so that I can see the color gradient. I'll show you the pictures for it also. I put it as different materials, and for second, I just put like nearby. I did not have 4, but again, nearby 4 is fine. I think I put it at 3.99 something. So I put 100% as that particle. It calculates the equivalent volume for that, which again, because it's not 100, it's not exactly 4 micrometer. For a 4 micrometer particle size, it calculates a 99% equivalent volume. And again, it gives you the value, right? So for this, again, the initial itself did not work for 50. I had to go 50. I had to go 35% is packing fraction by the point I actually got it. Meaning like trying to show you like, be it not be optimized, but for random seeding also, right? when you go larger particles, now you see that, right? Like the volume fraction is decreasing. Like you can't actually randomly distribute a smaller particle size to get more lesser porosity. You will have to have like at a point have different sizes so that it can kind of fit in. Because I did not have as much of a different sizes. I just selected 2, 4, 8, 16. And similarly, I have created like the file that you have is like kind of towards the limit. If you increase it slightly also on the number of particles that is defined, because this is simply one single particle, right? You are defining only single particle. So you could end up just changing the particle numbers in the input file. If you see the input file, there's one single large particle size saying 920. So instead of 920, you can type in 940 itself and just run the model. Because it's a single particle, you can end up seeing like how much can you push it to, like how many particles can you fit in into the system. So like that, similarly for 8, similarly for 16, I did it. And like for this, I think it ended up being, you see, right, 2 per micron, it was 50. For 4 micron, I had to go to 40. For 8 and 16, I had to go to 35%. I had to have the remaining as pores, because again, like the random seeding did not allow me to put, I already put a 16 micron diameter particle, right? Instead, when you put 2, chances of putting a 2 is very high. When I put 16, the other 16 fitting between 2 16 is very low, because now you have to actually have 16 micron, the gap between two particles, right? So that way the porosity increases even just for a random seeding too. With this, what I ended up doing at the end is, again, I have this mixture defined, right? So I can actually play around with the 4 different particle size, 4 different proportions. Meaning like I do not want to have 100% of a 2 micron size. I would rather have 50% of 2 micron, 40% of 4 micron, 10% of 8 micron maybe. So for that, I think like the example 13 has like 70, 15, 10 and 5%, which basically gave me a porosity of 55%. I think 50%, sorry. This again went to 50%. Like it could go maximum for the random seeding could go up to 50%. Now I wanted to optimize it. Again, I did not have much time to optimize it. So another one that I tried is like a 40, 30, 20 and 10. So basically what I did was like I had everything ready. So I just typed in 40, 30, 20, 10. Again, I have not restricted anyone to put it to 110 percentage proportion, but I have put a check saying like total is equals to 100, so that nobody puts it like 120 percentage proportion, because you want to have it at 100. You don't want 20 percentage extra in the same volume. So I just selected this. Like again, this is a random number I selected. I did not optimize it or something. For this way, I could go to 55%. I could go to 55% particle packing, and I could have 45% porosity. Kind of trying to give you a picture like, okay, with different sizes, you can actually push the limits. Like you can start pushing. Now, if I added 1 micron particle here, most probably there is a space to put 1 micron particle, right? My smallest particle right now is 2 micron. If I add another 1 micron, I have more space, meaning like I could push more particles in. And that will most probably end up giving me more volume, solid volume, because now, be it the system is the same. Think of it as such. Like maybe I can even load the picture and show you this, so that, yeah, seems pretty jam packed. But again, there are few gaps somewhere in between. Maybe like a 1 micron particle size might fit. Again, this is in terms of micron, right? Like let's say the smallest particle already was 5 micron. You could have fit in 1 micron, 2 micron, 3 micron, 4 micron. So those kind of things, like you can play around with the actual material you have. Maybe like again, you might end up sieving materials to actually get a certain sieve size, and you can play around with like how much percentage of a certain sieve size should I have to actually end up getting a better packing. How can I end up getting like the particles to be together? And again, this is in terms of picture. Now you have to have a number, right? You have to actually characterize this. You can't just have a picture say like, oh, I think like this looks better. And porosity wise also, like it's a different story, right? So there comes the whole concept of actual material parameters. Like define it in terms of number. Defining something in terms of number is always better. Like again, I think Professor Nethala went over all this, like what each represent. Each has a actual significance, why they are used for defining that generalized microstructure parameter. again, I think there are 2 or 3 papers we wrote kind of like based on this. Like it's that important. Like it governs the yield stress, it governs viscosity, it governs for USBCs, like the strength that you can gain. Like with this microstructure packing being better, we could end up getting like the USBC strength to 160, 180, and all those things. So this goes into like packing model as defining the microstructure, even defining in terms of 3D printing. Like these could correlate into like there's a whole graph. I should have put that here. I think you would have seen that in one of the slide, but I don't know if you saw it today. I think it's tomorrow or something. So it's basically with increasing particle packing parameter, you have like a 5 square increasing, and with increasing 5 square, you have like the yield stress increasing. So it's kind of an indicative of that also. Like you have an indication of like, okay, what kind of yield stress do you assume this material to have? So all this these images are what generates this, like the number of particles per voxel, the Cn basically being the coordination number, meaning like how many particles are within a radius. Like now again, this is something you yourself can define. Do you want, let's say you have a 16 micrometer particle, means your radius is 8 micrometer, meaning r by 2 distance is 4 micrometer. The chance of the surface of that 16 micrometer particle being 4 micrometer from a particle is very high. A 2 micrometer means like half is radius is 1, half is 0.5. A particle being within 0.5 for that is very low. So basically that Cn kind of like accumulates that. Like if you have a certain size only, most probably for all particles you will have similar Cn. But because now you have like a distribution of particles, right? That coordination numbers give you like an average of like all particles, like how close are all the particles together to. Like is a particle like close by to the other particle in terms of their radius, not in terms of the overall volume, but like for a particle we are defining it in terms of that particle itself. So for bigger volumes, it could most probably end up being higher. Smaller particles, it most probably will end up being lower. And MCD being the distance between these particles. Like again, it's another parameter where it's surface to the particle, like the closest one. If you have high micron means between particles you have a lot of porosity. If you have the particles too close by, that MCD kind of goes down. So those kind of parameters are there. We'll end up kind of like developing this into the system itself. Like when you generate the microstructure, next step you can actually get these parameters right away. For different reasons, they are not still incorporated into the actual system. But the way we are using it right now, it's in terms of a MATLAB code. With I think I have not shared this with you because it's kind of like development itself, where it's a kind of a MATLAB that generates a GUI rather than a actual GUI being there. So the microstructure that you generated, right? What you can do is like just load the microstructure. I'll do this one. Yeah, you can just load the microstructure. This thing is like, again, we have defined it as a radius value also. The latest one, we have defined it as half the radius. So I am kind of limiting it to half the radius. Again, this program can be rewritten into defining it for like, if you want it at 2R, also you can define it at 2R. Everything will be defined at 2R. So similarly, if you have it defined at R by 2 versus 2R, obviously 2R will give you higher Cn, meaning like you will get a higher microstructure parameter value. But if you define it for 2R for everything, then they at least will be comparable between them. It will not be comparable. Like you can't define for a system at 2R and for another at R by 2 and say like, oh, this has a higher microstructure and this has a lesser microstructure. But again, to allow the users to actually have the freedom to define that value, you can end up like the maximum you can define is 0.5. Yeah, 0 to 0.5. So it's limited to 0.5. You can even want to like, okay, I don't want to do 0.5 also. I want to do 0.25 because my particles are too close. So I want to have some kind of differences. So you can define that. Again, the system size is 100 because again, the whole system size right now, everything is defined by for 100x, 100x, 100. So this is something in future we'll be able to kind of like define this. But for now, I have just developed it into such that right now it's definable, but we just can use 100 for now there. This voxel spacing is like again based on calculations for 100 by 100. These are like 1 micrometer particle is going to that kind of pixel size. So that's the calculation that we had from the voxel volume, and that is like set right now. If we have 800, there will be a newer number for that. What I'm thinking of is like we'll most probably put it like, okay, if you have this, you should have this value. If you use this, so kind of define it the other way rather than the spacing. We define the user to say like, okay, what's your actual particle size, and based on system size and particle size, the system itself loads the particle spacing. And once you have that, you just run the analysis, meaning like it scans the thing, it tries to read all the particles and tries to come up with all this value for you. Like you can't go into the picture and start measuring its distance, right? So what it does is like it automatically does that for a certain particle. It tries to find how many particles are within a certain radius. For a certain particle, it tries to see the distance between adjacent particles and see come up with the lowest distance. And what it does is like it averages it out. Like you have like 1,400 particles, right? If it was for a single particle, you could most probably end up going into the picture and calculating this also. But for 1,400 particles, 1,800 particles, 2,000 particles, you can't calculate it yourself, right? So what this software basically does is like calculates it for you, gives you the value output, and between like different particle parameters, like between this system versus that system, you could calculate the parameters and check like, okay, which system might be better. Again, it's not a established equation that okay, if you have a k parameter of 0.1, you should have a yield stress of 1,000. It's not kind of defined, but you can most probably assume that if you have a parameter of 1 versus if you have a parameter of 2, most probably your 2 parameter is going to have higher yield stress than the 1. So those kind of comparison you can have, like for a certain mixers, like can I incorporate some kind of aggregate so that I can get higher structural parameters, so that most probably I'll end up being printable plus being like more having more yield stress. So those kind of things is what we can play around with this. I think am I over time or done? So these are the kind of things I had for presentation. Again, if somebody has any question, I'm happy to try to answer them. Maybe I'll not answer all the questions, but again, I'll try to answer it to my best. And again, as told, hopefully sooner than later, this will be completely developed and anybody can download in their Windows system, not a Mac. I think we'll never develop it for Mac, but for Windows, they can download it, run it for themselves. It will be open source. I think right now we have the thing linking to Professor Nethala's lab page where we have the download link. So we'll update that. Like as the versions come up, we'll just update that and we'll keep on developing on this. Like again, there might be a lot of bugs which I might have not found it, right? With programming, always that's the case. So we'll keep on updating that. Once something is fixed, once some upgrade is there, it will go onto the system right away. You can download. Most probably what I'll try to do is like have a readme file. I think we don't have a readme file yet. We'll have a readme file where we can actually, again, somebody who has not actually seen this or who has seen this at least can go read that and kind of refresh their memory saying that, okay, I should have done this or done that. So we'll have that. And hopefully, like again, I'm not going to promise you a date, but again, hopefully sooner than later, you'll have the whole system. And again, I did not show you guys this, but what it does is like from this same am file, the am and p file that you have, this will have like build ms will have a input file for those. Because here you don't have to do much. Build ms only requires one another file to distinguish the cement type and how the hydration happens. That again is a debload file. So you can load all 3 files and you'll end up getting the distribute ms output from there. That output will go to the hydration model and you'll get a hydration output from there. There will be some parameters you have to define in the hydration, saying that do you want like hydration for each day till 28 days? Do you want it at 25 degrees Celsius, 50 degrees Celsius? Do you want it? So those kind of parameters will be there most probably, but except that at least build ms, you should have it quicker, earlier than later, hopefully as early as possible. Yeah, so I think I'm done with my presentation. So any questions, anything in generic sense?
Okay, specifically what is the outputs that we can expect in the distributed machine and
So basically the output 2 files, these 2 files are generated for distribute ms. What distribute ms does is like basically tries to define it further into like what is C3A, what is C3S, C4 as AH, all these things. Like it tries to distribute everything again, and this go as an input, and that gives you a single output file which basically has that microstructure distributed now. you only had a particle. Now that particle is also distributed into fractions, and that fractions now go into the hydrate ms, which basically gives you the hydrate ms has a lot of files. Like it has like is it 25 degrees celsius, 50 degrees celsius, is it like certain days, certain things. Again, those will mostly be defined by the user, because this has been done in directions before. We know that what to expect out of it. The thing is, the app is not running it right now, so there will be a bunch of outputs for hydrate ms. And once you have the hydrate ms, you will see like they have the file actually has like hydration at this day at 50 degrees celsius, abatic condition, all those kind of things, those are there. So those will be generated by that. Right now, packing only. Like again, we will develop future. Like that's gonna take a lot of time.
Just get the parking part.
Mhm.
And that does parking for all the blend like this one and not for the actual
Yes.
like which is computation size. That's all.
Yeah. So that part is what I forgot to mention. I guess this is 100 micron kind of size, right? So you can't do a 4 particle aggregate right now. Yeah.
1,000, 2,000, if you want to spend a lot of time looking for things still we have
No, meaning for simplicity, what you can do is like if you have a 2 particle size, you can assume that as 2 micron, and everything that is generated is in terms of 100 now. It is just scaling it down. So you can scale down the particles. I am actually using the size I need, but you can actually use the scale down size also here to generate those microstructure.
it's like a distribution of this, and then you can discretize a particle size distribution into maybe 10 or 20 sizes that you can. We are actually going to do a way in which you can do the particle size distribution completely, but until then, you can discretize it into whatever number of sizes that you want, and you can scale the particles. For example, the maximum particle size says 500 microns, you can scale everything to 100 microns. So everything is 50 microns, because eventually the velocity that you get, the power density that you get, is independent of
The size.
sizes. It's only the ratio of sizes. So you can do it in whatever. Like you take a small structure simulation of the equator, you get results possible. So what was the maximum pattern which you could do?
Sorry?
What was the maximum pattern you could do for any particular mix?
Yeah, like as Professor Nethala showed afternoon, right? We had like this same thing was used in a different sense for aggregate packing for USPC, and we had like so he showed like 60, 70, 0.7. Those packing fractions that he showed are like basically kind of like developed with this build MS thing. It's not a software, that was like a C++ code with the file only. That's where it comes out. Like we had those done as such for a C++ code. So those are basically the output from here itself.
But it's just a small maximum height density. Depends on the size range of particles. Like I said, you can get so if you make cement particle size distribution that has like 100 micron maximum size and 1 micron smaller size. You can pack that you will make it depending on the number of particles. You can choose the number of particles, different sizes to get the maximum particle packing density. Sure. So you have one idea itself also. You guys have what we have achieved in the maximum. And then can be both companies itself can get actual results in the lab. Of what? Of any kind of use with the maximum package. No, because maximum planting density, for example, if you take if they take that, right? Your maximum planting density, if you have one size package, it's like a sugar number 4 aggregates level. You use a very hard that's where you pack it to the maximum in your pocket. You will get, depending on the size, you should ideally get more than 0.7. If you get more than 0.7, it's a meaningful multiple particles. So if you have one particle, now you take that multiple particle sizes and use the compressible packing model, you can get the maximum packing density corresponding to that range of particles. And you can try it out including the model that you pretty much will get very close. So it is you can the and verify that you can get that. That's it. Again, the assumption is that the particles are all spread as in real life can be different, and that difference you can. in different. But that can always be something. So maybe have this software view once we get details into everybody. You can download it. So it'll have multiple functionalities. You can do it based on particle sizes. You can base random, you can do based on reverse also. Given a particle size of cement via limestone, whatever, what proportions will give me the maximum value density? I think you can do the reverse if you want to do it and make sure that the reverse problem can be solved. So the optimization can be made easy. But you see that, you see the complications and trying to make it into a solve. It is very easy to explain it into slides. What is it actually developed in the form of it's not especially if you don't know how to put the right inputs, then you can take a jump.
If nobody has any other questions, we are gonna move on to quiz for the day. Yeah.
I think it's very hard because